Hello guys. What are we basically going to cover from basics to advanced? This will be specifically related to positions like data scientist, data analyst, related to business intelligence tool. Everything will get covered over here. We need to understand the basic differences between descriptive statistics and second one is inferential stats. The differences between descriptive stats and inferential stats, because the entire statistics with respect to data science is divided into these two concepts. In descriptive stats, some of the topics that I really want to mention is measure of central tendency, measure of dispersions. These are some of the examples. Anything that is related to summarizing the data. So all the tools that you're probably using like histograms, you're using boxplot, whisker plot, everything will probably come over here. If I subdivide many of the topics, here we are basically going to understand histograms. We're going to understand about PDF. We are going to understand about CDF. We are going to see that probably how do we create this PDF, by what techniques we create this PDF, CDF, everything. We'll also be understanding some topics like probability, permutations, which are pretty much, probability is very much important in terms for data science. Mean, median, mode. So you also have variance, standard deviation. We're going to cover many distributions. Let me name the distributions over here, like Gaussian distribution. Then you have log normal distribution, other type of distributions like binomial distribution. Then you have Bernoulli's distribution, Pareto distributions. This is also called as power law distribution. We'll also be discussing about standard normal distributions. The seventh thing that probably we will be discussing about is in standard normal distribution, we may also have different techniques. We'll be discussing about transformation. We'll be discussing about standardization. We'll be discussing about different kind of transformation. And this all will be with the help of Python also. We'll try to see. We'll discuss about something called as QQ plot. We'll try to find out how to determine whether a distribution is a normal distribution or not. That all things we will try to discuss. These are some of the topics that I have written. There is also something very much important which is called as inferential stats. Now in inferential stats, our main focus is basically like z-test, t-test, ANOVA test, chi-square test. If I just consider some example with respect to z-test, there are multiple ways to actually perform z-test. So in z-test, probably you will be having different ways. And this I will also try to show you by executing in Python. T-test also I'll be showing you by using Python programming language. Chi-square test, ANOVA test. So ANOVA test is also called as something called as F-test. We'll be discussing about this. Like factorial ANOVA, different kind of ANOVAs that we are going to discuss. Most important thing we forgot, right? Which is called as hypothesis testing. How can I forget this? Okay. So we are also going to discuss about hypothesis testing, right? In hypothesis testing, how do you determine your null hypothesis, alternate hypothesis, everything will probably get covered in this. Here we are specifically going to understand about p values. One very much important thing is something called as confidence intervals. Confidence interval. Then I'll also teach you how to see Z table, which is a kind of sheet where you can directly get the values over there. Similarly, T table is there, chi-square table is there. Many things will basically be there. Let's start the first topic. The first topic that obviously anybody needs to understand is that what is statistics. Okay, we really need to understand, because whatever I'm discussing, right, it is very much important in terms of interview. In terms of interview, I'm actually going to teach so that you will definitely be able to understand many things. So the first thing, we will understand what exactly is statistics. Many people have different kind of definition with statistics, but I really want to give a very simple definition, which is from Wikipedia. So I'm going to say statistics is the science of collecting, organizing, and analyzing data. Now, based on the amount of data that is getting generated, now you can just understand directly like how important stats is. You have tons and tons of data. You have huge amount of data, and definitely you can actually utilize this particular data to make sure that there is improvement in your products, there is improvement in your business goals, and that actually helps you to finally make a very good decision. So finally, why we are doing this for? Why we are doing this? We are doing this for better decision making. So we are specifically doing this for better decision making. Everything that is basically getting covered on this. And if I try to now define statistics or the types of statistics, first of all, there is one very important thing which is called as data. So data over here is nothing but facts or pieces of information that can be measured. So what is data? In short, a facts or pieces of information that can definitely be measured. And let's go ahead and let's see some of the examples. What do you think about data? Definitely, if I say that, okay, let's consider one very simple example. I am basically going to say that, fine, with respect to the data, I can give you lot of examples. So one example I can say that, let's see, if I want to measure the IQ of a class of the students, right? I want to measure the IQ of the students of the class. So I may probably get values between 0 to 100. Suppose let's say that I am getting this one, I'm getting this, I'm getting 55, I'm getting 75, I'm getting 65. So this is one example of data. Here we can basically measure, and the example is IQ of a class. Suppose I want to give one more examples. Okay, the ages of student of a class. I may have different ages like 30, 25, 24, 23, 27, 28. What is this? This is specifically data. And always remember, the most intrinsic meaning of data is that it can be measured. That is the most important thing. Types of statistics. The first type, as I said, is called something called as descriptive. So the first type is basically called as descriptive stats. Now, how do you define descriptive stats? Descriptive stats, I'll just say that it consists of organizing and summarizing of data. It consists of organizing and summarizing data. That's it. Very simple. If I really want to understand, I'll probably make you understand more about what is descriptive stats. But let's go towards the definition of inferential stats. Now, in inferential stats, you can basically say that it is a technique wherein we use the data that we have measured to form conclusions. Now, if I talk about two important things, one is conclusion and one is about data. Now, first of all, we will understand about descriptive stats, and then probably I'll give you a very good example. Okay, I'll try to give you a very good example, and based on that particular example, what is the type of question that may come up in descriptive stats? So let's consider that I have a classroom of math students, and in this classroom, let's consider that there are around 20 people. And now I want to find out the marks of the first sem, let's say. Now here probably the marks with respect to percentage are like this: 84, 86, 78, 72, 75, 65, 80, 81, 92, 95, 96, 97. So over here you can see how many data are there: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's consider that we have around 20 data. What is the average age of the students in the class? Student in the class. So this may be a perfect example of descriptive stats. Now here I've just told about the average. It can be anything. It can be standard deviation, it can be mean, it can be mode, it can be different things. So here you can see that I've taken a very simple example. I have a math students, like 20 people over here, and probably you can basically understand over here that we are trying to find out what is the average age of the student in the class. You may also say that what is the percentage of the people passing out from the class. You can also say that different examples probably you'll be able to understand when I talk about percentiles and all. Now let me go ahead and let me find out and let me tell you the other example of inferential stats. Based on this, what kind of question you can ask with respect to inferential stats? I've told you the definition. What inferential stats basically consist of? It is a technique wherein we use the data that we have measured to form conclusions. I may say that are the ages of the students of this classroom similar to the age of the college? Similar, and let's say age of the college, but age of the maths classroom in the college. So this is specifically my question. My question basically says that, are the ages of the student of this classroom similar to the age of the maths classroom in the college? So here, maths classroom in the entire college is my population. And probably just a classroom student's age is just like my sample. Sorry, did I discuss about maths? Okay, sorry. I'll not say age, but average marks. I'll just try to change over here. Just a second, guys. I'm extremely sorry. So this is not age, this is marks. So I'll not say this as ages. Let me, but you can also take ages as an example. I will say it as marks. Like that, let's consider the maths classroom. There are five different classrooms, and I've actually taken the data of only one classroom. And from this is basically called as sample. And this is my entire population. Now, since we have discussed about population and sample, and I'll be coming more on making you understand about descriptive when we are deep diving into various topics. Now it is time that we really understand about population and samples. So coming over here is basically population and sample. What exactly is population? Now, population basically means, let's consider one example again. See guys, I will definitely give you a lot of examples. The reason why I'm giving you examples is that because understand, if we learn statistics in such a way that we have examples in mind, we will be able to explain the interviewer in a very good way. So let's take an example of elections. Probably you may be talking about Goa, you may be talking about UP. Let's consider this two states. So obviously it is not possible. Probably let's consider that the election has finished and we really need to find out the exit poll. Now exit poll, what usually this press reporters and all will do, what they will do is that they cannot go and ask each and every person. Suppose the Goa population is this big. Let's consider. It is not possible for every reporter to go and ask each and every person that whom you have voted, because it is not possible. You may not find some people may be traveling, some people may be doing different things and all. So it is not possible at all. So what happens in this exit poll? This reporters, what they do is that they take up sample of population from different region. And again, there are different kinds of sampling techniques. They take up different samples, and then what they do is that they ask that whom did you vote, and based on that maximum number of people whom did they vote, they basically say, based on that they actually create their exit poll. Now in this particular case, what is my population data? My population data is this entire population of Goa. So this specific thing is my population data, and this round circles that I have actually done is basically my sample data. So I hope you have basically got some examples with respect to that. Guys, I hope everybody is clear with this. I basically told age over here, so don't get confused. Sometime when I'm teaching, sometimes students may come, ages may come, or marks may come. So you'll not get confused, don't worry. So here is one example. Now let's go ahead and let's try to understand one thing. Now in this particular scenario, in this particular example, many people have told about, Krish, why are you just considering, okay, you're considering samples to solve a particular problem. What are the different sampling techniques? You really need to understand or tell us that, because there are different sampling techniques. What are the different kind of sampling techniques? But before I go ahead, usually population, if I talk about population, you really need to understand about some of the notation. Population is basically given by capital N and sample is basically given by small n. So this is how we basically denote population. This is how we basically denote sample. Now the next question comes that, Krish, why you have selected samples randomly? Is there any better ways to do sampling also, or just we need to do the sample randomly? I would like to say that, guys, this entire sampling takes place based on various scenarios. And for that, I will be showing you some of the examples. So let's go and understand about some of the sampling techniques and what are different sampling techniques we basically have. The first sampling techniques, let me write it down for you. Now, the first sampling techniques, which is most of the time used, is called as simple random sampling. Simple random sampling. Very simple, very important. Suppose I have some data. I have some population. Suppose this is my population. Simple random sampling will be just like you go and pick up some people like this anyhow you want. There is no such confusion as such. You just go and randomly pick up people. simple random sampling. And simple random sampling is basically used in many of the scenarios. Probably in exit poll, you can use simple random sampling. Suppose if you want to use some kind of medicines, right? You do some kind of test for the medicines. At that point of time, you cannot use simple random sampling. You have to pick up some people, probably you have to check their medical history. Based on that, you have to apply. But simple random sampling, it's all about, I can basically say that, I'll just give you a small definition over here. When performing simple random sampling, every member of the population has an equal chance of being selected for your sample n. Now coming to the second type. The second type of sampling is called as stratified sampling. Let me give you a definition. Stratified sampling is a technique where the population, that is capital N, is split into non-overlapping groups. So one example, I'll be talking about it, don't worry. This is also called as strata. Strata basically means layering, stratified layering, like that we basically say. This is what a stratified sampling basically means. Let me give you one example. Let's consider gender. I want to do this sampling based on two things. One is male and female. Let's consider that I want to do a survey. And for a survey, obviously, I will be requiring some people. And based on that, my samples will basically be divided, right? Based on male and female. Male people will give different kind of survey. Female people may give different kind of survey. Okay. So something like this. So this is definitely one example. Any other example that you would like to say? Obviously, wherever you can see that there can be non-overlapping groups, obviously you can do it. Let me give you one more example. Suppose I want a survey to be done by 0 to 10 years of kids. I want the next, probably I'll try to make this kind of layerings based on age. Probably 10 to 20 will be one age group. Probably 20 to 40 will be another age group, and probably it will be 40 to 100 will be another age group. So based on different age group, I can also do a sampling. Understand one thing, this terminology is very much important. Non-overlapping. It should not overlap. Over here, there is no chance of overlapping. Based on profession, can I do stratified sampling? Based on profession, can I do stratified sampling? See, a profession may be that, let's say that this profession is with respect to different people who are working. Okay. Suppose a person is a .NET developer, a person is a PHP developer, a person is a data scientist, or he's working specifically in Python. Over here, definitely you can say that they have different stratified layers. But there may be some scenarios that it may overlap. A PHP person may know .NET, a .NET person may know Python. So both the scenarios will be there. If a person is highly experienced and he says that no, I don't know .NET, then it will not become overlapping. But definitely we can apply it for doctors, engineers, different survey can be there. So just understand that in some of the cases we can do stratified sampling, but by applying some other conditions, we can make sure that that sampling satisfies all the conditions. Coming to the third one. The third technique is basically called as systematic sampling. The third technique is called as systematic sampling. Here, from the population n, what we do, we just pick up every nth individual. I'll give you a very good example. Nth individual from this population. What does this basically mean? Let's consider that I'm outside the mall and I want to do a survey regarding COVID. So what I'm doing, every 7th or 8th person that I see, I am saying that for this person, do the survey. So in systematic sampling, you consider any 8th person. I'm just saying as an example, every 8th person. I may take every first person that I see, or every 5th person that I see, or every 10th person that I see in front of my eyes. I'll just tell him to do the survey. So this is what systematic sampling is all about. In systematic sampling, there is no reason why you're selecting the 8th or the 9th person. You just said that, okay, it is my personal duty. What I'm actually going to do, whichever person that I see on the 7th time, I'm just going to catch him and I'm going to basically ask him about this survey. So Thanos, when he snapped his finger, what do you think, what kind of sampling techniques may have used? Do you think random sampling is basically getting used? Because you could see, right? Probably random sampling may have been used. Okay, now let's come to the next sampling, which is called as You can say it as convenience sampling. You can say it as voluntary response sampling. I'll just say it as the fourth technique. I will say it as convenience sampling. This kind of samples, or suppose let's consider that I'm doing a survey. Only those people who are a domain expertise in that particular survey will be participating in that particular survey. Suppose let's say consider that I am doing a survey related to data science. I will say that any person who is probably interested in data science and has the knowledge of data science, if you consider only those people, then it basically becomes a convenience sampling. Only those people who are basically interested in this will basically be doing it, or who are expert in that will definitely be doing it, because this is a specific topic which requires domain knowledge, which require some amazing things in that. But basically he should be knowing based on this survey, because those surveys will be important. Through surveys you take out some kind of information, you will be able to make some kind of decision. So that is very much important, who is taking the survey. Like many people also, how do you generate your data set? That is also said. Like in many companies, what they do is that they make sure that the people actually try to put some kind of surveys in front of the people, and they basically use that data for doing different things. Again, I'm going to repeat what is convenience sampling. Let's consider that I am doing a survey related to a specific topic. In this particular example, data science. Obviously, I'll not go to some other people who don't have the knowledge of data science to do that specific survey. So I may collect my sample in a bit different way, where we'll focus on people who is giving that survey should have knowledge on that specific topic. Okay, now let me give you some of the examples. Let's say that there is an exit poll. What kind of sampling would be better? See guys, again people are getting confused with respect to stratified sampling and this sampling. In convenience sampling, we are just specifically considering a domain. There we are dividing groups based on something. So tell me the examples of exit poll. What kind of sampling technique we may use? So obviously we will be using over here as random sampling. See, RBI, I hope everybody knows RBI. They do something survey with respect to household surveys. For this household surveys, what kind of sampling probably they may use? See guys, you may also consider that over here you need to follow some stratified random sampling. Obviously we can do, but over here most of the time random sampling is basically done. In household surveys, RBI make sure that they have to fill the survey from a human, where probably they are trying to find out like what is the cost expenditure in running a house. So here you can probably consider stratified sampling. If you don't want to consider stratified sampling, we can also do convenience sampling. Only human you can basically consider over there, and you can do it. Now understand, sampling techniques may be different. It is completely dependent on the use case that we are following. Based on the use case that you really want to do, based on that you will do. And it is not like we will just be dependent on one kind of data. We try to use different sampling techniques, and finally we try to come to a conclusion on the same. Let me give you one more example. A drug needs to be tested. So for this, what kind of samples we may take? Now here I can bring up multiple use cases. First of all, to whom this drug needs to be tested. If I get that specific information, I will basically do the age groupings, and then I may probably apply. Let's consider this drug is for everyone. Probably then I may consider picking up some samples, but at least I'll put a condition that at least it should be greater than 15 years, because we cannot just directly use a specific drugs on kids. So different. It depends on the use case that you're probably trying to do, and based on that you will probably try to select it. And again, there may be many things, many questions that may come is that, okay Krish, why not this, why not that, why not this, why not that, right? This kind of questions may come. That is where we basically experiment with multiple things. So in the real world scenario also, when you are probably collecting the data, you will find this kind of scenarios a lot. Now let's go with the next topic, what is called as variables. Now what is a variable? Obviously if you are a coder, you obviously know that what is a variable. So I will just give you a definition that is much more related to you. I'll say that a variable is a property that can take on any value. A variable is a property that can take any value. Let's say an example. I'll say height. I may say weight. These are variables. We can have any value. We can have 170 centimeters, 172 centimeters, 185 centimeters, 190 centimeters, anything. I can have different values with respect to height. 182, 178, 168, 150, 160, 170, anything. Similarly, with respect to weight, I can have any values like 78, 99, 100, 60, 50, anything that I want. So this is a simple definition with respect to a simple variable with a lot of examples. Now, understand there are two kinds of variables. So let me go ahead and let me teach you this. There are two kinds of variables. The first kind is basically quantitative variable. Quantitative variable. The second type is basically you just say me the answer. I'll pause for 5 seconds. The second type is something called as qualitative variables. Qualitative or categorical variables. So these are the two types of variables that we specifically use. Now, I will try to divide this into many types and we'll try to understand these variables because these are also very much important. Now, first of all, coming to the quantitative part. This quantitative part will have some properties. It can be measured numerically. So we can measure them by putting numbers. We can perform a lot of operations like add, subtract, divide, multiply, right? We can perform any kind of operations that we want. So one example of this is I may consider age, I may consider weight, I may consider height. Some of the examples with respect to quantitative variable. If I say that, okay, age is a quantitative variable. In qualitative and categorical variables, if I specifically take an example, let's consider gender. In gender, I have male and female. Now, what does this basically mean? Based on some characteristics, we can derive some categorical variables or we can derive categorical variables. That basically means we have categories in categorical variables. Here we cannot add, subtract or do some kind of mathematical equations because here we don't have that option. Another example I may basically say that I may say, okay, I may have categories of, let's consider that I have IQ. IQ, if I say 0 to 10, I will divide this IQ 10 to 50 and 50 to 100. Whenever the values are between 0 to 10, I may say that less IQ. Whenever I say 10 to 50, I may say that medium IQ. Suppose I say this 50 to 100, I may say good IQ. I'm just saying this as an example. Now, based on some characteristics, I have derived or I have classified this into multiple categories, which is called as IQ. Here, don't tell me, sir, Krish, how, sir, like how, Krish, more than 50 you are saying that good IQ, then probably I'm just taking it as an example over here. Blood group is another example. I may have A positive, A negative, like that. I may have a lot of IQs. I may also say t-shirt size. Based on the properties, we may have large, XL, medium, small, this kind of things. Now coming to the quantitative part. Quantitative also has two different kind of categories. Obviously, we know quantitative basically means we have some numerical values. Here, I'm going to divide this into two. One is the discrete variables and one is the continuous variable. So, discrete variables and continuous variable. In discrete variable, you will specifically have a whole number. Let me just talk about some of the examples. Number of bank accounts of a person. In this particular case, the example is that you'll say that I have 2 bank account, 3 bank account, 4, 5, 6 bank account, 7 bank account. You can't say that you have 2.5 bank account. Another example that I would like to give, number of children in a family. So this is why another example. Here you obviously will say that, okay, there are 2 children, 3 children, 4 children, 5 children, but you cannot say it is 2.5 children or 3.5 children, right? Now let's go with respect to continuous variable. Here we have already discussed that any values it can have. Okay, suppose I say height, I can say that the person is 172.5 centimeters. I can say that the person is 162 centimeters. I can say a person is 163.5 centimeters. Any value that can come over here. Similarly, with respect to weight, here I can say the person is 100 kgs. I can say 99.5 kg. I may say 99.75 kgs. I can also talk about amount of rainfall, which is measured in inches. Suppose I say it is 1.1 inches, 1.25 inches, 1.35 inches, right? All these things are basically there. So this was an example with respect to continuous variables. I'll give you some examples. What kind of variable gender is? What kind of variable marital status is? What kind of variable river length is? What kind of variable the population of a state is? What kind of variable song length is? So gender is obviously a discrete one. I'll not say discrete, but I'll say categorical. Sorry, not discrete. Okay, so it is a qualitative or categorical variable. Marital status, again, same thing. River length, continuous. If I want to say discrete continuous or normal continuous, it will be a continuous quantitative variable. Population of the state, it will be discrete. And song length will also be continuous. What kind of variable blood pressure is? Blood pressure, it will also be continuous. What kind of variable is pin code? Discrete or categorical? Don't worry, as we go ahead in some of the classes, you will be able to understand this. Okay, that is where when you will be given a problem statement in data science where you have specifically pin code in a data set, how you are going to handle those. Okay, now let's go to the next one, next topic, variable measurement. So here we are probably going to understand how do we measure variables. So over here we basically have 4 different types of measured variable. The first type is nominal, the second type is ordinal, the third type is something called as interval, and the fourth type is something called as ratio. Now first of all, we'll try to understand about nominal. Probably I'll here also I'm going to give you a lot of examples and why it is very much necessary to know this kind of measured variables, 4 type of measured variables, because your data set will also have this kind of variables. You'll have nominal data, you'll have ordinal data, you'll have interval data, ratio related data, so that you'll be able to do a good data analysis. Okay, so you basically use this kind of variables. So if I talk about nominal variable, so nominal data also I can say, these are specifically categorical or qualitative data. So whenever I say categorical data, you know that it is split into different classes. Color is one example. You have example gender, you have example different things, type of flower. These are some of the examples with respect to the nominal data. Because the first thing I've heard this interviewer asking, what is the difference between ordinal and nominal data? Now let's go ahead and let's discuss about ordinal data. In order to understand ordinal data, I would like to say some example. Over here in this particular data, the order of the values, the order of the data matters, but value does not. I'll talk about it, why I'm saying value does not. Let's say that I have 5 students and here the marks of the students are like 100, 96, 57, 85 and 44. Now tell me over here, if I just try to find out the rank basically means who is having the highest marks will get the first rank, 96 will then get second, this 85 will get third, and this we will get as fourth, and this finally will get as fifth. This data that we specifically have is my ordinal data. Here we focus more on the order, not on the values. Here we mostly focus on this ranks. We are not worried like what marks that particular person has got. Yes, he has got the first rank. So this was with respect to the ordinal data. Now let me come towards the, so over here you can basically say that ordinal data will be present, and we also use a different technique to analyze those data, and probably when we'll be seeing some data set in the future, we will probably try to see that, okay, scenarios also. Now interval data, here the order matters, here the value also matters, and one thing is that here natural zero is not present. What is this natural zero? Here order also matters, values also matter. So if I take an example of interval, let's say that I have an interval of temperatures, and let's consider Fahrenheit temperature I'm just talking about. I may have values like this, 70 to 80 Fahrenheit, 80 to 90 Fahrenheit, or I may have 70 to 80 Fahrenheit, 80 to 90 Fahrenheit. Here interval is there, definitely some kind of values are there, 90 to 100 Fahrenheit. But if I say 0 Fahrenheit, it won't basically make a useful meaning in this. So definitely this is basically called as an interval. You have some range of values between them, and the order also basically matters a lot. I may also have distance, 10 to 20, 20 to 30, 30 to 40, where probably this interval data may be used. In Ola, I think you have probably booked cabs. You book the cab for, let's say you're booking the cab for 6 hours. There they'll be saying that you can actually go till 0 to 60. And then you can probably, if you are more than 60, that time you have to pay more money. Natural zero. Zero will not be present, right? 0 Fahrenheit will not make any difference. Now ratio data will be an assignment for you. Let me go ahead and let me take another topic which is called as frequency distribution. Now this is pretty much important because in the later stages you'll be understanding about histogram and all. Let's say that I have a sample data set, and suppose in this particular data set I have three types of flowers: rose, lily and sunflower. Now similarly in this particular data set I have a lot of flowers like rose, lily, sunflower, then again I have rose, then again I have lily, then again I have lily. Okay, so suppose let's consider that this is my entire data set. Now usually for showcasing this data set in some kind of visualized manner, we can basically use this frequency distribution table based on the flower type and how much is the frequency. Okay, and this will be very much important. Suppose if I say rose, in rose how many types I have? 1, 2, 3. So 3 is the count of rose. If I consider lily, so lily, what is the basic count? I am basically having 1, 2, 3, 4. So 4 is the count. If I consider sunflower, what is the count? 1 and 2. So this is the frequency of this particular values of this particular data set with respect to different categories. Okay. So here you can see that this is entirely frequency distribution table, and from this table you can derive bar charts, you can derive pie charts, you can derive different things. Now one more topic. Now this, you know that it is a frequency distribution, but there is something called as cumulative frequency. Cumulative frequency basically says that initially I have rose 3 flowers, then I am going to add this to this, so it will be 7. Then I am going to add this to this, it will be 9. At the end of the day, when we go with respect to cumulative frequency and when we go till the last category, we will be able to find out how many total number of flowers are present. This is basically the cumulative frequency. The frequency is getting added and finally you'll be able to see the cumulative frequency over here. Now what we can basically derive from this, I'll just show you an example. There is something called as bar graphs and pie charts. So that particular part now we'll try to draw from this, and we'll try to see that how does it look like. In the case of discrete variables, we can definitely draw a bar chart. If the variable is continuous, at that point of time we can draw a histogram. So let me just talk about bar graph. So first one is the bar graph. In bar graph, in the x-axis, I will probably have all my flowers. So this is rose, this is lily, and this is sunflower. In the y-axis, I will probably have frequency. So this will be my value 1, 2, 3. Obviously, I know how many roses are there. Roses are 3. So I'm just going to create this graph over here, which will be looking like this. So this is my bar chart for rose. Lilies are obviously 4. So I'm going to basically, lilies I may use blue color, and this will be my 4 value. And finally, you'll be able to see sunflower. This will be sunflower. Let's say sunflower is only 2. So I'm going to create this. This specific diagram is basically called as bar chart. From this, why do we use it? As I say, summarizing the data. This is still the part of descriptive statistics. Descriptive statistics. So this is how you basically define it. Here you can see that the values is discrete variables. Now what if I consider the next example, which is called as histograms. Now in the case of histogram, how do we define? First of all, your data should be continuous. It can be discrete continuous, it cannot be discrete continuous. Let's take one example of age. Suppose I have a data set of ages and I have values like 10, 12, 14, 18, 24, 26, 30, 35, 36, 37, 40, 41, 42, 43, and 50, 51. Okay, so suppose if I have this specific ages. Okay, now here you know that it is a continuous value. Now in the case of continuous value, if you want to represent it through some diagrams for the data analysis purpose, you can basically use something called as histograms. You can basically use histogram. So the histogram will have like this. Now understand one very important thing. In histogram, we make something called as bins. Bins basically means we make some kind of grouping. By default, the bin size is usually 10. Now, if I really want to make this bins, what I'll do in the y-axis, I will be having the frequency. Obviously, you will know this. Now, let's make the bin. I told you 10 will be the bin size. 30, 40, 50, 60, 70, 80, 90. You can change the bin value also. Between 0 to 10, Between 0 to 10, I don't have any value, so I'm not going to create it. So let's see that 1 is there, 2 is there, 3 is there, 4 is there, and 5 is there. Okay, so this is my frequency count. Now, between 10 to 20, I have how many values? 1, 2, 3, 4. So 4 values, I'm going to create a diagram over here. Between 10 to 20, I have 4 different values. I have 4 different values. And then 20 to 30, I have 3 different values. 1, 2, 3. Let's consider I'm going to draw my next diagram. Then I have between 30 to 36, I have 1, 2, 3. Again, I have 3. Between 30 to, no, sorry, I have 4. Because I'm also going to count 1, 2, 3, 4. Okay. So I'm going to draw my another building over here. And this building is basically called as histograms. Okay. And then between 40 to 50, I have 1, 2, 3, 4. Okay. So again, I have 4 over here. And finally, between 50 to 60, I have 1. This buildings that you see is basically called as histograms. This building that you basically see is called as histograms. And this in this histograms, your values will be continuous. Now, one amazing thing, because people ask about what is PDF. I say that PDF is smoothing of histogram. So I'll just tell you one example. If I smoothen this histogram, my PDF function will look something like this. Now you may be considering, Krish, how is this basically getting created? Okay, how is this basically getting created? I'll say that there is something called as kernel density estimator. Now this kernel density estimator, how it is done, we will try to understand that in the upcoming classes. Probably that is little bit in the advanced side, but I hope everybody got an idea about histograms. Everybody got an idea about bar graph. Definitely only for, okay, tell me what is the difference between bar versus histogram? Bar versus histogram. Why do we use bar graph and why do we use histogram? Bar is specifically used for discrete. This is used for continuous. Now, if somebody asks you what exactly is probability density function, you're just smoothing the histograms. Hello guys. So yesterday, if you remember, we have discussed all the basic things. Today, we will be moving from basics to intermediate. Stats specifically for data science. So this is what we are going to discuss, and there are so many topics that I am probably going to cover. Today we are basically going to cover measure of central tendency, measure of central tendency, measure of dispersions, Gaussian distribution. Then fourth, we are going to understand Z-score. Then we are going to understand standard normal distribution, and there are some more topics that we really need to cover. So the first topic that probably we are going to discuss is something called as arithmetic mean for population and sample. Mean basically means over here specifically we are talking about average. Now with population and with sample, we really need to understand the formulas of mean, and we will try to understand in this specific way. Population is basically given by capital N, sample is given by small n. Now coming to the first thing, whenever we are probably discussing about mean, you need to remember that we are trying to find out the average of a specific distribution. So let's say that my data set looks something like this: 3, 3, 4, 5, 5, 6. So if I really want to find out the mean of this population, I can basically give by a symbol which is mu, and I'll say summation of I is equal to 1 to capital N x of I divided by n. Now, what is this x of I? Let's consider that this is my random variable x, and probably I have so many different values inside my data set: 1, 1, 2, 2, 3, 3, 4, 5, 5, 6. So if I really want to expand this thing, x of I, basically we are going to iterate through all these n elements. So I may write 1 plus 1 plus 1 plus 2 plus 2 plus 3 plus 3 plus 4 plus 5 plus 5 plus 6 divided by capital N. Over here, capital N is what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 elements. So it is 32 by 10, which is nothing but 3.2. So 3.2 is basically my average. Now with respect to population, always remember how the symbol is basically given. We can write x bar which is specified by sample mean. Here I'm going to write summation of I is equal to 1 to small n, and here I can basically write x of I divided by n. Obviously we'll get the same answer because we are going to take the same data set. So this was the example with respect to arithmetic mean. Always understand that notation. The notation is quite important over here. The reason why I'm saying you notations over here in this way, because because in the real world industry, when you are working, when you're explaining someone as a data scientist, you really need to use this well-known notation. You can use your own notation, whatever you like, but think of a larger point of view. Here you really need to make sure that whatever standards is being followed, we need to try to follow in that specific way. So this was the basic things with respect to mean. Mean is the part of central measure of tendency. Apart from mean, there are two more things. So let me just define what is central tendency, which we basically say central measure of tendency. There are three main things. One is mean, second one is median, and third one is mode. Now if I really want to make you understand, because it is a very important interview question, if someone says you that what is central tendency, or so what is measure of central tendency, you can just say that it refers to the measure used to determine the center of the distribution of the data. So that basically means whenever I have a data, if I really want to find out the center part of that particular distribution, I can use mean, median, mode. Why specifically we'll be using it, that all I'll be talking about, but I hope everybody got the definition till here. Everybody clear with this definition? It refers to the measure used to determine the center of the distribution of the data. So average and mean are one and the same, guys. Understand average, mean. Okay, we use the same formula that is basically used. Okay, so this was the part with respect to central tendency. Now let's go ahead and let's try to solve some problems. Right, obviously I have given you a lot of examples with respect to mean, but now let's go ahead and try to understand median. And why do we specifically use median? So I'm going to take the same data set, whatever data set I have used over here, that is 1 1 2 2 3 3 4 5 5 6. Okay, so 1 comma 1 comma 2 comma 2 comma 3 comma 3 comma 4, and what was the data? Then you had 5 5 6, right? So here I am basically going to take 5 5 6. So suppose if this is my data, obviously the mean we found out was nothing but 3.2. Now what if I tell you that in this distribution you add one more element like 100? So when you add 100, then it will become 32 plus 100 divided by 11. 32 is basically from the sum of all the numbers that we have done taken previously, plus 100, which is a new element that is basically added, and we are just going to divide by 11. So once I do 132 by 11, we are getting 12. Before, when 100 was not added, when this element was not added, at that time my mean was 3.2. But after adding 100 in that specific distribution, my mean became 12. Now here you can see that there is a huge movement of mean. There is a huge difference with respect to this mean. And why it is basically added? Because of this number. We consider this number as outliers. Outliers really have a adverse impact on the entire distribution. So that is the reason why we should be very much careful with outliers. In data science also, in statistics also, we use different techniques to remove the outliers, which also I'll be discussing today when we are going to discuss about percentiles and all. So remember, outliers has a major impact because here you can see that the entire distribution of the central data is basically moving, and the difference is quite huge. For this particular case, what we do, we can definitely use median. Now in median, if I take the same number like 1 1 2 2 3 3 4 5 5 6, and then probably I have 100. Always understand, in median the first thing that you really need to do is sort the numbers. So first step is sort the numbers. So over here you can see that the numbers are already sorted. If your numbers is not sorted, at that point of time you will be able to see that you probably have to sort it. Right now by default I have made sure that the number is already sorted. So do you define distribution in statistical term? Distribution basically means that how your data looks. See, what is distribution? Okay, how do you see how your data is basically distributed? There are various ways. We use PDF, we use histograms, we use different techniques. So I will be coming in making you understand about different distributions. Still, I have not started that. Now, first step is always sorting the numbers. I have sorted the numbers. After sorting the numbers, what I am actually going to do is that I am basically going to take the central element. Now, central element means which one? Suppose if I have odd number of elements. So over here, what is the count? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 is the count. In order to find out the central element, okay, we will probably find out the center one. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this will basically be my central element. This will be my central element because it is the middle element. Now in this particular case, I can definitely say that my mode is nothing but 3. Now understand, even though the outlier is added, see, outlier basically means what? Outlier is a number which is completely different from the entire distribution. Over here you can see that 100 is a completely different from the entire distribution. Now what if, now your question may rise that, okay Krish, what if I have one more number like this? Let's say that I have one more number 112. Now in this particular case, you told to pick up the central element. Now in this case, which will be my central element? Now in this case, my total number of elements are 12. So in order to find out the central element, what I will do, I will take up the middle two elements. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So the middle elements is basically present over here. Now here, I will take this middle element, which is my 3 and 4, and I will do the average of them. So 3 plus 4 divided by 2. So in this particular case, I can say that my mode is 3.5, even though I had two different outliers. But yes, if I keep on increasing the number of outliers, then the distribution will become normal. Now understand one thing, why mode actually works in a better way. Before, because of this outlier, my mean was 12. Even though after adding the outlier, my mean was 12. But now here you can see that even though I added two outliers, my mode, which is again a measure of central tendency, okay, which is again a measure of central tendency, there is hardly any difference, a very less difference. So that is the reason why we use median. Did I say mode? Oh, sorry. It is median. By mistake, I wrote mode. It should not be, okay, median, okay. So median, I hope everybody understood what exactly is median. We basically take the central elements. If the number of elements is even, then we probably take the central two elements. We try to find out the average and we try to calculate it. But understand one thing over here. What is the main purpose? Initially, when we did not add outlier and we tried to calculate the mean, at that time I got 3.2. When I tried to calculate by adding an outlier, my median was 12. Sorry, my mean was 12. When I tried to do this with respect to median, even though I had added the outlier, it came as 3. And finally, you'll be able to see that when I probably used two outliers and then probably I got the median as 3.5. Now here you can basically see that there is less difference, right? Less difference when compared to this. If I talk about median, it works well with outlier. So this is the proper statement that I want to consider. So in the case of mode, the third topic, now suppose if I have a specific data set like this, 1, 2, 3, 4, 5, 6, 6, 6, 7, 8. Now, even though I have some outliers like 100, 200. Now in this particular case, what should be our mode, which is again taken as a measure of central tendency. Over here in this particular case, in mode, we find out the most frequent element. Most frequent element. Now in the most frequent element, we just try to count and we try to see that which element is having the maximum number of elements. So over here you can see 6 is basically having 3, the count is 3. If you see 2, the count is 2. So in this particular case, my mode should definitely be 6. My mode should be definitely 6, which is again the measure of central tendency. Now see guys, now in this particular case, there is one disadvantage. Even though, suppose let's consider that I have many outliers like this, 100, 100 or one more 100, let's consider. Now in this particular case, since we find out the most frequent element, we try to take this as an outlier. So usually in most of the outliers that we specifically use, we basically use median. Now where specifically mode is used, let's consider one data set. Let's say that I have a data set which is called as gender, salary. Let's consider I have this. In gender, you will probably find out male, female, some different values may be there. Or let me just change this data set and make it in a simpler way. Why specifically we use mode? In mode also we use it in both integer and categorical variables, but it works well with categorical variables. Let's say that this is a type of flower, and this is petal length and petal width. Now over here you'll be able to see different flowers like rose, lily, sunflower, and you have some flowers. Let's consider that you have some missing data over here, and based on this missing data, now this particular data set has come to me. And let's say consider that I've seen in this particular data there are around 10% missing data. Now what do you think, in order to handle this missing values, what type of things we can definitely use from mean median mode? Don't you think I can definitely use mode over here? Because the most frequent occurring flower can be replaced with this missing value. So what I'm saying, the missing value will be replaced with most frequent occurring element. So we can definitely say that most frequent element, you can actually get it by using mode, which is most frequently used, and this specifically works well with categorical variable. Now let's take another example. Suppose I have a feature age. I have values like 25, 26, dash, 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 32, 34, 38. Now in this particular case, what do you think, what may be a suitable thing? Suppose let's say that these are my ages of students. Should I apply mean, median, or mode? Which do you think, based on this scenario, that is ages of students, we should definitely apply? Just tell me this answer. In this particular case, definitely I would suggest let's go with mean, because I know students' age will basically range from one value to one value. It won't extend more than that specific value. So here a domain knowledge will also come into existence. If I say that this is probably the ages of all the population throughout the world, probably I'll not go with mean. So something like that, So this is a very good example, very good understanding with respect to various use cases that we can actually think. Now let's go and discuss about the next major topic, which is called as measure of dispersion. Now in measure of dispersion, what all things we specifically discuss? We discuss about two main topics. One is variance and the second one is something called as standard deviation. So these are the two topics that we are probably going to discuss. So let's go ahead and let's discuss about this. Now first topic is basically with respect to variance. Now how do we define variance? Variance is a concept of measure of dispersion. And probably for an interviewer also, this may be a confusing question they may ask candidates, and they may probably make them understand different things, and they may again confuse you. But when I say dispersion basically means spread. Please make sure that you remember this word. This basically means spread. Okay, spread. How well spread your data is. With the mean, obviously, see, let's say that I have two data sets. I have data set like 1, 1, 2, 2, 4. What is the mean? 10 divided by 5 is 2. Now let's consider that I have another distribution which looks like this. 2, 2, 2, 2, 2. This is my next distribution. If I try to find out the average, then also it is 2. So for both this distribution, we are getting the same average or mean. I'm getting the same mean, right? So if I'm getting the same mean, then how do I identify that these two distributions are different? Because we need to think about it, right? How do we basically come up like with this is that how this two distribution is different? We really need to understand. Okay, and probably interviewer may say you and he may confuse you in dispersion. What is variance? He may definitely confuse you. So for that specific reason, if you really want to identify how two distribution are different, at that point of time we may use variance and standard deviation. Now let's go ahead and let's try to understand the formula with respect to variance and standard deviation. And here also I will probably talk about two different things. And here one very important interview question will come. One is population variance and one is about sample variance. So these two things, why I am teaching you with respect to population sample, it will all make sense. So usually population variance is given by something called as sigma square. Here you basically use as summation of I is equal to 1 to capital N x of I minus mu whole square divided by n. Sample variance is basically given by small s square summation of I is equal to 1 to small n x of I minus x bar. X bar basically means sample mean divided by n minus 1. Now many people will say, so why n minus 1, n minus 1? Yes, this is an interview question. I will talk about it. Okay, I will talk about it. Don't worry. So let's take one very good example probably, and we'll try to solve this specific problem. Let's consider that I have my x value as 1, 2, 2, 3, 4, 5. So this is my distribution. So probably over here, this is basically my data set. So first thing first, let's go and calculate. Now we'll go and calculate. So with respect to population, we'll go and calculate the mu 2.83. So here mu is basically 2.83, 2.83, 2.83, 2.83, 2.83. The next thing is that from this equation, I will try to calculate x minus mu. So what is x minus mu over here? Just do the calculation, and it is good that you do the calculation. So here I get minus 1.83, here I get minus 0.83. This will basically become 0.17. This is plus. And over here you will be able to see that this will become 1.17. And then for the 5, you have this and it will become 2.17. Now the next step, you basically do the squaring. Now if you do the squaring, that is x minus mu whole square. You just have to do the square of this 3.34. So here you can see 0.6889. Then here also I can see 0.6889. And then for the remaining one, you can do the calculation. So here it will be 0.03, 1.37, and finally you will be able to see 4.71. Then what we do? We do the addition of this, because summation of this is there, right? So once we do the addition, probably then we probably calculate it. If I do the addition, this is nothing but 10.84. 10.84 divided by 1, 2, 3, 4, 5, 6. 1.81. Now understand one thing. Let's say if I have a data set which looks something like this, and if I have a data set which looks something like this. Comparing these two data, where do you think the variance is more? Variance, understand variance. Variance, whenever your things comes into mind, it should be talking about spread. So over here in the second picture, definitely variance will be higher. Let's consider that. I'm just going to take this example. Here my variance is 1.81. Let's consider that this is 1.81. And tomorrow, if I probably get 5.45, can I say that it may belong to this particular distribution? Yes. So the variance will be definitely higher because the spread is quite high. Spread, when we say spread is basically high, that basically means the elements that is present in the central region is more. Whenever I talk about more variance, that basically means the data is more dispersed. Let me talk about this also to you so that you can understand. Okay. Now let's forget about standard deviation for right now. Now in this particular image, let's see. In this particular image, what do you see over here? You can see over here standard deviation is 10, standard deviation is 50. Now if you see standard deviation formula, it is nothing but root of variance. Now here you can see when the standard deviation is smaller, that basically means you're having a very huge curve. That basically means the data is not that much distributed. When you have a big standard deviation like 50, 60 and all, you can see your data is highly distributed. So this is very much important to understand. Why variance is more for dispersed data? Because over here you can see, right guys? Okay, when you probably calculate, I'll show you some of the problem statements over here, but just understand this graphically, okay? Later on, I'll just show you one example where probably I will talk about it, and let's try to solve that particular example, and then we can definitely understand it. But some idea you basically got, because obviously the variance needs to be spreaded high if the variance is high, right? The dispersion becomes high because you have more number of values inside it. Now let's go ahead and let's try to see. Now I got my variance as 1.81. Now my standard deviation is nothing but root of variance. Root of variance. That basically means it is nothing but root of 1.81. So if I go and open my calculator, I'll just say root of 1.81, and there I'm actually getting is nothing but 1.345. So 1.345. Now see, what does standard deviation basically mean? What is the mean in this particular case? What is the mean? Mean is nothing but 2.83, right? Let's consider this one. The mean is 2.83. Now, from this mean, your data will be distributed because mean is basically specifying your measure of central tendency. It basically says that where the center is there for that specific distribution. So, from here, if I go one step right, one standard deviation to the right, you have seen standard deviation formula. The next element that may probably fall between the one standard deviation will range between, let's consider that this is my first standard deviation to the right. Then it will basically have 2.83 plus 3.4. So this is nothing but 4.17. That basically means in this distribution, whatever elements are basically present between 2.83 to 4.17 will be falling within the first standard deviation. And if I consider the same thing towards the left, that basically is one standard deviation towards the left, then what I will do, I'll just subtract 1.34. So this will basically be 9,741. So it will basically become 1.49. Now here it basically says that any elements that falls between 1.49 to 2.83 will be falling in this region, that is one standard deviation to the left. Similarly, we'll go with the second standard deviation. Now in this particular case, it will be 4.17, 1.34, 5, 5, 5.51. Similarly, you go and calculate. Similarly, you go and calculate. Similarly, you go and now your standard deviation is a very small number. Still, I'll say that this is a small number. And if I probably try to construct a graph, it will look something like this. The tip, right? This region that you probably will see, this is basically called as a bell curve. And based on the standard deviation and variance, you'll be able to decide two important things. With the help of variance, definitely you'll be able to understand how the data is spread. And with standard deviation, you'll be able to understand that between one standard deviation to the right and the left, what may be the range of data that may be falling in. So standard deviation is nothing but it is the square root of variance. That basically means from the mean, right, how far an element can be. Let's consider that if I consider 5. Now for 5, if you try to calculate, it may fall somewhere here. So how you are going to represent 5? You will say that it falls in 1.5 standard deviation from the mean. So this kind of definition you will be able to tell them. So that basically means from the mean how far a specific number is with respect to standard deviation. You're calculating, you're using a unit called as standard deviation for saying that. And variance specifically talk about spread. If the variance is high, the values, the data spread that is there is very, very high. Now let's understand some amazing basic things which is called as percentile and quartiles. This is the first step to find outliers. How do we find an outlier? So probably we are going to discuss in this the first, and with the help of code also you can basically do. Now with respect to percentiles, let's try to understand what is percentiles and how do you find out percentile. Now before understanding percentile, you basically need to understand about percentage. Suppose if I have a distribution, I say 1, 2, 3, 4, 5. Now my question is that what is the percentage of numbers that are odd? So how do you basically apply a formula over here? So I can basically say percentage is equal to number of numbers that are odd divided by total numbers. So if I really try to calculate how many numbers are odd, 1, 2, 3. So 3 divided by 5 is nothing but how much? 0.6, which is nothing but 60%. Very simple. This is how we basically calculate percentage. Now, and I hope everybody knows this. Now let's understand a very, very important topic which is called as percentile. Now I probably think you have heard about percentiles in a lot of things. Percentile, probably if you have given GATE exam, CAT exam, GMAT exam, SAT exam. Okay, one real life example I'll show it to you that is related to my my YouTube ranking also. If you can see my YouTube ranking Social Blade. So here, if I show you one example, here you can see that you can see education rank. Here, if you hover over here, it shows 96.1527 percentile. If I hover over here, it shows 94.98 percentile. Over here, if I hover, it shows 94.958 percentile. So we'll try to discuss about these percentiles right now. First of all, we will give the definition. What is a percentile? So a percentile is a value below which a certain percentage of observations lie. So this is the definition of percentile. It is basically saying it is a value. If I say, okay, this number is the 25 percentile, this basically says that 25% of the entire distribution is less than that particular value. So percentile is a value below which a certain percentage of observation lie. Let me take a very good example and show it to you. Suppose I have a data set, and inside this data set I have elements like 2, 2, 3, 4, 5, 5, 6, 7, 8, 8, one more 8, 1, 2, 3, 4, 5, 9, 9, 10, 11, 11, 12. So let's consider that this many number of elements that I actually have. Now in this specific number of elements, I want to find out what is the percentile. Let's consider this one. My question is, what is the percentile ranking of 10? So this is my question. We solve this problem by using a simple formula. I want to find out the percentile rank of 10, right? So my formula, let's consider this x is equal to 10. Okay, so here I'm specifically going to write x. So my formula will basically be number of values below x divided by small n, which is my sample, multiplied by 100. So if you try to calculate this number of values below x divided by n, what is n over here? N size is sample size. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 20 is basically my sample size. So here I am going to say number of values below x. So how many number of values? X is 10. How many number of values are below x? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this will basically become 16 divided by 20 multiplied by 100. In short, this will become 4 4s are 16, 4 5s are 1s are 20s are. So 80 percentile will basically be my answer for this. That basically means if I really want to find out what this 10 value percentile is, it is 80. Now understand what is the main meaning out of it. The main meaning is that 80 percentage, please listen to me very, very carefully. 80 percentage of the entire distribution is less than 10. This is the real meaning that you can probably understand from it. Now quickly, what is the percentile ranking of 11, of value 11? So how many elements are present below 11? I'll say 17 divided by 20 multiplied by 100. 1s are 5s are 85%. Let's do the reverse of this. So from this particular distribution, what value exists at percentile ranking of 25%? So how do you calculate this? For this, you use a very simple formula, and the formula is something like this. Value is equal to percentile divided by 100 multiplied by n plus 1. Now see guys, I'm not going to derive the formula, why it is n plus 1, why it is n minus 1, why it is this. For sample variance, I'll discuss about why n minus 1. But understand, we really need to understand what things we are doing and how we are using it in some specific purpose. So percentile over here is 25 by 100 multiplied by 21. Now understand this. This 5.25 is the index position. It is very much important to understand. This is not the value, the index position. Now I will go and find out which is 5.25. So this is my first element, first index, second index, third index, fourth index, fifth index, and 5.25 will be in between this. But right now I don't see any element find between this. So what we do is that we take fifth and sixth index and then we do the average and we calculate the value. In this particular case, my answer will be 5. So 5 is the value for 25 percentile. Try to find out what is 75 percentile. So if I use 75 divided by 100 multiplied by 21, 15.75 is the index position. Now go and count which is 15.75 from the top. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15.75 is the sum of these two numbers. So my answer is 9. 15.75 is the index position. So here I'm basically getting the 9 answer. Now let's go and discuss about a new topic which is called as 5 number summary. In 5 number summary, we need to discuss about something called as, first one is something called as minimum. The second topic that we should discuss about is something called as first quartile, which is also denoted by Q1. The third topic that we must discuss about is something called as median. The fourth topic that we should discuss about third quartile, which is also read as Q3. And the fifth topic we basically discuss about maximum. And with the help of this, we will be using these values to basically remove the outliers. So let's take one example and let's see that by the help of 5 number summary, how do we remove an outlier? So removing an outlier, a very important thing which is also called as IQR. So here we are going to discuss about removing the outliers. Now removing the outliers, let's consider that I have one data set which is like this: 1, 2, 2, 3, 3, 4, 5, 5, 5, 6, 6, 6, 6, 7, 8, 8, 9, 27. Now from this distribution, guys, what do you think which is the outlier? So obviously you'll be saying that 27 is the outlier. Always understand, guys, whenever we need to remove an outlier, we really need to define a lower fence. Let's consider that I'm going to define a lower fence and then I'm going to define a higher fence. The values that you have over here will be between lower fence to higher fence. That basically means after a greater number, all the numbers above that number will be an outlier. After a smaller number, all the number below that particular number, below this lower fence, will be actually treated as an outlier. It should also have higher, it should also have lower. If I consider that I had one element which is called as minus 50, is minus 50 an outlier for this distribution? Yes, the answer is definitely yes, right? If you have minus 50 over here, that is probably in the lower fence side, below the lower fence side, and it can be treated as an outlier. So in order to define the lower fence, we write a very simple formula. And the formula looks something like this. So here you can define lower fence is equal to Q1 minus 1.5 multiplied by IQR. I'll talk about what is IQR. And upper fence is basically defined as Q3 plus 1.5 multiplied by IQR. These two things are basically there. Now, what exactly is IQR? You really need to understand about IQR. What exactly is IQR? IQR is nothing but it is called as interquartile range. Interquartile range is basically IQR and it is given by the formula Q3 minus Q1. Q3 is nothing but 75 percentile and Q1 is nothing but 25 percentile. Now quickly check this distribution and try to find out the 25 percentile. So what exactly is 25 percentile? What exactly is 75 percentile? Simple formula: 25 multiplied by 100 multiplied by small n. Small n is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, 19. 19 plus 1, right? So this is nothing but 25 by 100 multiplied by 20, which is nothing but 5. This 5 is nothing but index position. So what is the fifth element index position? 1, 2, 3, 4, 5. Is everybody getting 25 percentile is nothing but 3? Is everybody getting 25 percentile or Q1 is equal to 3? Similarly, if you try to find out Q3, you will be able to get that it is 7. Q3 is 7. You will get the 15th index for Q3. So you are basically going to get 7. Now if I go and compute the interquartile range, what is interquartile range? 7 minus 3, which is nothing but 4. Now you have calculated the IQR. So what all things we have calculated? The IQR, Q3, Q1, everything is being computed. Now let's go ahead and compute the lower fence. Now the lower fence basically say Q1 minus 1.5 multiplied by IQR, right? This is what lower fence formula is. So what is Q1? Q1 basically is nothing but, what is Q1 in this particular case? I have computed it, it is 3. You can see over here, Q1 is 3, Q3 is 7. So I'm going to write 3 minus 1.5. What is IQR? 4. So 3 minus 6, which is nothing but minus 3. So the lower fence value is minus 3. Now let's go and compute about the higher fence. Higher fence basically say Q3 plus 1.5 multiplied by IQR. Q3 is 7. 7 plus 6 is equal to 13. So my lower fence to higher fence range is between minus 3 to plus 13. Now tell me which is the outlier from here. Minus 3 to plus 13. Anything that is greater than 13 is considered as an outlier. Anything lesser than minus 3 is considered as an outlier. So which number should we remove? We should remove 27. Why? 27 is greater than 13, which is from the higher fence. Now let me write the distributions once again for all of you. Let me write the distribution after removing the 13. So the remaining data, what I have, 1, 2, 2, 3, 3, 4, 5, 5, 5, 6, 6, 6, 6, 7, 8, 8, 9, 27. But I told you we are removing 27, right? So 27 is removed because it is an outlier. Now you know what is the minimum value out of all these numbers? Minimum value is 1. What is Q1? My first quartile we have computed over here. Q1 is nothing but 3. Median you calculate and tell me quickly. Then you have Q3. Q3 is 7. And the maximum number after removing the outlier is nothing but 9. So here you are getting your 5 number summary. Now quickly compute median and tell me what is median. Median is nothing but 5. Now let's draw a plot which is called as box plot. By this specific data, you can definitely draw a box plot. Now how does a box plot basically get drawn? So you will be having x-axis, and let's consider that in this particular x-axis you have values like minus 2, 0, 2, 4, 6, 8, 10. So this is your x-axis. Now just to go and find out where is minimum element. Minimum element will probably fall over here. That is in 1. Q1 will basically fall at 3. So this will be your 3. Median is basically 5. So this is basically your 5. Q3 is nothing but 7. So this is your 7. And max is nothing but 9. So this is your 9. Now all you have to do is that join these lines. So this exactly is your box plot. If I had kept 27 as an element, I would had to extend this line this much big and probably put 27 somewhere here, and this used to be one dot over here. Have you seen this kind of plot? This value is nothing but minimum. This is my Q1, this is my median, this is my Q3, and this is my max. And this technique of removing an outlier, we basically say with respect to lower fence and higher fence. And we also use something called as IQR. The first application that I shown you here, this is also used extensively in data visualization. So you really need to know all these things. I've drawn it in front of you. I can also do this with code. I have to just install a library. In Matplotlib, you have a library where you can probably do all these things. Now let's come back to understand about variance. Summation of I is equal to 1 to n x of I minus x bar whole square divided by n minus 1. This n minus 1, why we do it, it is also called as Basel correction. We also say it as degree of freedom. And I have probably made this video in my stats playlist, why sample variance is divided by n minus 1. You can go and search for that. You can definitely understand these things now. Now, tell me, one interview question may come that what is the application of box plot? Box plots can be used to determine outliers, because as I told you that if I was giving 27 over here, my element would have come over here. So box plot actually gives you a visualization way to basically see where an outlier is actually present. If someone asks you, how do you create or how do you determine an outlier, you can explain this entire concepts, whatever I have explained with respect to percentiles. Hello guys, regarding the agenda, first of all, I'm going to talk about, we're going to discuss about a lot of distributions. Now in this distribution, you will specifically have something called as normal distribution or Gaussian distribution. Then we will try to discuss about standard normal distribution. Then probably one more example on Z scores. We'll try to see Z scores both with uh, Z table. There is a concept called as Z table and why Z scores are actually used. Then we will discuss about log normal distribution. Then probably we will also discuss about Bernoulli distribution. Then finally we'll discuss about binomial distribution, and we'll see some examples. We'll solve some examples. And then whatever practical part is left that we have not covered till now, like mean, median, mode, everything will get covered over here. So if you want to do mean, median, mode, we'll try to do with Python programming language. Okay, and we'll also do variance, standard deviation. The third thing, we'll try to create histograms. We'll try to create PDFs, probability density functions. We'll try to understand how does a distribution, this normal distribution, will look in code. We'll try to find out how to find out this IQR using code, and we'll see all these things. And some examples of log normal distribution we are going to see. Okay, I can also discuss about bar plot, not to worry. That also we'll try to discuss about it. Okay, I can also discuss about violent plot. So whatever things will come, we'll discuss about. Now, first thing first, today we are going to discuss about distributions. Now, what exactly is distributions? Understand distribution of data. When I say I have a data set, let's say that I have a data set of ages like 24, 26, 27, 28, 30, 32, So we have a lot of data set. Now, when we have this particular data set, always in the first thing that we need to focus on is that how do we basically see this data set in a visualized way, because obviously this is a continuous data. We already know that this is a discrete continuous data. In this particular case, age, I'm just going to consider as discrete continuous data. Now in the case of continuous data, what kind of graphs do you see? Probably you'll be able to understand about that specific data. So if I really want to get one analysis, or if I really want to start my analysis, I really need to see a lot of visualized diagrams. And that is where, when I consider this entire distribution, there are multiple ways to visualize this data through various graphs. And these graphs can really play a very important role whenever probably we are discussing about, whenever probably we are creating reports, where we are doing exploratory data analysis and many things. So let's go towards distribution. Suppose I have a specific distribution of data. I probably want to plot this data through some way. Let's consider that I want to probably plot this data through some way. And the best and the easy way that you can probably think about is your histogram, right? So we have already seen how to create histograms. You will be able to create diagrams like this, buildings like this, right? So you will be able to get buildings like this. And finally, what you do, you smoothen this histogram to get some kind of curve. And this curve right now looks like a bell curve. Okay, so considering this, let's go to the first distribution. The first distribution that I'd like to focus on is something called as Gaussian or normal distribution. Now, why, as I said, why distribution is basically used? Distribution main purpose is to why this different kind of distributions are there, so that we can basically have some idea about a data set. Now, first of all, when we discuss about Gaussian or normal distribution, most of the time you have seen this kind of distribution in this specific way. So here probably you have seen a bell curve. Now this bell curve, this is my bell curve. Now they are very important information when I probably talk about this bell curve. This will basically, this can be your center line that you see, can be your mean, it can be your median, it can be your mode. So what does this basically mean? If I have a distribution and probably this distribution follows this kind of bell curve, and one important property of this bell curve is that this side is exactly symmetrical to this side. So there are many inferential statistics that we will probably be discussing about in the future. About this bell curve, about this entire distribution or Gaussian distribution, here you can see that it is exactly similar. It is exactly symmetrical. The right part of the curve, when I say consider this particular path, is equal to this part. That basically means that the amount of data that is present in this particular part will also be equal to the amount of data that will be basically present in this part. So here you can basically see that exactly this forms a bell curve, and whenever we have a specific distribution which exactly follows this kind of bell curve, we can definitely say this as a normal or Gaussian distribution. So this is basically my normal distribution. Now, why we are specifically focused on this distribution? This distribution is very much important because from this we can derive a lot of conclusions. What all different kind of conclusions we can derive, that I'll just talk about it. Now, let's go ahead and let's discuss about this distribution. Always understand, whenever, let's draw this distribution once again. Now, suppose this is my distribution. So this will be a mean, median, mode. Then you can go one step towards right, second step towards right, third step towards right. So what is this exactly called? Standard deviation. One step towards the right, one standard deviation towards the right, two standard deviation towards the right, three standard deviation towards the right. Similarly, I may have one standard deviation to the left, second standard deviation to the left, and finally I can also have one more standard deviation to the left. This will be very, very much important, guys. Now, what kind of different conclusions or what kind of things we can actually conclude from this kind of graph? This side is symmetrical to this side. Now, let's go ahead and discuss about some of the important things in this. Suppose if I draw this line, can I say this is my first standard deviation towards the right and second standard deviation towards the left? So this is my region of my first standard deviation. The center one over here, I can basically write it as mu. This will basically become mu plus sigma, mu plus 2 sigma, and this will be, just a second, mu plus 3 sigma. Similarly, here I can write mu minus sigma, mu minus 2 sigma, mu minus 3 sigma. Because of less space, I'm just trying to include it in this particular way. Now, the first thing that we will probably come up with is called as empirical formula. Now, this is very much important, empirical formula. Now, this empirical formula basically says that you really need to understand this 68, 95, 99.7% rule. Now, what does this basically mean? This basically indicates that, let's go with 68. Within the first standard deviation, around, suppose if I have some distribution data, let's consider that I have a data set which have 100 data points. Now, what does this basically indicate is that between the first standard deviation, between this region, in this entire region, around 68% of the distribution is present. That basically means out of this 100 data point, 68 data points will be present in this region. That is the reason it is basically called as a bell curve. That specific region, in that central area, you have a lot of data. So 68% of the entire data set lies in this region within the first standard deviation. Now coming to the second standard deviation. This is something very, very important. I'll also talk about what you can derive from all these things. Between the second standard deviation, around, let's come to the 68%, this is clear. Then within the second two standard deviation, right? Within the two standard deviation region, which is this specific region, around 95% of the entire data lies in this region. And similarly, if I go and consider with respect to the third standard deviation, which is from here to here, around 99.7% of the entire distribution will fall in this region. So that is the reason why it is basically called as 68, 95 and 99.7 percentile loop. So everybody is clear. That basically means is now if you have a distribution which is Gaussian or normally distributed, then this conclusion can definitely made that within the first standard deviation how much data is basically falling, within the second standard deviation how much data is falling, and within the third standard deviation how much data is basically falling. Now let's see some examples. Some of the examples, if I talk about, like height is basically normally distributed. Who is saying this? I am not saying it. The domain expert is basically saying it. Now who is the domain expert in this particular case? In this particular case, the domain expert is a doctor. Doctor have taken various samples from different places, and whenever the doctor was constructing this bell curve, it was forming something like this. And from that he was able to understand, he was able to derive, right? He or she was able to derive that within the first standard deviation how much data is basically falling, within the second standard deviation how much data is falling, and within the third standard deviation how much data is falling. Second example, if you consider weight will also follow a Gaussian distribution. Third, I hope everybody knows about iris data set. In iris data set, if you talk about petal length, sepal length, it actually follows Gaussian distribution. I will show you practically, don't worry about that. Does that following the empirical rule necessarily imply that it is distributed? See, whenever you have a Gaussian distributed data, at that time it will follow this 68, 95, 99.7 percentile rule. So this was the thing with respect to Gaussian or normally distributed. Now let's go ahead and try to see this. Let's take an example. Suppose I have a data set where my mean is 4 and my standard deviation is 1. If I have this two information, can I construct a distribution? Suppose this is 4. Then in the next step, what it will come? 5, 6, 7, 8, right? And then 3, 2, 1 and 0. So I will be able to create this. And let's consider that this is basically following this kind of distribution. So this basically follows this kind of distribution. Now understand, this middle one is basically your mean and standard deviation. Sorry, mean is 4 and standard deviation is 1. Now see one thing, guys. If I talk about 4.5, my question is that where does 4.5 fall in terms of standard deviation? So you may be thinking, okay, 4.5, where exactly it is? It is somewhere here. Obviously, when I say 5 is first standard deviation to the right, that basically means 4 will be plus 0.5 standard deviation to the right. Understand, 0.5 standard deviation. If you say 1 standard deviation, it is basically coming to 5. It is 0.5 standard deviation. Now, similarly, if I say, where does 4.75 fall? Then how you will be able to see it? See, the standard deviation was 1. I told 4.5. So 4.5 will be something falling over here, and this is like 0.5 standard deviation. But in the case of 4.75, it will be very much difficult for you to do the calculation. So that is the reason what we can do is that we can use a concept which is called as Z-score. Now Z-score will basically help you find out, whenever I talk about a value, how much standard deviation away it is from the mean. So this formula is x of I minus mu divided by standard deviation. Now I need to find out for 4.75. I will just write 4.75 minus mu is what? Mu is 4. 4 divided by standard deviation is 1. So here I am actually getting 0.75. So now I can see that it is 0.75 standard deviation to the right. Why it is saying right? Because this is positive value. Now if I give you the same question, try to find out where does 3.75 fall? Like how many standard deviation, what should be the standard deviation with respect to 3.75? Then you go and apply the same formula. So here I'll say Z score is equal to 3.75 minus 4 divided by 1, which is nothing but minus 0.25. So whenever minus comes, that basically means you have to check in this side. And it is basically saying that 3.75 will be falling somewhere here. That is nothing but minus 2.25 standard deviation to the left. Now let's go to the next thing. Suppose I consider this same graph. Now you understood, if I really want to find out how many standard deviation to the right or the left I need to find out, I can definitely use z-score. Let's consider this thing. I will use the same graph. I'm using the same bell curve. This is my 4, this is my 5, this is my 6, this is my 3, this is my 2, this is my 1. Here you know that my mean is 4 and standard deviation is 1. Understand one thing over here. I'll talk about z-score again. Don't worry. Now let's apply z-score to every values. What will happen? If I apply z-score to every values, what will happen? Okay, what is z-score formula? X of I minus mu divided by standard deviation. Okay, you know the mean. Mean is nothing but 4, standard deviation is 1. Now, if I apply z-score to everything, initially my distribution was like this: 1, 2, 3, 4, 5, 6, 7. Now, this was my distribution initially. Now, after applying z-score to this, what will be my distribution? That will be coming. Apply for 1 first of all. So, if I apply z-score to 1, then what will happen? 1 minus 4 divided by 1. This is minus 3. Can I say this 1 is getting converted to minus 3? 1 is converted to minus 3. Then if I apply this z to the next element 2, then what is 2 minus 4 my 1? It is nothing but minus 2. So here I am actually getting minus 2. Then if I go and apply the z-score to 3, then what will happen? Z of 3. So 3 minus 4 divided by 1, what will happen? Minus 1. So minus 3 will now get converted to minus 1. Then 4 will get converted to 0. Then it will get converted to 1, 2, 3. Now understand the main magic in this. With the help of z-score, is this not the standard deviation of the same elements that we got over here? Is this not the standard deviation of these all elements that we got after applying the z-score? After we applied this, initially my data set was like this, then I got this. This element falls at minus 3 standard deviation. This elements fall at minus 2 standard deviation. So here you can definitely see that I'm able to get the standard deviation. Now what is happening? See over here, one beautiful thing that is basically happening. I had a distribution which was 1, 2, 3, 4, 5, 6, 7. After I applied a z-score, this got converted to minus 3, minus 2, minus 1, 0, 1, 2, 3. And probably, right? I got this. Now, what is this distribution then called? This was initially a normal distribution or a Gaussian distribution. After I applied a z-score, what kind of distribution we are actually getting? And what is this basic distribution called as? So this distribution is called as standard normal distribution. So one of the most important property with respect to standard normal distribution is that your mean is 0 and standard deviation is 1. Is this satisfying this property or not? It is being satisfied, right? So can I write a random variable x or y will belong to standard normal distribution, where specifically your mean will be 0 and standard deviation will be 1. So after applying a z-score, we are able to get into a different distribution which is called a standard normal distribution. Now the question rises, why do we do this? What is the use of doing this? Let's go ahead with one practical application. And we do this in machine learning. We do this in most of the algorithms. Now let's go ahead and try to see the practical application. Suppose I have a data set. Let's consider that I am solving a machine learning problem statement. I have a data set, age, I have features like salary, I have features like weight. Suppose in this particular data set, I have these 3 columns. Now, understand one thing. Age, by what unit we will calculate? By years. Salary, we may calculate by rupees or dollar. Weight, we may calculate in kgs. Understand, these units, these are what? These are basically units of calculation. Now, whenever I have some values like this, like 24, 25, 26, 27, salary may be 40k, 50k, 60k, 70k, something. Weight may be 70 kgs, 80 kgs, 55 kgs, 45 kgs. Now here, when you have this kind of data, always understand. Now in this data, obviously you can see the units are completely different. Our main target should be that we should try to bring up in a form, probably in this particular form where my mean is 0 and standard deviation equal to 1. At that point of time, I can definitely apply standard normal distribution. That basically means I can take up this entire data and apply z-score and convert this into standard normal distribution. Similarly, I can go ahead and take up this particular data set, I can apply z-score and I can basically convert this into standard normal distribution. This process is basically called as standardization. Very super important. Many people will talk about normalization. I'll talk about the difference between standardization and normalization. Whenever we talk about standardization, in short, internally there is a z-score formula getting applied. So standardization is a process where I am basically trying to convert a distribution into standard normal distribution. The property is that the mean is 0 and the standard deviation is 1. Now let's go ahead towards something called as normalization. Now what exactly is normalization? In standardization, whenever we talk about, here we are getting converted as mean is equal to 0 and standard deviation equal to 1. Now in normalization, you have an option. You will say that I want to shift this entire values or whatever values that I have between 0 to 1. Let's consider it like this. I want to change all these particular values between 0 to 1. So in this particular case, I may definitely apply normalization. Now, how do we do normalization? There is a very important formula which is called as min-max scalar. In the min-max scalar, you just have to provide 0 to 1 and automatically this kind of normalization will happen. And yes, I will show you practically also, don't worry. If I want to probably shift this between -1 to +1, I can basically apply this. So normalization gives you a process where you can basically define the lower bound and upper bound and you can convert your data between them. Now, very important thing, where do we use normalization? I hope everybody knows about deep learning. In CNN, whenever you are doing image training, image classification or object detection, in this particular case, understand every image has a pixels. Suppose I have a 4x4 image. 1, 2, 3, 4. 1, 2, 3, 4. Each and every pixel ranges between 0 to 255. Now 0 to 255, what we do before we start training, this can be applied with min-max scalar and it gets converted between 0 to 1, where the minimum value 0 is assigned to 0 and the maximum value 255 is converted to 1. So when we do this, automatically we can apply this kind of min-max scalar or normalization. So in this particular case, I will definitely not use min-max scalar because min-max scalar has a different formula. I will take each and every pixel, divide by 255. So when we do this specific division by divide by 255, all your values will be getting changed between 0 to 1. And this is another type of normalization process. So till here we have discussed about min-max scalar, we have discussed about normalization, standardization. Now let's solve one practical example for z-score. Okay, recently India versus South Africa where India lost it obviously. Now let's consider that if I consider ODI series, let's say, and every time in last year also ODI series happened, this year also it happened. The series average of 2021 was somewhere around, let's say, 250. The standard deviation of the score was somewhere around 10. And Rishabh Pant, let's say Rishabh Pant final score was 70. So this was the series information for 2021. Let's consider. Now similarly, I have a data for 2020 series. Let's say the series average in 2020, let's say that the series average is a little bit different. In 2020, the series average of the team scoring in 2020 was 260. The standard deviation of the score of all the matches is 12. And then over here, probably Rishabh Pant final score is 68. Okay, my question is that this two data I have compared to both the series, in which year Rishabh Pant final score was better. So for checking this, obviously many people will say 2020, 2021, lot of confusion will be there. So we will just try to apply for Z score. Now for the 2021, we will apply the Z score. So Z score will be nothing but, it will be x of I minus mu divided by standard deviation. We know what is x of I in this particular case. X of I is nothing but, so 70 minus 250 divided by 10. So what we are getting over here? And similarly for 2020, my Z score will be x of I minus mu divided by standard deviation. So first one, this properly, this values may not be coming. Let me change this data a little bit, okay? Rishabh Pant final, I'll say average score, not final score, so that we change this data a little bit. Otherwise, the data will be very, very bad, okay? Rishabh Pant average score, let's consider that it is 240, okay? And Rishabh Pant average score is somewhere around 245. Let's consider like this, okay? 240 and 245. Because I gave one score, so that is the reason a huge standard deviation is basically coming. At that point of time, I'm just taking average score. Average score of the series, guys. Rishabh Pant, this player's average score of the series. Average score of the series. Okay. Now let me just make some changes and let me put somewhere over here as 240. So 240 minus average score of the series, guys. Three match series. So 240 minus 250 is nothing but minus 10 divided by 10. So this is minus 1 standard deviation. And this data will now change to 245. So 245, this will be minus 15 divided by 12, which is nothing but 15 by 12, which is nothing but minus 1.25. Okay? Clear? Everybody? Okay? आकाश सिंह इफ तीनों मैच में 80 मार दिया तो हो गया ना 240 एवरेज. So understand, along with the not out rule, something 240 is the average. Okay, let's consider in that specific way. I know the data is not approximately right, but I could also, instead of Rishabh Pant average score, I could have team average score. Okay, team average score, and probably team played well, probably in the last match or the first match, like that. Okay, in which series they played well. That also you can basically say. Over here, instead of Rishabh Pant, I could write team average score. Team score in final match. I messed up with the problem statement because I was just thinking something. Score, final match score, like that. Okay, team final score. Here also I can say team final score. This will probably be more problematic. Team final score. Now, based on this, I have always, again, this is an example, guys. Just think of it. The main idea is to teach you something so that you can apply that anywhere. Okay. So here I have got minus 1. Here I got minus 1. Here I got minus 1.25. Now see, I have seen that the mean is 2 in 2021. So let me write it down again for you. So if in 2021, the mean is 250. Over here you can see the mean is 250. X of I is nothing but how much? It is nothing but 240, and the mean is 10. And the standard deviation is 10. If I have this information, can I draw the bell curve? So this is my bell curve. The mean is how much? 250. Standard deviation is 10, basically means this will come as 260, 270, 280, right? This will come as 240, 230, 220, right? And this is my mean. Now, where does 240 fall into? 240 is falling into minus 1 standard deviation. So that basically means 240 will fall here. Now, in 2020, you know that your mean is how much? 260, right? Your mean is 260. X of I, that is your final score, is 245. And your standard deviation is nothing but 12. Now, based on this, I will definitely be able to create another curve which will have this kind of bell curve, and my central element will be 260. Since my standard deviation is 12, this will become 272, then it will become 284, then it will become 296. Similarly, over here it will become 248, then it will become 236, then it will become 224. So here I have my value over here, and what is the standard deviation over here? It is 1.25. So 1.2 minus 1.25 is this specific standard deviation. Now here you can see the area is little bit less. Here the area is little bit more. So where do you think India has probably performed well in the final match? In the final match, whether India performed well in 2020 or in 2021. Based on this information basically tells many things about probably the pitch condition. Whenever we say the standard deviation is less, that basically means most of the score was rotating around that much values. So tell me where probably India may have performed well. Understand guys, here the standard deviation is more. Here the standard deviation is less. Understand over here, obviously the Z score value is -1. Here the Z score value is -1.25, which is greater. Okay, now let's go to one more practical example of Z score. Now this example most of the time with respect to statistics will come. This may be probably asked in interviews also. And this is a very important question. I will probably take one very good example and show it to you how to be done, how you can basically do this, and how you can actually learn it. Okay. So one problem statement that I am actually going to give to you is that one example I'll give you, then we will try to see. Let's consider that I have an X random variable. So let's come to the stats interview question. Now in this stats interview question, let's say that I have a random variable X, and let's say that this random variable has this kind of distribution: 4, 5, 6, 7, 3, 2, 1. And let's say that I have a bell curve which looks like this. Now I want to know, my question is, what percentage of scores fall above 4.25? Now understand one thing, where does 4.25 fall? 4.25 will fall over here. So this is basically my mean, and 4.25 will fall over here. Let's consider that it is falling over here. My question is that these are my scores, right? Let's say that these are my scores, 2, 3, 4, 5, 1, like these are my scores. I need to understand from this distribution, from this my entire data set, what is the percentage of scores that falls above 4.25. That basically means I am interested in this region. I'm saying that what is the percentage of the scores that are greater than 4.25? This is my question. Okay, simple question is this. And now we'll try to understand how we can use Z score in this. So everybody knows about Z score formula: x of I minus mu divided by standard deviation. Here my mu is 4, standard deviation is 1. What is my x of I? X of I is nothing but 4.25 minus 4 divided by 1. This value is 0.25 standard deviation. 0.25 standard deviation. What does this basically mean? 4.25 falls 0.25 standard deviation from the mean. Okay, from the mean. From the mean it is basically falling to 0.25 standard deviation. Now I got the standard deviation. This is I got with the help of Z score. But now what is the next very important thing? Obviously from this we will not be able to understand, okay, what will be the percentage then. Probably this I have got that it is 0.25 is my standard deviation or a Z score. My Z score is 0.25. Now I'm interested in this region. So how do I come up with the overall percentage from this particular region? Understand one thing. This is a symmetrical bell curve. That basically means the entire area I can basically consider it as 1. Now since I am interested in this region, I will say this region as tail. Whenever we talk about tail, the region that I'm actually interested in, basically I want the value with respect to this. One part of the region I'll say it as tail. The other part, that is the remaining portion, I will basically say this as body, full from here to here. So this will basically be my body. Now understand one very important thing. How do I check based on this Z score what should be the value or what should be the body curve, the area of the body curve? I want to find out what is the area of this. Z scores actually help you to find area of the body curve. How do we find out? I'll talk about it. Z score will definitely help you to find out the area of the body curve. Now guys, just think over it, okay? What do you think this percentage may be? This red region percentage may be. What do you think? Over here, three numbers are there. Let's say that total numbers are 7. And when I say three numbers on the right hand side, what may be the percentage? If I say 3 by 7, what is 3 by 7? It is approximately around 48 to 49%, right? Now, can we calculate the same thing with the help of Z score? The answer is yes. I have already seen the Z value is 0.25. Now let me do one thing. Let me open something called as Z table, because I want to find out the area of the curve. So Z table, if I go and search for it, you will be able to see in the first link. And over here, I'll just go over here. Now see, this is how my curves look like, right? See over here, Z score, I'll just use another table because this table does not look right. Okay, so let's consider this table. So always remember, three types of Z score we can basically get. One is this type, which again I'll be discussing. One is in this type. Okay, now see this left Z table, and this is right Z table. Okay, just a second, I will just show you how to make the readings over here. 2.2 Z is 0.25, right? 0.25. See over here, what is my Z score from here? What is my Z score over here? 0.25. And remember, this Z table will be giving me the area of the body curve. See, a Z table shows the area to the right hand side of the curve. Use these values to find the area between Z is equal to 0 and any positive value. For area in the left table, look at the left tail Z table instead. Okay? If you want to find out the area in the left tail, search for it, guys. If you want to find an area in the left tail, look at the left tail Z table instead. In this particular case, let me take left Z table, because I want to look at the area of this. See this, guys. This is the area. Right now, this area I want to get the answer, right? If I get the answer of this area, I can just subtract 1 minus the left area. I want to get this particular area. Let me explain once again. Okay, everybody is able to see this? Over here, just see very, very important thing. The Z table shows the area to the right hand side of the curve. Use these values to find the area between 0 and any positive value. For area in the left tail, look at the left tail Z table instead. So here you can see that I want to see the left tail or right tail. Okay, what you want to see? Okay, first of all, see that. You come to this particular diagram. You want to see this part or this part? Obviously, you want to calculate this part. But understand one thing. In order to calculate this part, if I get the value of this part, I can just subtract 1 minus left area, right? If I subtract 1 minus left area, will I not be able to get the right part? Otherwise, you directly go and see in the right table. Again, I am showing you. Here, you can see 0.25, right? So 0.25, you will be able to see this much. This area will be giving from mean to this standard deviation. Right table is given. Don't worry, left table is also given. See over here, left table is also given. You can also check this. This table will be giving you the value between this to this. Then probably you have to find out this one or subtract 1 minus this area. Then you will be able to understand it. Now I will go to the left table. Understand? Again, I am going to repeat, guys. Here clearly it is given that for area in left tail, look at the left tail Z table. Why I am seeing left tail? Because if I go over here, This is my right tail. This is my remaining body. Left tail can become this part. So from the entire body, if I subtract 1 minus this, I will be able to get this. Very much simple. Now, how do I check this? I'll go over here. It has given me the instruction over here for area and left tail. Look at left tail Z table instead. So if I go and see, this is my left Z table. Now I will go and find out the Z value of 0.2 and 0.2 and 5. So how much I am getting? 0.5987. So 0.5987 will be my value of this. My area of the body curve will be 0.5987. Now, in order to find out this, I will subtract 1 minus 0.5987, 0.4013. So what is the percentage of scores that fall above 4.25? It is nothing but 40%. Why subtracting from 1? It's very simple. No, see guys, again I'm talking about this. My question is that this is my mean. From this particular curve, I want to find out what is the percentage of the distribution. Then what I can do if I want to find out this curve, I can take this whole curve, subtract with the left one. Then I will be getting this one. So here you are able to get 40%. Now did you understand how important it is basically to understand Z-score? Yes, 0.59 is the mean to all the left. This entire region from this to this, from 0.25 standard deviation to the left part. Now did you find out how important this is for the interview questions, guys? Why not directly taking from the right table? Understand guys, right table is not given. No, this is not right table. This is only given from here to here. If you want to find out from left table, then this is the diagram for this, for left Z table. Understand one thing, very much important. You cannot take it from right table. Right table, there is no information about it. You can see this graph, right? It is only giving information from here to here. In the left table, you will be able to get the information of the body of the area of the body of this particular part. So this was an example with respect to Z-score, standardization, all these things we have probably discussed. So the question is, in India, the average IQ is 100 with a standard deviation of 15. What percentage of the population would you expect to have an IQ lower than 85? So my Z-score will be what? So first of all, let's discuss about this graph. So here you can see that this is my graph. So this particular value is how much? The mean is 100. My standard deviation is 50. So 115, 130, 145. Similarly, I have 85, 70, 55. So I have all these values over here. Now with respect to this, first of all, let's go and compute the Z-score. How do you compute the Z-score? The same example that what we have done over here. Here in this particular case, 4.25 falls over. We are just taking IQ lower than 85. So what is IQ lower than 85? So it will become 85 minus 100 divided by 15. What it is? Minus 15 by 15. It is minus 1. So 1 standard deviation. This is my mean. This is my minus 1 standard deviation. Now this is the area that I want to find out. Now when I want to find out this particular area, this area is already the body part, the left of the curve. So what I will do, I will just go and compute for minus 1. Now if I want for minus 1, what it is? Go and compute it over here. How much it is? 1.0. So this is 0.86. Let me just compare the answers. Or let me just select some different Z table so that you will get an idea. I'm actually not able to find the right Z table. Yeah, this looks good. So I will give you the link 0.84. So what I'm actually getting? 0.84134. 0.84134. This is plus 1. Understand, this is plus 1. Plus 1 when I say, understand over here, plus 1 when I say, it is basically from this region to this region. Now if I subtract 1 minus 0.8414, 0.84134, that will basically be my values, right? Lower than 85. Understand, lower than 85, lower. You may also get a question, IQ between 90 to 120. Like this question also you may get for the same problem statement. So you may get questions like this. At that point of time, again, you have to solve it in a different way. But here is just an idea to talk about what is body area of the body. Yeah, negative will not matter. If you say negative, it will come from here. If you say, sorry, if you say negative, it will come from here. If you say positive, it will come from here. Understand, both the side are symmetric. -1 also you can look. That only I'm saying, no, in the table, whatever you are able to find out, you can definitely check out from -1 also from top. -1.0. Same thing you'll be getting, right? -1.0 is 1.15886, which is 1 minus 0.84, right? Same thing. Now let me do one thing, guys. Quickly show you Google Colab Pro so that we can have some programming sessions. So first of all, I'm going to import some libraries as this. Import numpy as np. Import matplotlib.pyplot as plt, and then probably I will say matplotlib inline. So all these things we are actually done, and then probably I'll also import statistics. Now first thing first, how to compute mean, median, mode. Okay, we are going to see that. First of all, let me load a data set which is called as, I'll load a data set which is called as tips, and this will basically be giving me df is equal to this one. Then I'll say df.head. So here you can see this is my entire data set. Now quickly, if you want to see how to do mean for this, let's say that I'm using np.mean function for finding the total bill mean, total bill of mean. Okay, so if I execute this, you will be able to see the answer. So this is the, what is the mean of the total bill. If I want to probably find out the median also, you will be able to find out median, np.median, df of total bill. So here you will be able to see np.median. So over here you see some differences. If you are seeing some differences, think that there may be something like some kind of outliers also. Okay. If you want to try for mode, I can use statistics.mode, and again I will be using df of total underscore bill. So here you go. This is got, mode is nothing but 13.42. Now the thing is that if I want to go and see my box plot, which is basically used to see outliers. So if I use df of total bill, total underscore bill, so here you will be able to see my box plot also. So this is one example of box plot. So does this indicate it has an outlier? Now definitely over here outliers is present, but what is this? This is 25%, sorry, minimum, 25 percentile, median, 75 percentile, and max. So all these things we have calculated. If you write df of SNS dot, there is something called as hist plot, which will basically help you to create histograms on a specific feature. So if I execute this, you will be able to see one example which looks like this. Is this a normal distributed data? I guess no. If you want to see with probability density function, I'll be using KDE is equal to true. So with KD is equal to true, does this look like a normally distributed? No. It is like a little bit skewed towards the right. I'll also show you some examples with respect to normally distributed data. So for that, I will do sns.load underscore dataset. I will be using iris dataset. Iris flower dataset basically is the dataset which will actually help you to give a data of a different types of flowers with respect to iris. So here you will be able to see that df1.head. So here you have flowers like setosa, versicolor, and here you have 4 features: sepal length, sepal width, petal length, and petal width. Now let's see, I will just try to plot the same thing with one of the feature. Okay, let's say that I am doing it with sepal length, sepal underscore length, df1. So here you can see that. Does this follow a Gaussian distribution? Does this follow a Gaussian distribution? No, I guess. Let's try with sepal width. Finally, we'll be able to see something. Wow, this follows a Gaussian distribution. Definitely, we can definitely say for this, this is a Gaussian distribution. So this is specifically a Gaussian distribution over here. And here you can also apply that rule, that is 68, 95, 99.7 percentage rule. So all these things you can basically check out over here and you are getting this. I'll also show you how to construct this PDF function and all as we go ahead. Okay, it is normally distributed. Definitely we can say that it is normally distributed. Okay. So this was one example with respect to normally distributed. This is not normally distributed, you know. SNS dot count plot of df of, if I use count plot with respect to species. Species spelling is wrong. Okay, df1. Again, I'm writing df. What is this plot, guys? This is a bar graph. Bar plot or bar graph, whatever you want. Okay, percentiles. Let's do for percentile. So for percentile, I can use np dot percentile and I can use my df of, let me open one example that I had written for you. So I will basically use over here like this. Let's say I'm going to use sepal length, and here I can basically give some parameters, like let's say that I want to get the 25 percentile and 75 percentile. So if I execute it here, sepal length, here's a df1. So here you can see that I'm getting 5.1 as the 25 percentile and 75 percentile is 6.4. So my IQR will be 6.4 minus 5.1. If you want to probably get the 99 percentile also, you can basically write like this, 99. So here you will be able to get the value 5.1 and 7.7. Hello guys. So how are you all? I hope everybody is doing well. So let's start. Today, what all things we are going to do. First of all, we are going to implement this IQR using Python. Okay. The second topic we are going to discuss about is probability. The third thing that we are going to discuss about is something called as permutation and combination. Once we finish this up, the fourth thing that we are going to discuss about is something called as confidence intervals. So in confidence intervals, then probably if we get time, we will cover up p value, and then we will start with hypothesis testing. Now what we are going to do, first of all, I am going to start with Google Colab. You can also open Google Colab. Okay, so I will just make a new notebook. So first of all, we'll try to implement z-score and try to find out IQR. And with respect to that, we will try to see what all things we can basically implement. Other distributions will also come. Don't worry. Bernoulli, binomial distribution, power law distribution, everything will be discussed. First, let's go in some specific order I've actually decided, and when those distribution will basically come, we'll discuss about it. Okay. Here you go. So in this session, we are going to first of all discuss about outlier. Now, first of all, what I'm actually going to do over here is that I'm going to import some libraries. Import numpy as np. Okay. Import matplotlib.pyplot as plt. And then I'm just going to import matplotlib inline. So I'll be executing this. Now the next thing that probably we will be discussing about is that let's define our data set. So here I'm going to just define our data set. Data set, you can take up anything that you probably want. You can just define your own data set, whatever data set you like. Now for my sake, I have just created one data set over here. So here you will be able to see that this is my data set. Can you say some numbers that are like kind of outliers in this? So now the first thing that we are probably going to do is that let's say that using z-score, I probably want to also find out some outliers. Now using z-score, how do you find out some outliers? Now let me just go and explain you over here. Let's say that you know about normal distribution. Till now we have discussed so many things in normal distribution. We know that this is the mean, first standard deviation, second standard deviation, third standard deviation, first, second and third standard deviation to the left. You know that 68 percentage of data, 95 percentage of data, and 99.7 percentage of data. Can I consider that during some of the scenarios, if my data is normally distributed, after the third standard deviation, probably the data are outliers? Yes or no? Yes. After third standard deviation, whatever data is basically present, right? Data are outliers? Yes or no? Just think over it. Most of the time, if the values are after probably third standard deviation, they are like kind of outliers. Yes. So just think over it, guys. it can be treated as an outlier, right? If data is present after third standard deviation. So first we'll try to implement this. Now what I am actually going to do over here is that, first of all, let me make a list. Okay, so here I'm just saying it is outliers. I'm going to basically create it as a list and put up all outliers inside this. Let's define, and how do you find out standard deviation, or by using z-score, right? We can definitely find out z-score with the help of z-score, how many data set or data points actually fall within the third standard deviation. So here I'm actually going to create a function which says define detect underscore outliers. So this will be my function. And here I'm going to give my data. Now the first thing that I will create a threshold. My threshold will basically be 3 standard deviation, right? Anything that falls away from the 3 standard deviation, I will basically be able to do it. And I hope everybody remembers the formula. The formula for z-score is what? If I go and probably define over here, my z-score formula is nothing but, it is x of I minus mu divided by standard deviation. We usually also write this formula by root n, but I'll talk about it why specifically I'm not specifying root n over here. Over here, I'll just try to use this formula. Okay, so this is basically the z-score formula. Okay, so I have to implement this formula in Python programming language. Okay, so what I am actually going to do, first of all, obviously in this, I need to compute mean, I need to compute standard deviation. You know how to compute mean, right? So here I will say mean is equal to np dot mean, and here I can actually give my data points, which will actually help me to find out mean. Then my standard deviation, here I can basically write np dot standard deviation of that specific data. I will be able to get the standard deviation. So I have got my mean and standard deviation. Now for each and every points inside my data set, I will just apply the z-score formula. So I'll say for I in data, I can say z-score is equal to I is my x of I points, right? I'll say x I minus mean, right, divided by standard deviation. So this is my z-score formula, and for every item I'm actually trying to find out the z-score formula. Z-score will basically give you how many standard deviation it is away from mean. So I can write one condition to check whether it falls below the third standard deviation or not. So I can basically use nb.absolute, which will basically help us to round off the z-score, and I'll say z underscore score is greater than threshold. If it is greater than threshold, what does this basically mean? Let's define threshold over here. I have already defined threshold, right? So if it is greater than threshold, then what does this basically mean? Oh, sorry, it is data set. I'm extremely sorry, data set. Now tell me, if np.apps z-score greater than threshold, what should I do? What does this basically mean? Green, more clarity you want? I think now it is fine, right? What should we do in this? This basically means that it is an outlier, right? Because it is falling away from third standard deviation. It is falling below beyond the third standard deviation. So what I can basically do is that I can just write something like this, because I have created a list. So I'll say outlier.append, and I'm going to append that specific z-score value. So I hope it is fine. I'm just going to append this z-score value, not z-score. I will append the I value, because I in data set, yes, I'm just going to append this I, yeah, outliers, sorry. It is outliers dot append of I. And then finally, what I'm actually going to do, I'm just going to return the outliers, return outlier. Let's see whether it will work or not. I'm also trying it for the first time. So this is my function that has got executed. I will just execute one more code. Threshold 3 basically means this defines our third standard deviation. Below, like beyond third standard deviation, I can basically say that this actually falls on. If you want to probably go and check how this distribution is, so I can write plot.hist on a specific data set. PLT is not defined. Why? Okay, this should be PLT. It's okay whether it is normally distributed or not, but I am actually trying to see this. Okay, there are some definite outliers, but it's okay. Let's see that whether we will be able to do this or not. What is which are past has changed data set data in for loop. It is simple, right, guys? This function everybody understood or not? Oh, sorry, this should be data. This data I'm actually passing over here. See, threshold here is my third standard deviation. If you want the data set, I can paste this entirely and give in the chat. So this is my chat with respect to the data set. I've already given it to you all. Now let's go and execute it. Now I have executed this. Now what I am actually going to do over here, I'm just going to call detect underscore outliers, and I'm going to call this specific data set. The data set nb.abs. nb.abs basically means nb.absolute function. Now once I execute it, here you will be seeing that it will be returning this 3 outliers. Are these my outliers or not, guys? The for loop is very simple. For I in data, I'm finding for every data which is in the form of list all the z score, and I'm comparing if the z score is greater than 3 or not. If it is greater than 3, I'm considering it as an outlier. Here you can see all the outliers are there. Outliers means a big number, right? If you have not attended the previous session, guys, see, if you have not attended the previous session, you can drop off, okay? Because you'll not be able to understand. This is a 7 days live session. Now I have got the outliers. Now this is one way how we can use z-score. So this was an example of actual z-score. So I'm just going to write it as z-score computation, and basically we have done it. Now let's go towards the IQR. IQR basically means interquartile range. So for interquartile range, what type of code I will be writing? Always understand in IQR, what are we discussing in IQR? First of all, we need to find out Q1. Q1 is 25 percentile. Then we have Q3. Q3 is 75 percentile. Then if I subtract 75 percentile minus 25 percentile, I will basically get the IQR, right? And always understand in IQR what we do. We basically find out what do we do in IQR? In IQR, we basically find out the lower fence and higher fence. That we really need to find out in case of IQR. So how do I write the code? Because this theoretical is already explained. So I'll write down all the steps that is required. So the first step is that I want to sort the data. Let's say that I'm sorting the data. Okay. This is the first step. The second step is that I will calculate Q1 and Q3. Q1 and Q3 is pretty much important in this particular case. So I need to do it in this scenario. I'll just move this up. I'll copy and paste it over here. So the first step is basically sort the data, and then calculate Q1 and Q3. Then we need to find out IQR, which is nothing but the third step, which is nothing but the subtraction of Q3 minus Q1. Then we need to find the lower fence. Now lower fence formula, I hope everybody knows it. So it is nothing but Q1 plus or minus, it is Q1 minus 1.5 multiplied by IQR, right? This is the formula to basically find out the lower fence. Then find the upper fence. Here I will basically be using Q3 plus 1.5 multiplied by IQR. So these are the steps that we are probably going to do. So these are my steps that I am actually going to plan for, and based on the steps, I will be implementing it. So these are the steps that I will be performing in order to find the outliers with the help of IQR. Now, first of all, if I really want to find out the sorted data set, how do I find out the sorted data set? Sorted data set, I will just say this will be my data set, and I can use sorted function. And in sorted function, if I give you the data set, this will basically be my sorted data set. So sorted is an inbuilt function which will actually help you to sort all the numbers. Okay, sort all the numbers over here. So right now I have actually created a data set which is completely sorted. So my first step is done. So I am done with my first step. Now second step, I need to calculate Q1 and Q3. So I'll say Q1 comma Q3, and here I will basically use np.percentile. I will give my data set over here. Along with this, I'll give two values. One is 25 comma 75. So once I execute it, you can see that it has got executed. Now I'm going to just print Q1 comma Q3. So here you can see which is my Q1, Q3. This is my 25 percentile. This is my what percentile? This is my 75 percentile. Now once we have this, now let's go ahead and compute the lower fence and the higher fence. Now in order to compute the lower fence and the higher fence, here I'm just going to write the comment. Find the lower fence and higher fence. The lower fence is equal to Q1, right, minus 1.5 multiplied by IQR. And before that, I need to compute the IQR. Let's say IQR is equal to Q3 minus Q1. So if I go ahead and print IQR, what is this error it is coming as? Now if I go and execute this, you will be seeing that IQR is 3. So this is my lower fence. For the higher fence, I will basically write higher fence is equal to Q3 plus 1.5 multiplied by IQR. Once I execute it, now I know my lower fence and higher. So I'm going to print lower underscore fence, higher underscore fence. So if I print it, it is 7.5 to 19.5. Now the further part, I think you can comfortably do it. And based on this lower fence and higher fence, you can write a condition and you can remove all the elements that is required. So now you can basically write, don't worry whether the data is normally distributed or not. Here what we are doing is that whatever data set you are basically getting, what you can actually do, you can basically find the lower fence and higher fence and basically do this thing. Now instead of doing all these things, if I import cborn as SNS, okay, and execute it, and there is an option which is called as box plot. We also saw how to create box plot. If the lower fence is negative, then what you can do is that based on that condition, any value lesser than that, you can remove all those things, right? And here if I give my data set, you will be able to see that this will be how a box plot will be created. Now this looks, you see that there is a very big outlier. So that is the reason. And this same outlier we found out with the help of multiple things. And here also you can see 7.5 to 19.5. So most of your data points that will be lying over here will be based on that. If I probably remove those 3 elements and try to see that particular data set, then this box plot will look bigger. Now let's go ahead and discuss about the next topic, which is called as probability. Probability is super important, and in this session I will discuss major important things in probability, and we will try to see that what all things we can actually do with the help of probability. Probability is by default used in machine learning, also in deep learning, also many places. Let's say one example, okay? Suppose I have 2 categories of data set. I have another category of data set. If I try to create a best fit line, you can see that, let's say that this belongs to class A, this belongs to class B. Now over here you will be able to see that if I talk about this, right, when I draw this linear line, this is basically used in linear regression, let's say. Now my question is that what probability of this particular point belongs to class A and what probability of this particular point belongs to class B, because it is passing through the line. So based on probability, we can definitely get a lot of things. In linear regression it is used, in logistically it is used, and all. So probability really focuses like base is basically used over there, and different things are used. Let's understand what exactly is probability. If you want to give a definition, what exactly is a probability? So here you can say that probability is a measure of the likelihood of an event. Probability is a measure of the likelihood of an event. The reason why I'm writing you this all definitions, guys, understand, you really need to think, what exactly is happening over here, what is the definition, if you can remember those definition in an easy way by example. So that is the reason I also give you a lot of examples. Let's say that I am flipping a dice. In a dice, what are my possible sample events? You know that it is 1 2 3 4 5 6. Now if I ask you a question, what is the probability when I roll a dice, roll a dice, not flipping a coin, it should be, I'll say roll a dice, okay? So here I am basically saying roll a dice. So what is the probability of getting 6? If this is my question, then how probability you will be able to calculate? What is the answer? Obviously you'll say 1 by 6, right? It's very simple. So how do we define probability? I'll say that number of ways an event can occur divided by number of possible outcomes. So this is the exact definition of this. Now in this particular scenario, number of ways an event can occur. Over here I am trying to find out what is the probability when I roll a dice I get a 6. So how many events can occur? It can only occur as 1. And what is the number of total possible outcomes? It is 6. So this is how we basically find out. Similarly, if I give one more example, let's say that I want to toss a coin. Obviously I know what are my sample space, head and tail. What is the probability of getting head? You'll just say that 1 by 2, because the sample space is 2 and one number of event that can occur is 1 by 2. So you basically say this as probability of head as 1 by 2. Now let's go one step above probability, which is called as additional rule. Now here is where you will probably discuss about something called as, so let's go to the next topic. Over here I'm basically going to define as addition rule. This is super important. Probably in your aptitudes you will be using this addition rule, or we also say it as probability or also you say it as like this or. Now in order to understand additional rule, you need to understand about two things. One is mutual exclusive events. What is this mutual exclusive events? So I can basically define two events are mutual exclusive. Two events are actually mutual exclusive. They cannot occur at the same time. If they cannot occur at the same time, let's see an example. Rolling a dice. Now when I roll a dice, at a specific time I can either get 1, or I can either get 2, or I can either get 3, or I can either get 4, or I can either get 5 or 6, right? You cannot get 1 and 2 at the same time, or you can't get 1, 2, 3, 4 at the same time. You will only get at one probably one experiment or one event that you're probably rolling a dice at a single time. You'll only be able to get one number. You will not be able to get two numbers. So this is specifically an example of mutual exclusive. Another example again, tossing a coin. In this particular case also, tossing a coin. In this particular case also, what happens? You may either get head or tail. You cannot get both unless and until your coin is standing there like shown in the movies. I hope, which movie am I talking about? Which movies probably I'm talking about? You can also consider, good movies like Sholay. In Sholay only one type of event occurs at every time, right? So for this kind of problem scenarios, now let's discuss about non-mutual exclusive event. Obviously you understood that what is mutual exclusive. Now with respect to non-mutual exclusive, obviously both the events can occur at the same time. Multiple events can occur at the same time. Here I'll say that multiple events can occur at the same time. Two or more events can occur at the same time. Let's say one example. Let's take a deck of cards, a very simple example with respect to this. In deck of cards, have you seen like what will happen in a deck of cards? Two events. Let's consider that from a deck of cards, when I pull out a card, a king can also come, or let's say that a queen card can come. Along with this queen card, a red color heart card can also come. Heart card can also come, right? So here multiple events are there. So these two cards are obviously not mutual exclusive. So here you can see that, okay, I can also pick up a king. It can be in black color. It can also be in red color, right? Multiple things are basically happening. So this is a perfect example of a non-mutual exclusive. Now based on this, there is some amazing problem statements that you can basically solve. Mutual exclusive. Suppose if I toss a coin. So my first question is, if I toss a coin, which is again a mutual exclusive event, what is the probability of the coin landing on heads or tails? Now whenever you get this kind of problem statement, first of all you really need to think that, okay, whether it is mutual exclusive or not. Yes, obviously it is mutual exclusive. Now I need to find out what is the probability of getting heads or tails. Right? This is what I need to find out. I need to find out what is the probability of getting heads or tails, right, from this specific event. So I want to define a common definition probably for this. We can write probability of A or B, where A and B are events, is equal to probability of A plus probability of B. So whenever you have a mutual exclusive event, at that point of time, you can define this specific definition, which is also called as additional rule for mutual exclusive events. Now here, what is probability of A? You know that it is 1 by 2 plus 1 by 2. So the answer will be 1. So probability of A or B to come is basically 1. These are some very, very important things. In exams also you will be getting this. In aptitude also you will be getting it. In multiple things, you'll basically be getting it. Now, I may also tell you, okay, let's take one more example. What is the probability? Suppose if I roll a dice, what is the probability of getting 1 or 3 or 6? Yes, many people are saying it right. It is 1 by 2. So here I will basically say that what is the this I can definitely say it as probability of 1 plus probability of 3 plus probability of 3, 6. These all are 1 by 6 plus 1 by 6 plus 1 by 6, which is nothing but 3 by 6, which is nothing but 1 by 2, which is nothing but 0.5. So 0.5 is basically with respect to this, and here you can easily solve it. Now this was with respect to mutual exclusive. This is what we have discussed in mutual exclusive. If I take the next problem statement for non-mutual exclusive, so for non-mutual exclusive, let me take a very good example again. So the question is very much simple over here. Let's say that you are picking a card. You are picking a card randomly. This is the question from a deck. So the question is, what is the probability of choosing a card that is queen or a heart? So this is the question. Very simple. Obviously, first step, you will see that whether it is mutual exclusive or non-mutual exclusive. Obviously, you will say that in this particular scenario, it is non-mutual exclusive. Or mutual exclusive, it is non-mutual exclusive, right? Because it can occur at the same time. Now, let's go ahead towards the answer. Obviously, you understood that this is non-mutual exclusive. Now, how do you solve this specific problem? Now, in this specific problem, first of all, you need to find out what all different things it is basically asked. Let's say that I have got probability of getting a queen. What is probability of getting a queen, guys? Just think over it. How many cards, how many queen card will be in deck of card? In the total deck of cards, there are 52 cards, right? If none of you have played cards, please go by today and see. The probability of getting queen is nothing but 4 by 52 because in every deck there will be 4 queen cards. Now, the next thing, probability of heart cards. So, what is this probability of heart? How many heart cards will basically be there in a deck? Obviously, there will be 13 cards. So, I'll say 13 by 52. Now, the next thing is that probability of queen and heart, because this is also one possibility, right? This is also one possibility. How many queen and heart will be there basically? It will be only one. So here I will write 1 by 52. So these are the possible things that can occur, right? This is the thing. Now if I come to the formula, and this is the addition rule for non-mutual exclusive event, non-mutual, I can write probability of A or B is equal to probability of A plus probability of B. There will be one important thing, which is this intersection, which I have to basically separate it. So it will be P probability minus P, sorry, minus probability of A intersection B. A intersection B basically means A and B, which is the possibility of both. Now my question is very much simple. What is the probability of getting queen or heart? I'll draw it with red color. You have the answer with you. This will be probability of queen plus probability of heart minus probability of queen and heart. So what is probability of Q? 4 by 52. What is probability of heart? It is 13 by 52. And what is probability of queen and heart? It is 1 by 52. So here I am actually getting 52. This will be 17 minus 1, 16. 16, how much is the 52? You can calculate. This will basically be the probability. Now you have probably understood addition rule. Now we need to understand one more rule in probability. See guys, if you do this much, I think you will be able to solve any problem statement that comes in your mind. So here was the problem statement that we did, and this was specifically to something called as addition rule. Now coming to the third one, which is called as multiplication rule. In multiplication rule, one thing you need to understand here, we need to understand something called as independent events and non-independent events. These are something very, very important. Sorry, it should be and, I said or heart. Okay. Independent events. Okay. Now, in the case of independent events, what are specifically independent events? Let me talk about an example. Let's say that I am rolling a dice. If I roll a dice, I may get 1, 2, 3, 4, 5, 6. Suppose for the first instance I got 1. In the second instance, it is possible I may get 1. In the third instance, I may get 2, I may get any number. So one event is not at all dependent on the other event, right? Because anytime we roll, every possibilities or every outcomes has an equal probability to come. So over here, what you can understand is that each and every events are independent. If one comes, or if two comes, or if any events come, it is not going to impact any other event. Every time you probably have to roll, and everybody has an equal probability to come over here. This is what is an independent event called. Let me talk about non-independent event, or I will also say it as not non-independent, but instead I'll say dependent event. So I will talk about dependent event. Now in dependent events, suppose let's say that I have a bag. In this bag, let's say I have 3 red marbles and 2 green marbles. Now in the first instance, if I pick up a marble, what is the probability of red marble? What is the probability of taking out the marble? Very simple. You will be seeing that how many number of marbles are there? There are total 5 marbles. And how many number of red marbles are there? There are 3 marbles. So you are basically able to write 3 by 5. Now let's consider in the first event, you picked out a red marble. So you picked out a red marble. So I'll make it as red color. Now, after taking out the red marble, how many marbles are remaining? So I will now update this. Okay. So how I'll update this? I'll update this bag. Now this bag will basically have 2 red marble and 2 green marble. Now, if I try to go ahead and find out what is the probability of now taking out a green marble, then how you'll basically say, you'll see that, okay, how many number of marbles are there? 2 by 4. So here what is happening after this particular event, it has impacted this event because the number of marbles was reduced, and finally you got 2 over here. So this is a perfect example of a dependent event. Multiplication rule basically says that in the case of an independent event, we have to solve it in a different way. In the case of a dependent event, we have to solve in a different way. Because of this dependent event, there is an amazing algorithm which is called as naive Bayes. Have you heard of naive Bayes? I think most of you have heard of, right? There is a topic which is called as conditional probability. This is where conditional probability will come into existence. So I will talk about it. Okay. So let's go and solve some problems. So let me just go ahead and talk about a problem statement. First, we will talk about independent events. So independent events, we are going to basically discuss about the problem. First thing, the question is, what is the probability of rolling a 5 and then a 4? So this is your question. What it is saying? What is the probability? In the first event, you have rolled a dice, you are getting 5, and then again you rolled a dice, then you got 4. So what is the probability of getting 5 and then 4? This is a simple question, and for this obviously is an independent event. You know that. Now, how do we solve this particular problem? So I'll say independent event, here we'll apply the multiplication rule. What is the multiplication rule? What is the probability of A and B? A and basically means first A event has occurred and then B event has occurred. What is the probability of this? So obviously here, I'll define the formula over here. First of all, I'll say probability of A multiplied by probability of B. A and then B. Okay, so this is the usual formula that we use for an independent event in a multiplicative rule. So obviously you know what is probability of A. So here I'll say probability of 5 and 4. You know probability of 5. Probability of 5 is nothing but 1 by 2 multiplied by, 1 by 6. 1 by 6 multiplied by 1 by 6. It is nothing but 1 by 36. Now let's take another example. Obviously because independent event looks very simple. So here I'm basically going to take another example, and this example will be of a dependent event. So let's go ahead and let's try to solve a problem for this. What is the probability of drawing a queen and then a aces from a deck of cards? See over here, 2 events are actually happening. So let's go ahead. First of all, again, you need to find out whether this is an independent or dependent event. Obviously, in this case, this will be a dependent event because a deck of cards will get reduced. So in this particular case, I am saying what is the probability of A and B in the case of independent event. So here I can basically write probability of A multiplied by probability of B given A. Now what does this mean? This term is basically called as conditional probability. Let me show you an example with respect to the bags, right? So I have a bag over here. Let's say that I have 3 marbles, 2 red marble, okay? Now in the first instance, I want to find out what is probability of green and then red marble. Now see over here, how many marbles are there in the first instance if I'm taking out green? Obviously there is 3 by 5, right? In the first instance when I took out the green marble. After I take out the green marble, my total number of marbles that will be remaining is 4. So the probability of red will be 2 by 4. Now this term is basically probability of green. And what is this term? 2 by 4. This is nothing but this only, right? Multiplied by probability of green given red. Sorry. Probability of red given green. Given green basically means this green event has already occurred, right? So that is the reason the number of marbles has got reduced. This is called as conditional probability, and this is very, very helpful in something called as Naive Bayes, or I'll also say it as Bayes theorem. In Bayes theorem, this will be very, very important. So here, what is probability of king? It is queen and king, right? Queen and aces, sorry. So here what I'll do, probability of queen multiplied by probability of aces given queen. So what is probability of queen? It is nothing but 4 by 52 multiplied by 4 by 51. So, sorry, 53. How many cards are there? I forgot. How many cards will be there in deck? 53, right? Kahan gaya? No, 52 only. Don't confuse me, guys. Okay, 4 by 52 multiplied by 4 by 51. So whatever answer you get over here, this is basically your. Now let's discuss about something called as permutation and combination. A very small topic, probably in 5 minutes I will be able to complete it. Now let's say that, first of all, let's discuss about permutation. Let's say that I have taken some students to a school trip, and then we have gone to something like a chocolate factory, in which many chocolates are basically they create a lot of chocolates. They make a lot of chocolates. Okay, so I catch a hold of a student and I say that, okay, I'll give you an assignment, and let's say that in this chocolate factory 6 different types of chocolates are created, like dairy milk, right, like 5-star, Milky Bar, and let's say eclairs, okay, gem. How many? 1 2 3 4 5, and one more chocolate, normal toffee. Let's say one more category, silk of dairy milk is there. So these many chocolates are basically there. So I've given a student an assignment to that, saying that, okay, there are 6 chocolates that are getting created in this factory. Let's create, in your diary, you write the first 3 chocolates, whichever you see. Whichever chocolates you see, once you enter into that factory, whichever chocolate you probably see the top 3, the first 3, you just write that name and you come back to me. So that student went inside the factory. Now in the first instance, how many different options this particular student can have of seeing the chocolates? He may definitely have 6 different options. Now once he sees probably any one chocolate, right, he may have 6 options, because 6 different, any chocolate he may see, right? So obviously he may have 6 options, out of which he writes one name over here. Let's say in the next instance, how many chocolates will remain? Total 5 will remain. So how many options he will have to write the name? 5 he will have the right to write the name of the chocolate. Then finally here you will be seeing that when he comes and write the third name over there, they will be having 4 options. Now if I try to multiply this, 6 multiplied by 5 multiplied by 4, it is nothing but 120. Now 120, what it is? It is all the possible permutations with respect to the chocolate name that he may see. All the possible permutation. Like he may see in this way, dairy milk, gems, Milky Bar. He may also see in different way, Milky Bar, gem, dairy milk. So all the possible options that are possible is 120. Now when I say 120, okay, these are all the possible options. Now this is what permutation is. Permutation formula, how do you write? Now let's go back to school days where directly used to ratify all the formulas. NPR is equal to n factorial divided by n minus r factorial. Over here, n is nothing but the total number of chocolates. R is nothing but how many names I have told that person to write. So here you will be seeing 6 factorial divided by 6 minus 3 factorial, which is nothing but 6 into multiplied by 4 multiplied by 3 factorial divided by 3 factorial. This and this will get cut. So total answer is 120. This is with respect to permutation. Now, how does combination come into existence now? And what is the difference between permutation and combination? Now in combination, always understand permutation. If I have the same element like this, I have dairy milk, I have gems, I have probably eclairs. If I've used this element once, this combination, I cannot use the same element and probably make a different combination. So combination will be unique with respect to the elements that is used. Okay. If I have used dairy milk, gem and eclair, I cannot again reswap it and make it as a different order. So in the case of combination, you have a other formula which will actually help you to focus on the uniqueness of the objects that you are picking up. So for this, the formula is NCR, which is nothing but n factorial divided by r factorial n minus r factorial. What is n factorial? You know that it is 6 factorial. What is r factorial? 3 factorial and 6 minus 3 factorial. So here you will basically say 5 more 4 and this will be divided by 3 factorial. This I'll make it as 3 to 1 multiplied by 3 factorial. This and this will get cut. 2 1s are 2 2s are 3 1s are 3 2. 5 2s are 10, 10 2s are 20. So 20 unique combinations you can basically have. Let's say, first of all, the first topic that we are probably going to discuss about is something called as p-value. Super important topic. Many people gets confused in this. Now, let's take one example. Everybody uses a laptop. Let's say that this is my laptop. This is my mouse pad. This is your right button to click. This is your left button to click. Your laptop mouse pad over here, you will move the fingers, right? Here you will move the fingers. Let's go ahead and let's understand. Don't you think most of the time when you're moving your fingers, you will be moving in this specific region? In this specific region? You will be moving your fingers in this specific region, not in the corner. Hardly you'll touch somewhere in the corner. Now, why I'm specifically drawing this? Because this thing will basically specify your distribution of touches. And most of the time, your distribution of touches will be also looking something like this. Now, understand one thing. Why this area is bulged? This area is bulged because most of the times you will be touching here. This area is less because over here hardly you will be touching over here. Now let's consider that I say my p-value for this position is 0.8. Now here what I am actually going to do, what does this 0.8 basically means? That let's say I am doing 100 times I'm touching this mouse pad. 100 times I'm touching, or let's say that every 100 times, okay, let's remove this. I'll write in white color only. Every 100 time I touch the mouse pad, 80 times out of this 100, 80 times I touch this specific region. I hope everybody understood this one. Every 100 times probably I touch this mouse pad. The probability of touching this region is 80 times. That is 80%. Similarly, if I say my p-value over here is 0.01, what does this mean? Similarly, you can consider any region. This region is the tippest, like broadest, right? So this region may be p is equal to 0.9. That basically means out of every 100 touches, I am basically touching 90 times over here. This will be one time. This will be only one time. So I hope you are getting the understanding of p-value. P-value basically says most of the time what is the probability with respect to a p-value for that specific experiment. Now let's go ahead and let's understand something called as, now I'm going to combine multiple topics. The first topic that I am going to combine is something called as hypothesis testing. In that, I'm going to combine confidence interval. In that, I'm going to combine significance value. In that, I'm going to combine many things. Okay. Let's say I am solving a problem. Okay. My problem is I have a coin. I want to test whether this coin is a fair coin or not. Simple problem statement. I have a coin. I want to test whether this coin is a fair coin or not by performing 100 tosses. Now we are entering into inferential statistics. Okay, very important, super important. When do you think a coin is a fair coin? Obviously, when the probability of heads should be 0.5, when the probability of tail should be 0.5. If you have this two condition, definitely you will be saying that yes, in this particular scenario, obviously the coin will be a fair coin. But if you have a Cholet coin, then what will happen? If you have a Cholet coin, then probability of heads was 100%. So for this kind of things, you'll definitely not say that it is a fair coin. Now, in order to support this, I am performing 100 experiments. 100 experiment basically means 100 tosses. So 100 tosses I will be performing. Now inside this 100 tosses, what I am going to do is that, let's say that from this 100 tosses, obviously what will be the mean? Let's say that I'm just focusing on probability of head. I should basically get 50 times. So from this 100 times, if I'm performing 100 experiment, I can definitely say that my probability of head, or probably let's consider that, forget about this probability of head. The number of times I should get head is how much? 50, right? If I get 50 times head, I can definitely say that the coin is fair. The coin is fair. I can definitely say this. If the number of times after performing 100 experiment, if I get 50 times head, I can definitely say the coin is fair. Now, very important. First of all, in this particular scenario, we have to focus on something called as hypothesis testing. We have to focus on hypothesis testing. In hypothesis testing, the first thing is that we need to define our null hypothesis. The null hypothesis is usually given in the problem statement. What is we want to test whether the coin is a fair coin or not. So whatever the default question is, I'm going to use it as a null hypothesis. So here I'm saying that the coin is fair. Like one scenario you have, right? A person cannot be acquitted as a criminal unless and until it is proved. So the coin is fair. Now the second thing that we basically define is something called as alternate hypothesis. Here I'll say the coin is unfair. Now the third step, and always remember, alternate hypothesis will be the opposite of null hypothesis, whatever thing we are trying to put. Okay. Now the third thing is that we perform the experiments, and the experiment can be anything. It can be a Z test, T test, whatever things you want, you can do. All this practical, I will discuss it. Don't worry. Now inside this experiment, we see some values, and based on that, the fourth step that we do, we reject or accept the null hypothesis. Null hypothesis. These are the possible steps of the hypothesis testing. Now let's define this, guys. Let's say that my mean value is 50. I need to get at least 50 times head, right? I need to get 50 times head, yes or no? Let's consider that this is my mean. Okay, minimum 50, not minimum, but 50. 50 I should be getting in order to say that my coin is fair. Let's say that for this problem statement, I'm just examining, okay? The standard deviation is 10. So it will come as 60, 70, 80, 90, 40, 30, 20, 10. Okay, right? In this particular case, it is there. And probably if I know my mean and standard deviation, I may draw a curve which looks like this. What happens if I want to prove this? Now see this. I'll perform the experiment. Let's say I have performed 100 times. Now just imagine I got 30 times head. Let's imagine I got 30 times head. 30 times head is nothing but it is somewhere at this point. Can I still say that this coin is fair or not? Can I say the coin is fair or not? Or coin is unfair? Can I say? Think over it. If I'm getting 30 times head, can I say that this coin is unfair? You tell me whether it should be fair or unfair. Tell me. Let's say that I have performed the experiment and I got 30 times head out of 100. So tell me whether this will be fair or no. Many people are saying no, not fair, 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 not fair. So for this to define, it is always said that our experiment should be nearer to the mean. Okay, nearer to the mean. Now, how do we define that how far it can be away from the mean? We need to define that how far it may be away from the mean. So for that, we use a very important property which is called as significance value. Now, this significance value is basically given by alpha. Suppose let's consider that I am considering alpha as 0.05. Now, this 0.05, what exactly it is? What exactly it actually means? This means that if I do 1 minus 0.05, this answer, let's say that this answer, how much it will come? It will basically come as this 0.05. Okay, I have taken my significance value as 0.05. When I convert this into percentage, it will become 5%. Okay, 5%. So from my 100%, if I subtract 5%, this basically indicates that it is 95% confidence interval. Now, what is this 95% confidence interval? If I probably subtract from 1, my probably the 95% confidence interval is there. Okay. Now, this 95% confidence interval is what part? Let's consider that I know my 2.5 is this part, 2.5 is this part. Since this is a two-tailed test, I'll talk about two-tailed test also, don't worry. So let's consider that this part to this part. This is my entire 95% confidence interval. This is defined by a domain expert. Defined by a domain expert. Let's consider that it has been defined. Now, what does that 0.05 indicate? I'm trying to show it to you. When I probably divide this into two parts, here my 2.5% will come. Here my 2.5% will come. Now, understand one thing very important over here. Now, let's say that 30, I got 30 over here. So, this is my 30, right? And I have also defined my confidence interval from this point to this point. Whenever we are coming inside this, then we say that the coin is fair. Why? Because understand, it is within this interval. Here we need to define, because we don't know, right? What should be the number? You said that when I got head 30 times, many people is saying that not fair. But who are we to decide? Domain expert will decide. And how will he decide? With the help of this significance value. Suppose they say significance value is 0.05. That basically means that the experiment, if it falls in this 95% confidence interval, that time I will say that that coin is fair. If it falls outside this confidence interval, that time I will say that the coin is not fair. Now tell me, let's say that this number that you are seeing is 20, let's say, and this number that you are seeing is 75. 20 to 75 is my confidence interval. Now I perform the experiment. If I get 10 heads only out of 100 experiments, should we accept or reject the null hypothesis? The null hypothesis is basically the coin is fair. The null alternate hypothesis, coin is unfair. So if I get 10 heads, which region it is falling? It will fall somewhere here. It is not inside the confidence interval. So we can definitely say that coin is not fair. So for that particular case, we reject the null hypothesis and we accept the alternate hypothesis. I hope everybody is able to understand the terminologies that we are using over here. I cannot teach you separate topics. Understand, I have to combine these topics together to teach you how to do it. What if we have, okay, let's say that. Guys, if you have 95 heads in those 100 experiments, which region it will fall? Will it not fall in this region? 95 is somewhere here. So should we accept the null hypothesis or reject the null hypothesis? We have to obviously reject the null hypothesis. and alternate hypothesis will be accepted. It's very simple. I perform the experiment, whatever value I get, I go and check in this. Okay, let me tell you now one more scenario. Okay, here let's say that my domain expertise said that Krish, you are a fool, and probably I will now use this is 50, 60, 70, 80, 90. Okay, let's say that Krish, you are a fool. Why have you taken alpha 0.05? Okay, I don't want that. Huh? So let's say that your alpha is 0.20. Now, what will be your confidence interval? What will be your confidence interval? Let's say that your confidence interval will be now 80% instead of 95%. So now your graph will look somewhere here like this. It will be still more in this side. So this side will basically have 0.10, this side will basically have 0.10, and this all will be your 0.80%. When you combine all this, when you add up all this, it will be 1. So at that point of time, then you can go and find out your confidence interval. This value will give you your lower confidence interval. This value will be giving you a higher confidence interval. You perform the experiment. Now just imagine you got 25 from that experiment, whether you should reject or accept it. Tell me one thing. If your alpha value is 0.3, what is your confidence interval? Vishweshwaram, I just took it for heads only, right? So what is your confidence interval if your alpha value is 0.3? Obviously, you'll say that it is 0.7, that is 70% confidence interval. So alpha, significance value and confidence interval are reverse, right? You need to calculate in that specific way, right? Now, usually when we say like p value, right? Suppose if it does not follows in the confidence interval, I may say that the p value is less than 0.3. So because of that, I have to reject the null hypothesis. Hello guys. Today topics, what all things we are going to see is that the first thing that we are going to check out is something called as type 1, type 2 error. So the first topic that we are going to see is something like type 1 and type 2 error. Very super important. Probably in machine learning, you'll be discussing about, confusion matrix. Fine guys, if it is not uploaded, don't worry, it will get uploaded today. Okay, I will say the backend team to do it. The second thing that we are probably going to discuss about after after type 1 and type 2 error is basically your one-tailed and two-tailed test. The third topic that we are going to see is that how to find out confidence interval. Okay, that is what we are going to see. Now, confidence interval, how to calculate this. Probably when an alpha value is given, I told you we need to define some confidence interval in order to solve some problems. The fourth topic that we will try to see after confidence interval is something called as Z test, T test, and if we get time, we will also finish up chi-square test. So let's start. The first topic that we are probably going to discuss about is something called as type 1 and type 2 error. Always understand whenever we do any kind of hypothesis testing, one very important thing I told you that what we have. The first topic that we are probably going to discuss about is type 1 and type 2 error. Type 1 and type 2 error. Always understand in any kind of hypothesis testing, right? We do have something called as null hypothesis. Null hypothesis is usually denoted by H0. We have something called as alternate hypothesis. Okay, alternate hypothesis, which is denoted by H1. Okay. Now, at the end of the day, after performing any kind of experiments, right? Let's say that I'm performing an experiment where to check whether the coin is fair or not. I'll take the same example what we have discussed yesterday, and coin is not fair. I will probably go and check whether it falls within the confidence interval. I'll check the significance value. Based on that, the confidence interval will be defined. Everything we will do, and that is what I explained in the yesterday's part. Now, from this, after we perform the experiment, there are two types of decisions that can be made. First of all, we'll go with respect to the reality check. So the reality check will be that either null hypothesis will be true, null hypothesis is true, or null hypothesis is false, right? Only these two things we will be able to see in reality check, right? If I go and check with respect to the decision, because this is what I am actually trying to test, right? In decision, I may either get null hypothesis as true, null hypothesis is true, or null hypothesis is false. When null hypothesis is false, I will say that alternate hypothesis is accepted, right? Or we reject the null hypothesis. Now, from this two, what you can basically derive is that, see this, very important. First outcome, let's say, what may be the possible outcome? Okay, so what may be the possible outcome? So outcome one, I will say that, okay, outcome one is that we reject the null hypothesis. Reject the null hypothesis, that is my decision, when in reality it is false. Is this a good decision? Yes. We reject the null hypothesis when in reality it is false. Is this a good decision? Yes, it is obviously a very good decision. This is how we should take a decision. Now, when in reality, when I say that in reality it is false, obviously we are rejecting the null hypothesis. Okay, very good decision. Now, the second outcome, let's go ahead and discuss the second outcome. Now, suppose I write the outcome 2. What are the possible outcomes? I'm just trying to show you. Okay, we reject the null hypothesis. We reject the null hypothesis when in reality it is true. So over here, what should be your decision? Whether this is a good decision or not. Again, I have to note at this particular point, when in reality it is true. If we are rejecting the null hypothesis, is this a correct decision or not? Over here in this particular case, obviously many people will say that it is a bad decision. So here I will say no. And this kind of decisions is specifically called as type 1 error. So this decision is basically called as type 1 error, right? So this decision, when we are rejecting the null hypothesis, when in reality it is true. Let's say that I take my null hypothesis as the person is innocent, and my alternate hypothesis is person is not innocent. Now in this particular case, the person, we are just acquitting him. In movies you have seen, right? Many people will just be awarded death sentence even though they have not done anything wrong. So that kind of example is what you are actually seeing over here. We reject the null hypothesis when in reality it is true. That basically means the person is awarded a death sentence even though he did not do anything. So this is a perfect example. You have seen in movies, right? In movies, okay? You'll be seeing that a person will be awarded a death sentence even though he did not do anything. In the case of a fake case. So at that point of time, this person is not innocent, but in reality, he is innocent. So this becomes a perfect example of type 1 error. Outcome 3. Outcome 3 basically says that this is also a very important outcome. And this all things you will be able to relate in confusion matrix. I don't know how many people knows about confusion matrix. So we retain the null hypothesis, or we accept the null hypothesis. Let's say that I'm saying we accept the null hypothesis when in reality it is false. Is this a good decision? The answer should be no. So this error is basically called as type 2 error. Only 4 outcomes will be there. 4 outcomes will definitely be there. So here you can understand that in this particular case, even though the person has committed crime, he is not acquitted. So definitely this error is basically called as type 2 error. Okay, I hope everybody's got is clear, right? Now let's go to outcome 4. Outcome 4 is that we accept the null hypothesis when in reality it is true. So this is obviously a good case, right? So here I can say that fine, this decision and this decision are perfectly fine. But whenever we have this scenarios, we basically have to consider it as type 1 and type 2 error. So I hope everybody is getting it, right? So similarly, in the real world scenario, you define something called as confusion matrix, right? In confusion matrix, what you have? You have true, positive, right? Sorry, true, false, and just a second. In confusion matrix, what you have? You have true, false, positive, negative, right? So here you are basically defining your true positive, true negative, false positive, false negative, right? So this basically becomes your true positive, true negative, false positive, false negative. Tell me out of this which is type 1 and type 2 error. Either this can be type 1 or type 2 error. That will be a answer for you. So you have to tell me, okay, whether false positive will be a type 1 error or true negative will be type 2 error or vice versa. Perfect. So this will be one assignment to you. If you don't know, just check out one of my video, you'll be able to see it. But clear guys, was this explanation good for type 1 and type 2 error? So we have completed this specific topic, that is type 1 and type 2 error. Perfect. So some people are basically saying false positive is type 1, true negative is FP is type 1. So here you have actually solved a very good topic which is called as type 1 and type 2 error. Now let's go to the next topic, that is one-tailed and two-tailed test. This is also very much super important. One-tail and two-tailed test. So one-tail and two-tailed test. Now let's go ahead and let's try to understand what is one-tailed and two-tailed test. Now already you have seen that I have probably drawn a curve, a bell curve, and in that I basically define a kind of one-tailed and two-tailed test. Still you have seen it, but let me give you a one good example. Okay, so the example is that a college in, let's say a college, or let me write like this, colleges in Karnataka have an 85% placement rate in the placements time. A new college was recently opened, and it was found that a sample of 150 students had a placement rate of 88% with a standard deviation 4%. Does this college have or has a different placement rate than the other colleges? Okay, so understand this question very much importantly. Oops, sorry guys, I made one mistake. This should not be type 2. False negative should be type 2, right? True positive and true negative are perfectly fine. Okay, this should be type 2. True positive and true negative are always right. Let's try to understand some very important thing. Now, what does this question basically say? Whether, see, there are colleges in Karnataka which has 85% placement rate. A new college was recently opened and it was found out that a sample of 150 students had a placement rate of 88% with a standard deviation 4%. Thus, the college has a different placement rate. Thus, this college, this basically means the new college. Now, in this particular case, first of all, think about the question. Now, over here it says, does this college has a different placement rate? What is the placement rate of the entire college? 85%. So does it have a different rate than 85%? That is what we really need to check, right? Now in this particular case, this becomes a two-tailed test. Why? We'll think over it. Let's say that here the significance value is given as 0.05. Let's consider that over here the significance value is given as 0.05. Now what we do over here is that we will try to create a graph. Now when we have 0.05, that basically means if it is a two-tailed test basically means right now I have a placement rate of 85%. So 85% is, you can just consider that 85% will be what in this particular case, right? 85% passage rate, or sorry, placement rate, right? So 85%, but we need to find out over here when alpha is given, 2.5 will be here, and this will be my 95% confidence interval. So 95 will basically be here. If I combine all these things, it will become 1. Now you need to understand whether this will become a two-tailed test or a one-tailed test. This is what is very much simple. Now this 85% will be my mean. My value can be greater than 85. It can be less than 85. Okay, it can be greater than 85. It can be less than 85 because we are just checking whether it has a different placement rate. It can be greater. It can be less also. So that is the reason this entire test becomes a two-tailed test, because the new college that gets added, it may fall in this region also, it may fall in this region. Right now, you will be able to see that we are just trying to check whether it is greater than 85 or whether it is less than 85. So this becomes a two-tailed test. Now let me just make a little bit change into the question. Now my question says that, let's say that my question, I'll just change the question saying that, does this college have a placement rate greater than 85%. Now what will this be? Greater than 85%. Think over it. What this will basically be. Yeah, what this will be. Now my question will look like this. This is my alpha value is 0.05. Obviously it is 95% confidence interval, but this is only focused in finding greater. So this entire value I'll put over here, and this region will be my 5 value. This region will be my 95% value. So this becomes one tail test, that also in the right hand side, because here the important keyword is something called as greater. So this becomes a one tail test, and remember we cannot divide this alpha value into two parts in this case. Only in one part it will be basically present. Now just think over it. If this value is lesser, then what will happen? It will come in this particular side. So I hope you are understanding what is the difference between one tail and two tail test. So always make sure that focus on the question, what the question is basically said. Here, does this college has a different placement rate? From the experiment, any experiment that I may carry on, my answer will be either greater than 85 or less than 85. So that becomes a two-tail test. In this particular case, I am saying greater than 85% with alpha value is 0.05. So I am definitely sure that I am actually checking only this region. I'm not worried at this particular region because I need to check whether it is greater than 85. This is the most important thing with respect to one tail and two tail test. Now the next thing that we are going to discuss about is, so we have finished one tail and two tail also. Now let's go ahead and understand how to find out this confidence interval. I told you, right? See, this is very much important. Confidence intervals with respect to means. I told you, right? In confidence interval, what we do? We basically have this graph. When I say my alpha value is 0.05, then this becomes a two-tailed test. Suppose I need to find this value, right? I need to find these two values. How do I find out these two values? That is what we are going to see. We are going to do some kind of calculations which will actually help me to understand. So in order to find out confidence interval, you really need to understand some things. Sir, if it asks less than 85, so it will be considered as one tail test? Yes, obviously one tail test, but in the left hand side. Okay, right now this will be in the right hand side. Now let's try to understand with respect to confidence interval. Now in order to understand confidence interval, you really need to understand a topic which is called as point estimate. Okay, so I will basically give the definition of point estimate. What exactly is point estimate? Point estimate can be defined as a value of any statistic that estimates the value of a parameter is called a point estimate. So a simple definition I have written over here. I'll define about what is this statistic and which estimates the value of a parameter. So two things, one is statistics and one is parameter. So what exactly is point estimate? A value of any statistics that estimates the value of a parameter. Now understand one thing, guys. In inferential statistics, any work that we will be doing, first of all, we will be considering a sample data. Based on this sample data, we will be estimating something for the population data, right? In this particular example, let's consider that I will try to, if I have the sample meal, I'll try to estimate the population. And usually this only things happens in inferential stats. You'll just have the sample information, probably population standard deviation you may know, but you really need to find out or estimate the population value. And as you know, like let's say that I'll give one example. This is my X bar. This X bar, we will try to estimate the value of mu bar, right? Because if I have a population with the help of sample, I can definitely estimate mu. But always remember, this value may be approximately equal to this. It may be also less, it may be also greater, right? In one case, I may say that if my X bar is 2.9 and probably my population mean is mu is equal to 3, right? This may be equal, this may be less, this may be little bit greater also. This is what point estimate is all about. So this is the point estimate which will be estimating the mu value. So in this particular case, I hope you understood what exactly is point estimate. Okay. So point estimate is the value of any statistics that estimates the value of a parameter. So through this, we are basically estimating the mean. So at least get this specific knowledge. Now, in most of the problem statement, I will be given this and I really need to estimate this. How will I be able to do this? So for that specific case, we will try to see a problem statement. And here we will use something called as confidence interval. Now understand, I told you that this value will be approximately equal to mean. It may be less than mean, it may be greater than mean. So in this particular scenario, we define something called as confidence intervals so that we will be able to come towards the population mean. So confidence interval is usually given by the formula, which is nothing but point estimate plus or minus margin of error. So there is some margin of error. There is some margin of error because over here you can see 2.9. This is obviously less. It can also be greater. So I have written plus or minus of margin of error because obviously we will not know the exact population mean, right? We don't know. So obviously the point estimate plus margin of error will actually help us to get the same mean. And this is how we determine the confidence interval. Now let's see one problem statement. By this you will basically be able to understand what I am actually saying. From this formula, you will be able to understand that how close we are near to the population mean. The second thing is that suppose if you are given the population standard deviation, at that point of time, what formula you should use to do this and how large your sample size is. So let me just solve one very simple problem and give it to you. So the problem is very simple, not that difficult at all, and we'll try to solve that specific problem. So this is my question. On the quant test of CAT exam. I hope everybody knows CAT exam. On the quant test of CAT exam, the population standard deviation, the standard deviation is known to be 100. Now, the next thing is that I will take a sample of 25 test takers. 25 test takers has a mean of 520 score. So here my question is that construct a 95% confidence interval about the mean. Now let's see what all information is given. Over here, you know that some information is definitely given, you know that, right? So first information, what is given? Over here, you know your population standard deviation is given. What is your population standard deviation? Here you can see that it is 100. 100 is your population standard. What is your small n size? It is nothing but 25. What is your confidence interval? With respect to this alpha, I will get 0.05. And what is your mean? What is your mean over here? Mean is nothing but x bar, which is nothing but 520. Is this information given in the question? Is this information given in the question? Is this information given in the question? Obviously it is given, right? Now my graph looks something like this. See this. My graph is looking like this. My mean is basically, what is my mean? My mean is nothing but 520. Now my alpha value is 0.05. So here I have 2.5, here I have 2. And this is my 95% confidence interval. Now I need to find out what this value, what this range is basically. If I say that I want to construct a 95 confidence interval about the mean, what is this value? What value from here to here it will range? That is what I need to find out. So this is what is my problem statement. I've also given the standard deviation. Now here, whenever population standard, first thing, whenever population standard deviation is given, guys, why 90 alpha is 0.05? See, I've given the question as 95% confidence interval, right? So it is nothing but 1 minus 0.95, which is nothing but 0.05. So this will be my alpha value, right? Alpha and confidence interval are interlinked. Very simple. Now, when population standard deviation is basically given, we apply a test, right? What kind of test? Now here I know that this will be my point estimate plus or minus margin of error. This is for my confidence interval formula. Now point estimate is obviously your x bar. Now plus or minus, whenever you have this population standard deviation, you apply a z test. So here you will write z alpha by 2 and the formula will be standard deviation divided by root n. Now this is your formula. This term, I'll talk about this term. This term that you see is called as standard error. So in this particular case, one more second point is that when we should use this formula to find out the confidence interval. Next thing is that over here you will be able to see that I have taken a sample of 25, but usually the sample size will be greater than or equal to 30. But just for an example, I have taken as 25. Okay, so it's okay. Now don't fight with me, Krish, why I have taken 25. Take it 30 also, we have to do the calculation. But these two conditions suits well for this kind of problem statement. Okay, so for a z test to happen, most of the time this two condition needs to be approved. Now this z test is nothing but z score. Okay, z score to find out the z score. That is what z test is basically used. Now understand over here what this alpha is. Okay, so this is the entire formula to find out the confidence interval if your population standard deviation is given and when your sample size is greater than or equal to 30. Now let's go and solve this particular problem. Now when I go and solve this particular problem, the first thing is that I will split this equation into two parts. One is I will get one higher confidence interval. Alpha value is 0.05 divided by 2. Standard deviation is, what is standard deviation over here? It is nothing but 100 divided by root 25. Now you understood why I have taken 25, because my calculation will become easier. Don't fight with me, guys. I don't have energy to fight. Nowadays I fight with a lot of people. So this will basically be my upper bound of confidence interval. Similarly, lower bound of confidence interval, I'll try to find out. That is x bar minus z 0.05 divided by 2, 100 divided by root 25. Now here I will write 0.05 by 2 is nothing but z is nothing but 0.025. I hope everybody is getting this. Now how do I find out this particular value? For this, go and open your browser and open z table. So if I go and open z table, let me just open a z table, another z table I'll try to open, just a second. Point here, all minus are basically shown. So I'll not use this z table, wait. I'll use the other one because there are only negative values given. Here probably I'll be able to find out. Okay. Now in z table, always understand over here when I say 0.025, okay, my entire area is how much? So my entire area is 1. If I subtract 1 with 0.025, that basically means this part. The entire area will become 0.975. So 0.975 I have to check in the z table. So for this, what I will do is that I will go to my browser and go and check it. Where is 0.975? 0.975 is nothing but this specific area. Go and check this 0.975. I hope you are able to see this. So what is this value? 1.9. And if I go on top, it is 0.06. That basically means the z value is 1.96. So go down over here, you will be able to see 0.9750. It is nothing but 1.9 and this is 0.06. So this becomes my z score. So finally I get my value as 1.96. Now go and calculate it. So what is my x bar? For the upper bound, I will say my x bar is nothing but, what is the mean of the sample? It is nothing but 520. Okay, so it is 520 plus 1.96 multiplied by 20. Similarly, the lower bound, it is nothing but 520 minus 1.96 multiplied by 20. Now go ahead and compute this. 559.2, 480.8. So this is my lower bound and upper bound. That basically means whenever I am defining my confidence interval for this distribution with alpha is 0.05 and this value will be 559.2 and this value will be 480.8 and my mean will basically be 520, right? So one stats interview question that I told, right? Find the average size of the sharks throughout the world. Can you solve this by taking your own example? Because one of my student solved this particular problem and he gave some confidence interval. He said that let's assume this and try to solve in this particular way. He said that, okay, let's consider, oh, there the interviewer said, you know the population standard deviation, you know the x bar value, you know the n value. Try to solve it with alpha as 0.05. Ayush Nautiyal understand that over here, when my alpha value is 0.025, I am just worried about one tail, right? This side. This entire area is 1. So 1 minus 0.025 is 0.975. Now, after performing any experiment, if my value falls between these two, at that point of time, I will assume that it is, we need to accept the null hypothesis and we can go ahead with it. If it does not fall within this range, then it is going to fall away from the hypothesis. But basically, we need to reject the null hypothesis. Now, the next question that we are probably going to see is that what if the population standard deviation is not given? Now, in that particular scenario, what will you do? For that particular case, you really need to use something called as t-test. So let me just show you one very good example, and that also will try to solve. Let's say that the same question, this standard deviation is not given. Standard deviation is not given. Population standard deviation is not given, but sample standard deviation is given. So I'll write down the question over here for you, but I hope you are able to understand it. So the question is that on the quant test of CAT exam, on the quant test of a CAT exam, a sample of 25 test takers has a mean of 520 score with a standard deviation. Now, this standard deviation that is given is basically your sample standard deviation. Has a standard deviation of 80. Construct 95% confidence interval about the mean. So this is basically my question, right? So this is my question. So over here you can see that population standard deviation is not given. So in this particular case, I definitely have to use Z test. So over here, sorry, T test. Condition I'll write, okay? First of all, we'll try to see what all things are given. Your n value is given, which is 25. Your x bar is given, which is nothing but 520, right? Your sample standard deviation is given, that is 80, and your alpha is 0.05. So when you see over here, your values have not been given over here. That basically means your, the conditions, I'll not say conditions, but here your population standard deviation is not given. So I can write a condition saying that here population standard deviation is not given. So in this particular case, we use something called as t-test. If population standard deviation given, at that point of time, you use t-test. Let's go and try to compute it. Here also the same formula will be used. Point estimate plus or minus margin of error. Here your margin of error formula will change. Okay. Now what kind of formula it will have, that you need to understand. The formula will be something like x bar plus or minus, instead of writing z alpha by 2, here you will be writing t alpha by 2, and then you will be using s by root n. This is your standard error. Now go and substitute it. So two things you will be basically having. One is upper bound. It will be x bar plus t 0.05 by 2 s by root n, right? Now first thing first, always understand to calculate the t. Okay, to calculate the t value, you need to find out something called a degree of freedom, because in the t table you will be asked this. And degree of freedom formula is just like your sample variance problem, that is n minus 1, which we also use with respect to Basel correction. So this will be 25 minus 1, which is nothing but 24. Now I will go to my browser. I will open over here t table. So t table I am having here. Now first thing first, you need to understand with respect to degree of freedom. What is degree of freedom? 24. Degree of freedom is 24, 25. Let's see this. This is 24, right? I hope everybody is able to see the degree of freedom over here. Try to have a look onto this table. 0.025. 0.025 is nothing but this one, right? This is what? 0.975. So if I see with respect to 24, it is nothing but 2.064. Is everybody getting it? We have to see in this line 24 degree of freedom on the left hand side. On the right hand side, you can see on top it is 0.025, 0.05. So the answer is 2.06, 2.064. So here I'm basically going to find your t 0.05 divided by 2 is equal to nothing but 2.064. Now the next step, once you get this, I will go and see what is my x bar. 520. 520 plus 2.064 multiplied by s. What is s over here? It is nothing but 80 by 5. 5 is nothing but root 25 is 5. 553.024. And then if I go and compute the lower bound, 520 minus 2.064, 80 by 5. So this minus 520. So here I'm actually getting 486.97. So my lower bound is nothing but 486.97. The upper bound of the confidence interval is nothing but 553.02. So with this, we have done, wow, I've written so much today. We have finished confidence interval. Congratulations, everybody. We have successfully completed. Congrats. Why this is not two tail? This is two tail only, no? I told you, no, this is two tail. Why are you getting confused? See over here. If I see over here 0.025 for one tail, for two tail, this is 0.05. Now let's go ahead and try to do the first Z test. I hope everybody has understood why do we use Z test. So the first question that we are going to solve is one sample Z test. Now we will perform hypothesis testing. So the first problem that we are going to solve is one sample Z test. Now we are going to perform hypothesis testing. What exactly is one sample Z test? First of all, I told you two conditions with respect to Z test. The first condition is that the population standard deviation is given. At that time, you use Z test. The second thing is that your sample size should be have a size at least n is greater than or equal to 30. Just to make calculation easier, I just put it at n is equal to 25 because root of 25 was 5. So because of that, I put it. Don't fight with me. I have no energy. I think you'll beat me and go, but I don't have any energy. Okay. So let's go ahead and let's try to see how to do a hypothesis testing. Okay. Let's say that I'm writing a problem statement in the population, the average IQ with a standard deviation of 15. Okay. Researchers wants to test a new medication to see if there is positive or negative effect on intelligence or no effect at all. A sample of 30 participants who have taken the medication has a mean IQ of 140. Did the medication the intelligence? Just by reading the question, what do you get it from it, guys? Did the medication improve the intelligence or not? Now I'll show you how to perform a hypothesis testing. Okay. Obviously, you got to know that what test it is used. Okay. So let's go ahead and discuss it. Now, first of all, how to perform a hypothesis testing. Okay. So, the first step is that we need to define the null hypothesis. Now, in this particular case, null hypothesis is S0. Now, in S0, what you will basically say that your mean is nothing but 100. Can I say your mean is 100? Because see, obviously we need to check whether the medication affect the intelligence or not. So here I'll say that my null hypothesis will be that my mean IQ is 100. My alternate will be that my mean is not equal to 100. I hope everybody is agreeing with this. Everybody is agreeing with this clearly, right? So over here H0 is equal to mean is equal to 100. Okay, so this basically says that it is your null hypothesis. The second thing is that we need to define our alternate hypothesis. My alternate hypothesis is S0 where my mean is not equal to 100. My mean is not equal to 100 because if I am saying my null hypothesis and the mean is equal to 100, then this will not equal to 100. One important thing that I forgot to mention, my alpha over here will be 0.05. That basically means my confidence interval is 95%. So this is also a part of the question. Now the third step, let's go to the third step. Okay, mean is not 140, mean is 100. Sample mean is 140. You can apply in any concept, guys. It need not be that you can only apply in something. Okay. The third step, we basically state our alpha value. So my alpha value is 0.05. The fourth step, let's go to the fourth step now. What do you think the fourth step is? In the fourth step, I need to provide my decision rule. So here I will say state decision rule. And always understand in the decision rule, you need to specify this graph. And here you will basically say that since my alpha is 0.05, what kind of test this will be? Did the medication affect the intelligence? The question, understand this question. Did the medication affect the intelligence? So here we are just focusing on that whether the medication increased your intelligence or whether it decreased your intelligence. Okay. So either it can be. So this definitely will become a two-tailed test. So two-tailed test. So here I will be having 2.5, here I will be having 2.5. So this will be 2.5, this will be 2.5 and this will be 95%. Right? Everybody is clear with this? Can I get a quick yes? Right? This will definitely become a two-tailed test. And one more important thing over here, when I say 2.5, then if I really want to find out with the help of Z test, what will be this value? I have to check it for 1 minus 0.025, right? So this will be 0.975. In this particular value, I need to check in my Z table. So I need to find out this value and this value, right? Go ahead and check it. What will be the value over here? This will be plus 1.96. This will be minus 1.96. We just checked it, right? We just checked it over here. You can see over here, right? Where did it go? Here we got this. This was for T, right? This was for Z. For Z we got this, right? 1.96. See this? We got 1.96. Okay. So 1.96 plus minus 1.9. Now I know my decision rule. My whatever experiment I will perform later on, whatever Z score value I will be getting, I should be getting within this minus 1.96 to plus 1.96. Now here I will use my test statistics. Now what will be my test statistics over here? It's very simple. What is the Z score formula we basically use? Calculate test statistics. And this will be T test, right? So the formula that we basically use, Z test. I'm extremely sorry. This will be Z test, not T test. Z test. Calculate Z. What is the formula that we basically use? X minus mu divided by standard deviation. I hope everybody remembers this formula, right? But understand one thing. The real formula of Z square is, Z test is this divided by root n. The reason why we did not consider before root n, understand for every sample my n value will be 1. So whenever I write root of 1, it will be 1, right? But when we are working with a huge sample, right? When we are working with a huge sample, we have to basically use root n. And this is called as standard error. Standard error. Like how we divide something by, n minus 1. there is some reasons why we do it, okay? And probably I don't know whether you have seen my video or not, okay? So this is basically called as standard error. So we have to divide by root n. Always understand, for one sample, this root n will already be 1. So we have to use this particular formula, okay, to do this. Okay, so this is basically my standard error formula, which is specified by this. And always remember, because why do we use this? I'll just give you one example. Suppose I take 5 samples, right? I take 5 samples, 5 different samples from a population. Five samples from different. Let's say that I have a population of 1000 points. Okay. Let's say that I have a population of 1000 points. 1000 points. Let's consider that I am considering a sample of 100 points. Every time I take, otherwise just wait for it, guys. I will teach you. There is a topic which is called as central limit theorem. I will discuss that and then probably I'll teach you this particular topic. But just right now understand that to make our standard error become very less, because here we are working with sample data. If we are working with population data, directly we can write standard deviation like this. But since we are working with sample data, we have some kind of standard error, and by dividing it by root n, as the sample size keeps on increasing, our values, our mean values will be matching with the population. So don't worry, just give some time and I will explain you this. For right now, just consider that it is standard deviation divided by root n. If I go ahead and calculate this particular thing, so what is my x bar? My x bar is obviously what? Let's see. What is my mean? A sample of 30 participation is nothing but 140. Okay, so 140 minus, what is the population mean? IQ, the average IQ is 100. So here I will say 100. Divided by what is standard deviation? Population standard deviation with a standard deviation of 15. So here I have 15. Divided by root n. What is n? What is the sample that we have taken? 30. So here it will be root of 30. So this will basically be 40 divided by 15 multiplied by root 30. I hope I'm right. It is 14.60. Finally, we state our decision. Now, this is a very important step, because from this particular step, I will be able to understand something. I got from my Z test 14.60. Now, let's go and see our decision rule. What did our decision rule basically say? It should be between minus 1.96 to plus 1.96. Is this greater than 1.96 or not? So 14.96 over here, 14.60 is greater than 1.96, which is obviously that my condition will be that if Z is less than minus 1.96 or greater than 1.96, then what we have to do? We have to just reject the null hypothesis, because my Z value over here is 14.60. But let's take out one amazing thing from this. So when I reject my null hypothesis, that basically means my mean is not equal to 100, right? I'm accepting this. Now tell me one very important question. Does this medication improve the intelligence or did it decrease the intelligence? My next question is that, did the medication improve the intelligence or decrease? Now this you have to answer me after solving this much. Obviously it is improved. Improved, guys. Improved the intelligence, not decreased. Improved the intelligence. Very simple. If I was getting the Z value as minus 0.2, that time what was happening? Then what would happen? It would have decreased the intelligence. It has increased the intelligence. Rejecting the null hypothesis is saying that the medicine had an impact. Now do the same problem. I will just change one value over here. This mean will be 110. This mean of this 30 participants will be 110. Try to solve the problem and tell me whether the null hypothesis is accepted or the alternate hypothesis, whether the null hypothesis is accepted or rejected. Okay, so do this from your side. So do the problem statement. So we will start our second test, which is called as one sample t test. Now, I hope you like the session. So, guys, see, I like to teach in this particular way, right? Like write everything. I never prepare PPTs. Probably you have seen my YouTube videos. Hardly I prepare any kind of PPTs. I write it like this. The reason I write it like this because it also helps me to practice. It also helps me to see that what mistakes I'm probably making, I'll become perfect in this. So tomorrow, if you call me in any session, Krish, probably teach statistics or machine learning, I will just go and start explaining everything over here. Now let's go towards the next problem statement, which is called as one sample t-test. Now I hope you understood what is t-test, right? First of all, let me say z-test. Whenever you have population standard deviation, you use this, right? You really need to remember this. If you don't have population standard deviation, that is an unknown case of population standard deviation, then what you do? You use t-test. Okay, so this is the basic difference between t-test and all. Okay, now I'll take the same problem. Okay, so let's solve the same question. Okay, first of all, in a population, the average IQ is equal to 100. Then a team of researchers tried a medication to see whether there is a positive or negative effect. A sample of 30 participants were taken and they have a mean IQ of 140 with a sample standard deviation of 20. So did the medication affect the intelligence? The first thing first, answer. What is your null hypothesis? Your mean is equal to 100. What is your H1? Mean is not equal to 100. The first step, the second step is done. Now the third step that we do in t-test, which I have discussed before also, calculate the degree of freedom. Here I basically use n minus 1. So this will be 30 minus 1, which is nothing but 29. Fourth step. What is my fourth step? I will go ahead with the decision rule. Now my decision rule is nothing but, it's very, very simple. I will go and define this graph. I know what is my alpha value, 0.05. I know my question. Did the medication affect the intelligence? It can either increase or decrease. So it will become a two-tailed test. So here you have 2.5. Here you have 2.5. Here is your 95. What is this value? We have probably found it out with degree of freedom 29. So let's go and try to find out with degree of freedom 29 what will be the value. So it is T table, degree of freedom 29. So 2.045. So 2.045. So here you will be able to see plus 2.0. What was that? 2.045. Sorry. And minus 2.045. Right? So this is your decision rule. Now your t value that you should be getting should be between this. If it is greater or lesser than this, you reject the null hypothesis. That is what you have to probably do. Finally, we go to the test statistics formula of t-test. The formula will be almost same. T is equal to x bar minus mu divided by population standard deviation is not given, sample is given, and this will be root n. So try to compute the values, guys. X bar is nothing but 140, mu is nothing but 100, s is nothing but 20, n is nothing but 30. So compute it. So if I try to do the calculation entirely, this entire answer will be 10.96. Now since we have got 10.96, it is obviously greater than 2.05. So the t value, which is nothing but 10.96, is greater than 2.045, and it is also greater than this particular value. So what we do, we reject null hypothesis. Now when we reject null hypothesis, that basically means my p value is less than or equal to the significance value. That is, I am falling in this region or in this region. Now, if since I am getting 10.96, what do you think whether my intelligence increased or not? So obviously, final conclusion, you can see that it has increased the intelligence. So what you do? You reject the null hypothesis, accept the null hypothesis. Sorry, reject the null hypothesis, accept the alternate. So from my teaching, did your IQ increased or not? Now let's see a real world problem. And probably you can do this from yourself. A bank wants to open an ATM machine in a specific area. So this problem you have to formulate and you have to think over it, how we can apply hypothesis testing. You can consider any values that you want. Like you can say that average money people take out from the ATM machine with 95% confidence interval. You can formulate, because this was one interview question in one bank that is called as Standard Chartered. Interview question from there. Think over it. What all things basically required, right? Think over it and try to solve it. Okay. Hello, guys. I hope you're doing fine. Today, first of all, we will continue with the discussion where we left. So, we will solve a chi-square problem. The second thing that I forgot about some of the topics over here is with respect to covariance, correlation, Pearson correlation coefficient. And the fourth topic that we are going to see is nothing but Spearman rank correlation coefficient. Spearman rank correlation coefficient, we are going to discuss about this. Then probably we are also going to see practical implementations. Okay, so we are also going to check out some practical implementation things. Now in this practical implementation, we will try to perform Z test, T test, and probably also see how to perform chi-square test. This topic, we will also see F test, which is the last topic, which is also called as ANOVA test. The reason why I've kept F test as last, because the calculation will be the calculation is quite complex in that particular case. So now let's go ahead and let's try to discuss about the chi-square test. Chi-square test has quite amazing problem statement. So if I really want to discuss about chi-square test, it is mostly I'll talk about it, okay, right now. So let me just define what is exactly chi-square test. The chi-square test claims about population proportions. That basically means if someone asks you, Krish, okay, someone asks you in the interview, why is chi-square test used at? Why it is used? You can just say that it is a non-parametric test that is performed on categorical variables. Categorical, it can be nominal or ordinal data. So this is how you basically define a chi-square test. So it is a non-parametric test that is performed on categorical or ordinal data. So this is what chi-square test is basically used. So if probably they ask you in the interview, make sure that you are basically understanding why a specific test is actually done. This is very, very important, okay? Because in the interview, they may give you a problem statement and they may ask you what will be your plan to solve that specific problem statement. But with respect to definition, you should definitely be able to tell them. Let's go ahead and let's solve a specific problem. For solving this specific problem, I am just going to take a chi-square test problem. Okay. Let's say that I'll take a very good example. So this is my question. In 2000 Indian census, the ages of the ages of the individual in a small town in the small town were found to be the following. Now over here you have three categories: less than 18 years, 18 to 35 years, and greater than 35 years. So you had this information in the 2000 census. That basically means less than 18 years were basically 20%, 18 to 35 were somewhere around 30%, and greater than 35 was somewhere around 50%. Okay, so this is the information that is given from the complete census. Considering this, In 2010, ages of sample n is equal to 500 individuals were sampled. Below are the results. So we basically have three columns again. That basically means in 2010, again, they took a sample of 500 people and they found out this was the basic results. Let's see. So out of those 500, less than 18, 18 to 35, and greater than 35. So less than 18 were 121 people, 18 to 35 were 288 people, and this was 91 people. So the question is, using alpha as 0.05, would you conclude the population distribution of ages has changed in the last 10 years? So this is the question that is basically given to you. The question is very much simple. It is saying that in 2000 census, in 2000 census, the Indian census, the age of the individual in a small town were less than. This is basically the data. This is the population information. Like less than 18% were 20%, 18 to 35 were basically 30 percentage, and greater than 35 was 50 percentage. Okay. Then in 2010, the ages of n is equal to 500 individuals were sampled. Below are the results. Then in 2010, what happened is that, you know, this again they again found out by picking up 500 people as a sample data, and they found out that less than 18 were 121 people, 18 to 35 were 288 people, and greater than 35 were 91 people. So using alpha is equal to 0.05, would you conclude the population distribution has changed in the last 10 years? Now, what we are going to do over here is that we are basically going to solve this particular problem. Now, you may be thinking that, Krish, you have told that it is a non-parametric test that is performed on categorical, that is nominal or ordinal data. Now, what exactly is non-parametric test? Non-parametric test usually occurs with respect to population proportion. Whenever you are given some kind of proportions of data, at that point of time, you cannot specifically use a kind of parametric test. So you have to go with non-parametric test. Now, here you can actually see that when this is the original data with respect to the population, then you sample the data and you found it out, right? And then we are just trying to see that what is the difference between this to this to this. Do you think the population may have probably changed just by seeing the specific data, or still you will probably just say that, yeah sir, it may be population has changed, probably 18 to 35 you can see a huge quantity or number, greater than 35 just seeing the percentage it shows a very less number. Obviously from the above population proportion you should be saying that greater than 35 should be more. In this particular scenario, what kind of assumptions we can make? There is two kind of assumptions, whether the population distribution has changed or whether it has not. So how to go ahead and approach and solve this particular problem? So here I am going to basically start the answer. So the first step, what we are going to do as usual, you can let's go ahead and let's make two tables first of all. So this is my first table, this is my second table, because this table will play a very important role, guys. Okay, the first table basically have the population information. So I'm just going to draw it over here. Here I'm going to basically say less than, this is less than 18, 18 to 35, and greater than 35. Now this is the expected. See why I'm saying expected, because this is the population information. This is the population information. So here less than 18 is 20%, this is 30%, and this is 50%. Now this is what your entire distribution is expected to be, because in 2000 US Census they found out this data. Now, right now after 10 years when they took the sample of n is equal to 500, this is the observed one. So the observed one was less than 18 was 121, 18 to 35 was 288, and greater than 35 were 91. So this two information you definitely have. The reason why I'm drawing this two or writing this two information, okay, we will be able to understand it. Now we will create one more table, and the table is something called as expect based. This is the observed one, right? Now what I'll do, I'll create one more field, and let's say based on this, suppose if I take n is equal to 500, based on this, what should be our expected? What should be our expected distribution based on this data? If I'm picking up 500, so we will try to divide this based on this percentage, right? So here my value will be 500 multiplied by what is 20% is less than 18. So I will multiply by 0.2. Here I will say 500 multiplied by 0.3. Here I will say 500 multiplied by 0.5. So this should be my expected distribution based on 2000 census. Observed is this one, that is fine. But we really need to find out our expected also. So if I multiply this two, so if I multiply 500 multiplied by 0.2, this is basically 100. So here I'm basically going to write 100. This will be how much? This will be 150. And this will be 250. This was what was the distribution I needed to have based on the 500 data, based on this 2000 census. But this is what is observed. So now let's go and focus on this two table right now. Okay, so we have got 100, 150, 250. Obviously, there is a huge difference. By seeing this only, you will be able to say that, okay, Krish, there is a huge difference. Here only I can definitely say that, okay, just reject the null hypothesis. But understand over here, alpha is basically given. I want 95% confidence interval. Why multiplied? Again, understand why multiplied. Because we need to find the expected distribution based on this data from this 500 sample. So if I consider 500 sample in 2010 also, I need to get this data 100, 150, 250. So I'm basically going to say this is my observation and this is my expected. So this here has less than 18, 18 to 35 and greater than 35. So less than 18 is how much? I have basically 121, 288, 91. This is the observation. And then I have 100, 150 and 250. Now these are my three categories. This is one category, this is two category and this is the third category. Now let's go ahead and let's try to understand what is the next step. Now next step, I will first of all, obviously you have to define your null hypothesis, alternate hypothesis when you start the hypothesis testing. So let's say that my null hypothesis is that the data meets the distribution. This is the data, right? This is the data, observation data. It meets the distribution of 2010 census. Of 2000 census. My alternate hypothesis will say that the data does not meet the distribution of 2000 census. So I hope everybody is able to understand the null hypothesis and the alternate hypothesis. Then the second step is my alpha value. My alpha is 0.05. That basically means 95% confidence interval. Now, the third step in this is that whenever we do a chi-square test, we also need to know the degree of freedom. So how do we calculate degree of freedom? This is the steps, guys. And always this will be like this only. N minus 1. What is n over here? N is nothing but this is 1, 2 and 3. This is where number of categories are coming into picture. 1, 2 and 3. So 3 minus 1 is basically 2. Age is now categorical, right? Absolutely perfectly fine. You know your degree of freedom. Your degree of freedom is 2 and your alpha value is 0.05. All you have to do is that go and check in the chi-square table, okay, to find out your decision boundary. Is this a one-tailed test or two-tailed test? The data may be less than your distribution, it may be more, right? So here is this a two-tailed test because alpha is 0.05. Guys, we have to pick 3 as n because there are 3 age categories. So this will become a two-tailed test. Now in two-tailed test, all I have to do is that open a chi-square table. Let's see. Now this is my chi-square table. Hope so I get the answer quickly. So df is 2. Or to look upon an area on the left, subtract it from the 1, 0.05. See, 0.05 is here and degree of freedom is here. So this becomes 5.991. So over here, we usually mention chi-square by x square. And chi-square is basically denoted by x square. And my decision boundary is that if chi-square is greater than 5.99, I have to reject H0. Now let's go and compute the chi-square test as usual. Very simple definition. So my definition will be that fifth is calculate the test statistics, which is called as chi-square test. This is nothing but x square is equal to summation of f0 minus fe whole square divided by fe. Again, notation can be used in all different ways, but let me talk about what is f0. F0 basically means observed, okay, observed. Fe basically means expected. So I am going to do the summation of all these three values. So here I will first of all write 121 is my first observed value. See, 121, 100. So 121 minus 100 whole square divided by 100. Then if I go to the second element, over here you can see 288 minus 150 divided by 150. So 288 minus 150 divided by 150. Okay, whole square. Then third one will be 91 minus 250 whole square divided by 250. So this will be 91 minus 250 whole square divided by 250. 232.94. That basically means my x square is 232.94, which is obviously greater than 5.99. So what we have to do? We have to reject the null hypothesis, and which is absolutely true because the population distribution has changed. So 232 is greater than 5.99, so we are rejecting the null hypothesis. Okay, it is 494. Huh? Okay, let me write 494. So if you want to define chi-square, it claims about population proportion. You can just say that it is a non-parametric test that is performed on categorical, nominal or ordinal data. It is specifically applied on nominal or categorical data. Okay, let's see one Python example. Okay, so I'm just opening this. Okay, let's say that in my I want to perform z test. Okay, so let's say that I have some values like this. So this is my question. Suppose the IQ in certain population is normally distributed with a mean of mu is equal to 100 and standard deviation of 15. A researcher wants to know if a new drug affects IQ level, so he recruits 20 patients to try it and record their IQ level. Now I'm going to show you the code in Python to determine if the new drugs causes a significant effect or not. So I'm just going to execute this. And let's say that I have this 20 records. For z-test, we use this library, which is called as statmodels.stats.weightstats. Import z-test as z-test. So these are my 20 patients, and I have recorded their IQ after the medication is basically applied. Now, in order to apply z-test, no need to do that much calculation. Just write z-test, and here just give the data, and the next parameter that you will probably be giving is this IQ, that is 100. Okay, which you are actually trying to compare to basically reject or null hypothesis or not. In this, the null hypothesis will be mean is equal to 100, mean is not equal to 100. Now when you execute this, now here let's consider that I think the library is not there, or tuple index, what is the problem? Value is equal to 100 I have to write. So here let's consider that my alpha value is, see, let's see this. These are the two values that I'm getting. The first value is the z-test value. The second value is the p value. What does this p value basically mean? Now many people were asking the difference between significance and p value. In z-test, they try to give us some kind of p value. Here they also give the z-test value. The z score that you are able to see is here. And this p value. This p value can be used along with significance value. And suppose right now the p value is 0.001. Let's say that 0.11. This 0.11, suppose if it is less than significance level. Now in this particular case, let's consider that I'm going to take a significance level of 0.05. So if this is less than this, then obviously this we reject the null hypothesis. This is just saying that based on this p value, it is basically falling in this region. So that is the region it is less than 0.05. So it obviously gives two value. Here, just for understanding purpose, we can definitely use this value and try to do the remaining calculations if you want, because this is my real z-test value. Other than that, this value will basically help you to compare with the p value and then decide whether it has got rejected or not. So I can give you the entire code in the Okay, since it is 0.11, this is less than 0.05, we are going to reject it. Suppose if we get 0.005, let's say that in this particular case, I am going to use the mean as 110. Now you see I am getting 0.002. So do we reject or accept the null hypothesis? Here in this particular case, if I go and probably see, you will be able to see I am getting 0.0002. 0.002, which is obviously less than 0.05. So we accept the null hypothesis. This is obviously not, right? Not less than. So we reject the null hypothesis. This is not less than. 0.11 is greater than 0.05. So we reject the null hypothesis. Alpha can vary. You can have 0.01, you can have 0.10. It depends on the domain. Now let me discuss about the next point, which is called as covariance. Yes, if p-value is less than, significance value, that basically means it falls in the tail region. So we reject the null hypothesis. If it is greater, then we accept the null hypothesis. If it is greater, we have to accept, or I'll say we accept the null hypothesis. Yes, in medical domain, it can be depending. Now, like that, you can do for t-test. What all data you require? See, whatever a question I am writing with respect to this, that kind of data you require. Now, in this case also, when I gave this problem statement, here you can see that, right? I have written the same type of question. Suppose the IQ in this is there. So he recruits 20 patient. This is the 20 patient data, and I am basically checking out the Z test. So if mean IQ before meditation is 110 and p value is 0.002, it means that even after taking medication, the IQ will be around 110. It means medication has no effect. Yes. With respect to that specific thing, let's say that it has got medication has been applied before the IQ was 110, and after giving this medicine also it was near 110. Alpha and significance value are one and the same. Okay, let me define once again. This is my graph. Okay, this is this. Initially I got 1 1. This was my p value. This is obviously greater than 0.05, and let's consider about p value as 0.002, which is less than 0.05. When I have this scenario, this basically means I am in the confidence interval. If I am having this scenario where it is greater than 0.05, I am falling in the tail region. I hope now you are able to understand. If I am having this scenario where the p value is less than significance value, I am in the confidence interval in this 95%. If I am over here, that basically means it is greater than the significance level. Yes, if p value is less than, we do not reject, right? In this case, we accept the null hypothesis. We fail to reject the null hypothesis. We accept null hypothesis. Okay, in this particular case, we reject. Now let's go ahead and discuss about the next topic, which is called as covariance. Let's say that I have two data set, two columns, x and y. So if I have these two columns, let's say that this is basically my weight and this is basically my height feature. Okay, in this particular scenario, let's consider that you have some weights. Let's say you have like 50, you have height like 160 centimeters, then you have 60, 170 centimeters, then you have 70, then you have 180 centimeters, and then probably you have 175, you have 181 centimeters. Now in this particular thing, you can what kind of things you are seeing, what kind of relationship you are seeing. When x is increasing, y is increasing, and similarly, can I say when x is decreasing, y is decreasing? So both this relationship will basically follow this specific thing based on this particular data. So when x is increasing, y is increasing. When x is decreasing, y is decreasing. Suppose let's say that I have one more data set, weight and height only. Let's say I have let's consider that number of hours study and number of hours play. Now in this particular case, if I am studying for 2 hours, let's say I am playing for 6 hours. If I am studying for 3 hours, I am playing for 4 hours. If I am studying for 4 hours, I am playing for 3 hours. In this particular case, what is the relationship? You can see that when x is increasing, y is decreasing, or where x is decreasing, y is increasing. So this relationship is basically used over here. So here you can see these two conditions, right? These two conditions. Now This is what you can observe. But the main thing is that how do I quantify? How can I quantify or show some relationship? Quantify relationship through numbers between x and y. Now, in that particular case, I can use a formula which is called as covariance. Now, covariance is basically given by COV x comma y, which is nothing but summation of I is equal to 1 to n, x of I minus x bar, y of I minus y bar divided by n. So this is basically the formula with respect to covariance. If you are working with sample, again this will be n minus 1. Right now, let's consider that we are working with sample. Now in this particular case, you can see what is happening. Covariance of x comma y. Covariance of x comma y is nothing but x minus x bar. X bar is nothing but the mean of x. Y minus y bar is the mean of y. Now when we calculate, you will be able to see either we will get a positive number or a negative number, or I may get 0. Now tell me, what does a positive number basically indicate? So positive number, positive value indicate two things. One is when x is increasing, y is also increasing. When x is decreasing, y is also decreasing. So this shows if this positive number is basically coming, it basically shows or it basically quantifies the relationship between x and y in this particular way. That basically means when x is increasing, y is increasing. When x is decreasing, y is decreasing. So here you will be able to see with this with a positive. Now similarly with a negative number. So with a negative number, here you can find out that when x is decreasing, y is increasing. When x is increasing, y is decreasing. So this relationship you will be able to find out. So this is nothing but positive correlation, I'll say, and this will basically be negative correlation. So here you will be able to see this. If it is 0, that basically means when x is increasing, y is not increasing, or probably there is no relationship between x and y. So understand this particular thing. But let's understand with respect to covariance. Like suppose if I have a data set which looks like this. Now in this particular case, if this is my x and y, what do you think will this be? Whether it will have a positive correlation or negative correlation? Think over it. It will obviously have a positive correlation, right? Because here when the x is increasing, y is also increasing. If the y is decreasing, x is also decreasing, right? Both this condition are getting satisfied. So here you can definitely see this positive correlation is there. And when you are trying to apply this particular formula, you will either get a positive value in this particular case. Suppose if I have another graph which looks like this, this is my x and this is my y. If I have some data points which looks like this. Now in this particular case, what type of correlation you will have? You will basically have a negative correlation. Sorry, I should not say correlation over here. I'll say negative for now because we have not started correlation. But here you will be having some negative correlation, okay? I can also say it as negative covariance. Suppose if I have another data set which looks like this with respect to x and y. If my data set is like this, then what will be my value of covariance? Covariance will be 0 because there is no relationship. Covariance will be basically 0. Now let's understand one basic disadvantage of covariance. Now covariance over here, you will definitely be able to see positive or negative. You will be able to find out the positive or negative correlation. But with respect to the disadvantage, there is no fixed value. You may have plus 100 also, you may have plus 1000 also, you may find out minus 200 also, minus 2000 also. Like this, with respect to the magnitude, there is no such limit. You will definitely be able to see the direction, whether it is positive or negative. But this magnitude is not limited. So if we have two distribution, how much positive, how much negative, that part, if probably if you have two distribution, one is plus 100, the other one is plus 1000, you will not be able to identify because it is just a magnitude value. It is just a magnitude value. Now that is the reason we really need to restrict these values between some range. So for that specific region, we use another one which is called as Pearson correlation. Now Pearson correlation coefficient, what it does is that it basically restricts all your value between minus 1 to plus 1. The more towards plus 1 or minus 1, more positively it is correlated. Sorry. The more towards plus 1, more positively it is correlated. The more towards minus 1, more negatively it is correlated. you should be able to see that, okay, then what is the difference between covariance with respect to the formula? Now for the Pearson correlation, you can basically use something like this, x comma y. It is nothing but, it is very simple, covariance of x comma y divided by standard deviation of x and standard deviation of y. Because of this multiplication, all your values will be between -1 to +1. So here you will be able to see that it is always between -1 to +1. Now, let me show you some examples in Wikipedia. So if you go and search for Pearson correlation coefficient, here you will be able to see this, okay? Now tell me, this particular diagram, here you can see all the points are in one straight line. So when you draw this particular line, your correlation, obviously in this particular case, when x is decreasing, y is increasing, right? In this particular case, if x is decreasing, y is increasing. If x is increasing, y is decreasing. This is the relation that is found. So it is negatively correlated, and if it falls all in the straight line, it is -1. Then here you will be able to see that over here you have some of the data points distributed in this. Here also you can actually see negative correlation, but not all are in the straight line. So your value, your correlation will be ranging between -1 to 0. Similarly, in this particular case, here you can see that when x is increasing, y is also increasing. So here we'll have a positive correlation since it does not follow in the straight line. It is between 0 to 1. If it falls in the straight line, then it is +1. So it captures the linear properties very well, because everywhere you can see that there is a linear line. It captures it in an amazing way. That is the most advantageous things with respect to Pearson correlation. Now in this particular case, here you can see that the correlation is 0. Why? Because we cannot identify when x is increasing, y is also increasing. The data is completely distributed here and there. Now some more examples. Here you can see this is 1, this is 0.8, 0.4, 0, -0.4, -0.8 and -1. And similarly these all are 1, 1, 1, 1. This is 0, -1, -1, -1. And similarly here you can see some more zeros. You can also see some more zeros. This you cannot definitely identify what exactly is this. There is a lot of difference between covariance and correlation. So here your values will always be between -1 to +1 and nothing more than that, okay? Let me search for one more thing, something called as spearman rank correlation. Now you'll be understanding why do we specifically use spearman rank correlation also. So I'll go to Wikipedia. Here, one thing that you have to identify, it captures the linear properties well. Linear, when the line is linear, obviously it will say you 1. Even though the distribution is like this, it will try to create a linear line and it will tell you the value. Now let's go to spearman rank correlation. Now in spearman rank correlation, just see this graph, everybody. This graph over here that you are actually being able to see, this is obviously having a positive correlation because when the x is increasing, y is increasing. And when I try to calculate with respect to Pearson correlation, it is giving me 0.88. You will be able to see that at every point over here, at every point, when x is increasing, y is definitely increasing. In this region, it is increasing by a small amount. So this properties has not been able to capture by Pearson correlation. So that is the reason it is showing you 0.88 even though when x is increasing, y is also increasing. We need to get 1, and that is where spearman rank correlation will come. Because spearman rank correlation will also satisfy non-linear properties. Pearson correlation is good at satisfying linear properties that we have already seen, because if you see this example, it tries to determine the linear properties and tries to give the value. In this case, non-linear properties will also work well. Okay, so spearman correlation. And what is the formula? Probably they will try to change it to the formula. Only one difference is there. Instead of writing, suppose let's say that I'm going to find out the spearman rank correlation between x and y. Here everything will be same. Here instead of standard deviation of x, here you will be having rank of standard deviation of x multiplied by rank of standard deviation of y. Now you may be thinking, what is this rank of standard deviation of x and standard deviation of y? Let me just show you that also. So this is the formula. Okay, I missed one more thing. This will be covariance of rank of x comma rank of y. Now what is this rank of x and rank of y? Let's consider that I have this feature weight and probably age. If this is 170, the weight may be 45. If it is 160, the weight is too high. This is not possible. So I will just say height and weight, let's say. So if I say the height is 170, the weight may be 75 kgs. If I say height is 160, then the weight may be 62. 150, the weight may be 60. 145, the weight may be 55. Now in this particular case, how do I define my rank? This is my x, this is my y. How do I define my rank of x? Now rank of x is very simple. You just assign rank. Over here you have 4 points. Okay, which value you want to give the highest rank? Go and see over here. This is having the highest value, right? Highest value. Or let's say let's consider that I have one more 180 and this will be 85. Let's consider in this you just need to convert this, or you just need to assign rank to this particular data. Now rank basically gets applied to this. In height, if I say rank of x, 180 is the highest, right? So I may give this rank as 1. Then 170 is the next highest. Then 160 is the next highest. Then 150, then 150, 45, right? So here you will be able to see that I'm assigning rank. And similarly, I'll go and assign rank for y. In this particular case, my one rank is 85. Then you have 2, then you have probably 3, then 4, then 5, like this. This rank will be basically used to do this calculation. That is the reason I told, right? Covariance of rank of x and rank of y divided by standard deviation of rank of x and rank of y. So this value will be taken, this will be completely ignored. So this is what is basically the entire Spearman rank correlation, and I hope you have understood. But understand, if someone asks you why do you use Spearman rank correlation coefficient, you should basically say that it captures the non-linear properties. It captures the non-linear properties. Now let's go ahead and let's try to do this one example. Let's go and see something like t-test and try to do it. Let's see whether we'll be able to get or not. So here I'm actually going to show you t-test. So suppose I have this ages. Let's consider I want to initialize this ages. So this is my ages. You can randomly initialize whatever you want because we are just doing a hypothesis testing. Okay. So it's up to you. If you want this ages also, I can ping it in the chat. So this is the ages. Now my main aim is that let's compute the mean of these ages. So ages underscore mean is equal to np dot mean of ages. So if I go and probably print ages underscore mean, so this is 30.34. Now let's do one thing. Very simple. From all these ages, let's consider that these are my population. I will just take a sample of age and then we'll try to verify whether we are coming nearer to this mean or not using t-test, because here we don't know the population standard deviation. So let's do one thing. I'm just going to take my sample size as 10. This will basically be my sample size, and I will just pick up all the sample from this particular ages. So I'm going to say np dot random dot choice. So here I'm just going to give my ages, and this will basically be my sample size. So if okay, I'm getting an error. Okay, random np dot random, still error. Okay, random it became now. Insert random. My goodness. So here now if I go and show you my age underscore sample, here you'll be able to see that this ages have been picked. Now can I basically, whatever mean is basically coming from this, can I actually come near to this population mean with the help of t-test? That is what I'm actually going to. So I'm going to say from scipy dot stats import t-test underscore one sample. This we have done yesterday. Okay, t-test underscore one sample basically means one sample t-test that we have probably done yesterday. That is what we are going to do. Now t-test underscore one sam, here I'm basically going to give you two things. One is my age underscore sample, and probably I want to give and compare with respect to this mean. Okay, so here I'm just going to give you 30. So here you can see that I'm getting the p value as 0.76. If you don't believe me, just go and compute the np dot mean of age underscore sample. I'm getting 31.5, right? Which is little bit away from here. Now it is up to you. I got the p value as 0.76. Now if I say my alpha value is 0.05. In this particular case, my p value is greater than the alpha value. So tell me whether it should be accepted or rejected. Suppose if I execute the same code and I write sample size with respect to 31. Now I'm getting 0.918. Suppose if I execute with respect to this and I take up with my sample as 28. Now I'm getting 0.48. If I keep on doing this and make it to 26, here you'll be able to see 0.27. So this is with respect to different things. I can also even change this. Now if I go and execute this, here I'm getting 0.60. Here I'm getting 0.45. Here I'm getting 0.96. Here I'm getting 0.67. If I try to change this random value again and again, let's say that I have taken now different sample. My sample is mean is nothing but 24.3. Now if I execute this, this is 0.015. It is, tell me, 0.05, right? Greater than 0.05 or less than 0.05. Now in this particular case, it is, if I say with respect to 31, this is 0.006. It is within that confidence interval or not. Similarly, if I go and see with respect to 28, 0.085, 0.397. So here you can basically see. And here I've just taken a small example. Usually in the main scenario, you will basically have a huge data set to check out all these particular things. So this was an example with respect to t-test. Let's take one more example. Now I have a problem statement. I will consider. So my example is that suppose I take the ages of the entire college student. Suppose I take ages of the college student. Now what I'm going to do, I'm going to take the class, let's say one class student's ages I'm going to take, and then I'll probably find the mean of all the ages, and then we'll try to compare whether this will be able to give that specific output. Basically, can we come to the population mean ages of the college student? That is what I'm actually trying to do. So first of all, let's say that I'm having this code. Let's say this is there. Now everybody focus on the code. Here, this is a Poisson distribution. It is just saying that you have to start from 18 age and the mean is 35, and we are going to consider our population ages as 1500. Then we are basically considering class A with starting age as 18, mean as 30, and size that is only 60 sample. So in this particular case, if I go and see school underscore ages, here is my value. And similarly, if I go and see class A underscore ages, so this is my class A underscore ages, which are basically my 60 data. Now let's do something, one amazing thing. First of all, let's try to find out the class A underscore ages dot mean. So here you can see that it is 46.9. Now what I am actually going to do, I'm basically going to apply again this t-test one sam, and here my first data will basically be my class A ages, and then the second parameter will basically be my mean. My mean, I will try to give this specific mean, school underscore ages dot mean. So this will be a parameter. If I go and see over here and press shift tab, you will be able to see that the second parameter I have to give as mean. This is nothing but my pop mean. Now here you can see that I'm getting the p value as this one. So tell me whether this needs to be accepted or rejected. And if I go and probably see the school ages mean, it is far away, right? It is 46.9 and this is 53. If you're considering alpha is 0.05, it will obviously be very. So similarly, you have to reject it, guys, not accept it, okay? Because this is way higher than that. You have to basically get p value less than the significance. Let's say that I am putting this nearer to the class A mean. Let's see what will happen. 47. It is coming somewhere here. Oh, sorry, I have to give this as my sample mean. So like this, you can basically check out all the things and verify it. Whatever we have done, we have done. It is 10 raised to minus 13. It should not be rejected. Guys, it is 10 raised to minus 13. I'm extremely sorry. It should not be rejected. So that is the reason what we do. We can put if. So here I will just say underscore comma p underscore value is equal to this. So if I say if p underscore value is less than 0.05, Then what we do? Print except S0. So what I'm actually getting over here? Okay, guys. Okay, one more final thing that I probably missed out. Let's say that I'm using Seaborn. So df is equal to, because I need to show you correlation and all also. So we'll check out that also so that you'll be able to check it out. Okay. So sns dot load underscore dataset. Let's consider that I'm going to use iris dataset. So this will be my df dot head. So if I use the correlation df dot corr, so this is how my diagram looks like. Here you can see that it is basically showing you the correlation with sepal length and petal length. It is positively correlated. Now see, with respect to correlation also we have various ways. Okay, I'll not use in this. Instead, I can also use sns dot pair plot df. So here also you have a way to see in a diagrammatic way. So here you can see this is how your diagram looks like. Okay, the entire correlation in visualized way. Guys, this will be reverse. Sorry, it should basically write less than or equal to 0.05. So I have written it correctly over here, but in the code I have written wrong. Okay, if p value is less than the significance value, we reject. Okay, code wise, but this wise I have written it correctly. Sorry, this should also be rejected. This should be reject. This should be accept. Anywhere I made a mistake here again. Okay, here also I think accept, here reject. I made one mistake, guys. Again, I'm going to repeat it. See, if p value is less than or equal to 0.05, in this particular case, we reject the null hypothesis. The reason why we do this, because p is basically defining the probability part, right? Now, in this particular case, they are just saying that it is less than 5% probability that the null is correct. It basically says that 5% probability the null hypothesis is correct. This will be applicable in coding, guys. So don't worry, in coding. So this is what it is basically saying. Okay. So if p is greater than or equal to 0.05, here we accept the null hypothesis, which in turn is saying that more than 5% probability, there is a chances of more than 5% probability for the null hypothesis correct. So this is basically for alpha 0.05. I hope now it is clear. Here I have written it anywhere wrong so that this gets solved. This is fine because this is greater than 5.99. Only the relationship between alpha, p value and alpha is important, guys. See, in coding, we always get a p value. So here also, if I go and see with respect to the coding, let's say in this particular case, if I'm getting 0.015, this basically indicates that, what does it indicate? We have to reject the null hypothesis. So here also I will just write a condition saying that this condition will work over here. It is always a confusing thing, p value. Because p value I defined in that particular way, everything is correct. Because see, what exactly p value basically specifies. I'll talk about it. I told you an example of mouse bar, right? If I have like this, here if I say p value is 0.8, that basically means out of all the 100 touches, 80% of time you're going to touch over here. Out of all the 100 criteria. If you say p value is 0.01 over here, one time you are saying. Now, if you are saying p value is less than 0.05, that basically means you have less than 5% probability for the null hypothesis to be true, which is basically present over here. P value less than or equal to 0.05 basically is specifying your tail region, and this is specifying your this confidence interval region when the p value is greater than or equal to 0.0. Greater than 0.0. Always understand this relationship between p value and significance value. Significance value specifies your confidence interval. P value is from the test result. If this is less than or equal to Ci, the confidence interval, or in this particular case the significance value, here you specifically reject the null hypothesis because it is just saying that less than 5% probability it is there. So we reject the null hypothesis. And in the other case, we accept the null hypothesis, okay, when the p value is greater than alpha. The first topic that we will discuss about p-value and significance values. So today I'm going to talk about the exact relationship between this p-value and significance value, because from the tests that we were doing, we were seeing that, okay, most of the tests, from that test, how do we derive this p-value? That is what I'm actually going to discuss about it, and practically also one example will be shown. Then we'll move towards distribution. First we will discuss about central limit theorem. Then we are going to discuss about distributions like Bernoulli's distribution, Bernoulli distribution. Then fifth, we are basically going to discuss about binomial distribution. And then sixth, we'll also be see something called as Pareto's distribution. Okay, I'll include log normal also, right? Log normal distribution. Poisson, Pareto distribution, there is something called as power law. We'll discuss about it. One final thing that is pending is called as F test, which is also called as ANOVA test. This will take 1 hour time, guys. Just to do this, I will upload a separate video. Okay, I'll upload a separate video on the same. Today I will show you how you will derive the p-value. So we are basically going to see how do we derive the p-value and what is the relationship between p-value and significance value. So this all things we will be discussing. Let's take a problem statement. The problem statement, I'm going to take it off as that test, and let's write down the question. Before that, everybody ready? Take up your book and pen. I've already discussed about permutation and combination, guys, in the previous session. The question is nothing but, it is very simple. The average, we'll do a z-test problem and then we'll try to derive this. The average weight of all residents in Bangalore city is 168 pounds. We take a sample. Now we take a sample. Okay, one data I have missed. So over here, the average weight of all residents in Bangalore city is 168 pounds with a standard deviation 3.9. Now, what we are saying, we take a sample, 36 individuals, and the mean is 169.5 pounds. From this information, we really need to check whether this sample is being able to tell us the weights are same or not. Okay, so this is what it is given, and our confidence interval is basically 95%. So over here, you know what is your mean? My mean is 168 points. The standard deviation is 3.9. The x bar is nothing but 169.5, and my n sample is greater than 36. And obviously my n sample is given, my population standard deviation is given, so I am going to basically use z-test. Very good. The alpha value is 0.05. 1 minus 95% is 0.05. Let's go ahead and solve this particular problem. So what is your null hypothesis? Mean is equal to 168. What is your alternate hypothesis? Your mean is not equal to 168. Then what we do, we basically come to the second step where we specify our alpha, 0.05. The third step, we basically find out our decision boundary. So my decision boundary is quickly how much? It is nothing but, it is this graph. It is a two-tailed test. It can be greater than 168, less than 168. So here I have basically 0.025. Here I have 0.025. Here I have 95%. Now what is this value that I can get from the Z table that we see? Can I say 1.96 plus minus 1.96? If you open a Z table with respect to 1 minus 0.025, you will be getting 0.9750. We are going to check this area of curve, and usually we get 1.96 and minus 1.96. Now the next step, I hope everybody is clear because we have already done this in our previous session. Next step, we do that is my fifth step, we calculate the z-test. Now z-test formula is very much simple. I hope everybody remembers it. X minus mu divided by standard deviation of root n. What is x? 169.5 minus 168 divided by, what is standard deviation? 3.9 root by 169.5, guys, not 1, root of 36. So here we are basically going to get 169.5, 1.5 divided by 3.9 multiplied by 6. So 2.307. So right now, let's go to our decision rule. My Z value is 2.307. Is it greater than 1.96? It is greater than 1.96. So we reject the null hypothesis. But this is already we have done many number of times. Okay, we have done many number of times. But now one step will go ahead. This is fine. This is one way of solving this problem. But where does p value comes into existence? Where does p value comes into existence in this particular case? Now what it is saying is that initially this graph I was checking it for this to this where it was plus 1.96 minus 1.96, and obviously I got 2.307, so it is falling somewhere here. It is falling somewhere here, right? If I'm considering 2.307, it is falling somewhere here. It is on the top hand side. So we are rejecting the null hypothesis. Now if I really want to find out the p value, what I am actually going to do, I'm going to remove this, and now my curve will be a little bit bigger because based on this I got the z value as 2.307, and here also I got minus 2.307 because both are symmetrical. Now the next step what I will do, I will take out my z table and I'll try to find out what is those values with respect to my z score of 2.307, right? So what I'm going to do over here, 2.3, I'll check based on this z score, what is the area under the curve? What is this specific area? I really need to find out. And I don't know what is the area right now. So I will go ahead and calculate it. Now based on 2.307, okay, so 2.3 is here and 07. If I say 07, it is somewhere here. So 2.307, I am getting somewhere around 0.99111. I hope everybody is able to understand what I am getting over here. 0.99111, right? So what I am getting over here, it is nothing but 0.99111. So here, based on this, my area under the curve is basically 0.99111. So this, with respect to the area under the curve, I am actually getting this. Now, understand one thing. If I subtract with 1, see 0.99111 is basically the area under the curve of this particular curve. Now, if I subtract this with this, how much I will be getting? So this area is nothing but 0.0089 and this is nothing but 0.0089. So I am getting 0.0089, 0.0089, right? So this, you can see this 889, sorry, it is 889. So here I get 89. Here also I am getting 89. Now, according to the p value, now see this middle one is 0.99111. If I add up all this particular value, I should be getting 1. And if you add it up, and probably you will be getting 1. P value is nothing but I have to add this area of curve of this tail and this tail because it is two tail. I have to add this up and then this will basically give my p value 0.00889. So once I add this particular value, I am actually going to get 0.01778. Is it not 0.889 divided by 2? No, because see both the area are symmetrical. Understand one thing, both the area are symmetrical. If I am getting one value over there, probably I'll be able to see that specific part, right? Because this part is symmetrical to this part. Do you think it is divided by 2? No, I don't think so. It should be divided by 2. It is basically considered at this part and this part, right? 0.99111. Oh yeah. Should we divide by 2? Yes. Then only probably I will be able to. Okay. So probably we are getting more than 1. So over here, I'm getting 2.307. 2.307 is greater than 1.96. With respect to 2.3007, I am actually getting the value as 0.99111. Okay. So 1 minus 0.99111 will be nothing but, so 0.0044, this area 0.0044. Now if we add it, we will be getting till 1. Now in order to get the p-value, I will take this area 44 plus 0.0044. Now here you can see that I am getting 0.0088. Now this is basically my p-value. Okay, because based on the real z-score that I have got, I'll be deriving my p-value from here. Now, obviously we know that we have to reject the null hypothesis. Now from the p-value also we can actually verify. Here, now this p-value is obviously less than 0.05, right, which is my significance value. So obviously 0.0088 is less than 0.05. So what happens over here? We basically reject the null hypothesis. So here we are rejecting the null hypothesis. Suppose if this p-value is greater than 0.05, always understand two important points. One is p-value is less than your significance value. I hope you understood how to calculate the p-value, right? So if this is less than or equal to the significance value, this means we have to reject the null hypothesis. If the p-value is greater than significance value, then what we do? We fail to reject the null hypothesis. We fail to or accept the null hypothesis. We fail to reject the null hypothesis. Now it is clear, guys, from the yesterday's session. Now you can try out in every problem that we have probably discussed this many days. See, guys, whenever we have a Z table, right now, one thing is that first of all, I'll check with 0.025. 1 minus 0.025 is 0.9750. So if I go and see, probably somewhere you'll be able to see 0.9750, where it is here. So it is nothing but plus 1.9 and this is 6. But we saw that our real Z score was coming as 2.37. 2.30. 2.30 is this one. Okay, guys, 2.30 is this one. I took 2.307. Okay, so again, there was a confusion over here. You can also take this one. See, 1 minus 0.9828. 1 minus 0.9828. You can also do this. 1 minus 0.9828. So if I subtract this 1 minus 0.9828, 0.0172, if I divide by 2, this will be 0.0086. You can take this up. Okay, again I'm going to repeat this. Okay, let's say I'm planning to repeat it. Okay, fine, not a problem. See, initially what I got, my value was this, right? I got this as minus 1.96, this as plus 1.96. But based on the Z score calculation, how much we got with respect to Z score calculation? Here you can see I got 2.307. Okay, 2.307. So here I'm actually going to get 2.30. Okay, let's take this. So obviously my Z is 2.30. It is greater than 1.96. So I have told you we have to reject the null hypothesis in this case. This is with the help of Z score. Now what I'm actually going to do? Let's calculate the p-value. Now in order to calculate the p-value, okay, what I will do? I will rub this and I'll try to find out the area with respect to this Z score, that is 2.30. So plus 2.30 minus 2.30. And I will try to find out what is this area, and based on this I will be able to find out this area also. So let's go ahead in the Z table now. So this is my Z table, 2.30. Okay, 2.30. So here is my value, 0.98. See this, guys. I'm again repeating it, 2.30, right? This is my Z square value. So 0.98928. So here I'm actually getting 0.9828, right? So this is my area under the curve, 0.9828. I guess 0.9828 only, 2.3, 0.98928. Okay, 0.98928. Now when I subtract 1 minus 0.9828, then I will be getting this area and this area, right? Since I will have to get this particular area, so I have to subtract with the whole 1. So if I go and calculate now, 1 minus 0.98928. So it is nothing but 0.0171072. Now understand, this is not one tail test, this is two tail test. So I have to divide the area from here to here also. So that is the reason why I divide by 2. So I'm going to divide by 2. So I'm actually going to get this as 0.001 minus 0.98928 divided by 2. So it is nothing but 0.00536. Then 0.00536. In p-value, I will add this two term. Understand, guys, what I am actually trying to do. You have to check out the Z table. So if I add this, probably, then I will be getting some value, and then check whether this is less than significance value, less than alpha, less than or equal to alpha, then you reject the null hypothesis. And obviously, this case also it will be less than. Let's solve this problem. So the average age of a college 24 years with a standard deviation 1.5. So this is a college over here. So average age of a college is 24 years with a standard deviation of 1.5. Now what I am actually going to do over here is that I'm just going to say that, okay, fine, the average age of the college is this much. So we take a sample of 35 students. Let's say that the mean, we take a sample of 35 students, and we find out that the mean is 25 years. Then with alpha as 0.05, that is the confidence interval as 95%. With alpha as alpha as 0.05 and confidence interval, do the age vary? Okay, so this is the question. H0, you'll say mean is equal to 24. H1, you'll say mean is not equal to 24. You know your standard deviation, it is 1.5. You know your n value, it is 35. Let's take it as 36. Okay. And then your x bar is 25 and your alpha value is 0.05. Now tell me whether this is a two-tail test or one-tail test. It's a two-tail test. So here you have your alpha as 0.05. Now if I make my confidence interval, my decision over here, this will be 0.025. Why 0.025? This 0.05 will be divided into two regions since it is two-tail test. If it is a one-tail test, focus over here only, no? Focus over here only to solve it. Why you don't have to worry about all those things, Then let's go and solve with respect to z-score. Z-score x bar minus mu divided by standard deviation by root n. So what is my x bar? It is nothing but 25. 25 minus 24 divided by 1.5 multiplied by 6. So it is 1 multiplied by 6 divided by 1.5. Go and calculate it. The z-score is 1.2. You know the decision boundary. What is the decision boundary? Plus 1.96 plus 1.96. Right? Now you are getting 1.2. If you are getting 1.2, then obviously 1.2 is less than 1.96. Should we reject or accept the null hypothesis? 4? Are we getting 4? Oh, sorry, it is 4. Extremely sorry. Now, if you are getting 4, the 4 is greater than 1.96. So we reject null hypothesis. Now, what you are going to do for this particular 4? You have got a 4 value, right? So this will be your plus 4. This will be your minus 4. Now go to the Z table, try to find out what is the 4 value. So go over here, try to find out what is 4. It is 0.99997. 497s, right? So it is 0.9997. So I will go and subtract this to this. Now if I subtract this to this, what will happen? And I have to divide this by 2 since this is what? Two-tail test. So this side will basically be my area as 0.004015, and this will be my area as 0.4015, and this middle one will basically be 0.9997. Now what is my p-value? My p-value is 0.00015 plus 0.00015. So what this will be? This will be nothing but the same thing, 0.403. 0.403. Now my p-value is obviously very, very lesser than significance value. So what we have to do? We have to reject the null hypothesis. Reject the null hypothesis. So here you can definitely say that with the sample size that we have taken, definitely we will not be able to conclude that the mean is that much. So let's go ahead with log normal distribution. Okay guys, so Log normal distribution, usually log normal distribution, it will have this kind of shape. Obviously, we have seen a lot of examples like wealth distribution. These all things are actually there. So this was the example of log normal distribution. Now suppose I say that if if y is a random variable that belongs to a log normal distribution with mean as with some mean, let's say that this is there, it belongs to a log normal distribution, then if I apply log of y, then it should follow a normal distribution. So if it is satisfying this condition, we can say a distribution is basically in this kind of log normal distribution. So log normal distribution I have already discussed in the previous section also. A lot of examples are there. People writing comment session, people writing bigger comments, people writing, there will be very less number of people who write big comments, right? Big comments. So this is one example. And again, this is also, I have uploaded a detailed video in my stats playlist. Let's go to the next distribution. If I say that next distribution is there, so I will talk about Bernoulli's distribution. So let's talk about Bernoulli distribution. Okay, let's start over here and talk about Bernoulli distribution. Now in Bernoulli distribution, you can see that it's more about P and Q. It's more about, see, whenever you have a Bernoulli distribution, that basically means you need to understand there are only two outcomes. So if I go and probably open it over here, in Bernoulli distribution, there are specifically two outcomes. Two outcomes basically means that it can be either 0 or 1. Let's say that I have two outcomes of 0 or 1. But I really need to find out the probability, you know, when we need to focus on probability with respect to Bernoulli distribution, we define by two values. One is P and one is Q. Suppose I say I'm considering an experiment which is called as tossing a coin. In tossing a coin, I know what is the probability of head. Let's say that I'm getting probability of head as 0.5. So this will basically become my P value. Okay. When I talk about the Q value, it will become 1 minus P. Okay. That basically means it's the probability of head, because when we are probably tossing a coin, there are two choices. Either you get head or either you get tail. So when I say probability of head is 0.5, so this is what one outcome probability is there. What about the other outcome? So that is nothing but 1 minus P. So here if I have 0.5, then Q will be 1.5, then this will be 0.5. Suppose I do not have a fair coin. Now in this particular case, and this is only related to single trial, not multiple trials. Single trial distribution. Now let's say that I do not have a fair coin. Let's say that my probability of head is 0.3. Now in this particular case, what will be my probability of tail? This is basically P. Then my probability of tail will obviously be Q, which is nothing but 1 minus P, which is nothing but 1 minus 0.3, 0.7. So this is basically 0.7 over here, you can see over here. Now similarly, if I go and probably discuss with respect to this, here you can see that a Bernoulli distribution named after Swiss mathematician Jacobi Bernoulli as a discrete probability distribution. Now here you see this, okay? Three examples of Bernoulli distribution. Here the probability of x is equal to 0 with one of the outcome is 0.2. So we are drawing this graph, this line. See, this will come as 0.2, this will come as 0.8. Over here, next outcome you can see over here is 0.8 and 0.2. So this is how you basically create in this 0.8 and this is 0.2. In the green color, you can see 0.5 and 0.5. So this is my 0.5 and 0.5. Now understand one important thing. Whenever we draw this kind of experiment, if we draw in the form of graphs, on the left hand side, obviously, you know what will be there with respect to this, and the right hand side, there will be probability. So this is basically 0.2, 0.4, right, 0.6, 0.8 and 1. Now suppose let's consider that I have one coin. Over here, this one coin is basically head, this is basically tail. Now, if I try to show you with respect to the probability of head and tail, I can basically draw. Suppose if I say this probability of head is 0.5, so I can draw this line like this. I can basically draw this line with respect to this and this. Then if I'm drawing this line, then probability of tail will also be 0.5. Suppose if I say the probability of head of not a fair coin is nothing but 0.8. Then we will draw a line like this. Here I can basically say then what will happen if this is 0.8, then this will become 0.2. So this is how we basically draw this, and this is not a probability density function. Understand, This is a probability mass function. In probability density function, it is completely different. Probability density function is for continuous variable. This is specifically for categorical variables. So this probability mass function that we have over here, we'll basically say it as PMF. Before we used to say it as PDF. So whenever we have this kind of variables, categorical variables at that point of time, this is basically called as probability mass function. So I hope everybody is able to understand with respect to this. Now let's go to the Wikipedia page. So here you can see probability mass function, and the same thing probability mass function is saying. If k is equal to 0, I will write q is equal to 1 minus p if k is equal to 1. And the PMF is basically defined in this particular manner. Any probability that I want to form, I want to find out, this is how the formula is basically utilized. We really need to know only this much things about the distribution and one probability formula. This was with respect to Bernoulli distribution. Now let's go ahead and try to discuss about binomial distribution. See, binomial distribution is also very much good. Till now we discussed about single trial, right? Single trial, whenever we take up multiple trial, then it becomes a binomial distribution. Inside this, let me write it down over here. So if I go and see with respect to binomial distribution says that obviously with respect to every trial, there will be a Bernoulli distribution, but here we have multiple trial. That basically means we have the combination of many Bernoulli distribution over here. Suppose in this trial, my probability of head is this much. Suppose in one more trial, I will go and write probability of head is 0.6. This is 0.4. Like this, I will be having many trials combined together in one kind of binomial distribution. Whenever you have a categorical variable, and whenever we try to draw this kind of diagram, then it is called as a probability mass function. In the case of a continuous variable, we have probability density function. So if I go and probably see this, the binomial distribution is given by two notation, n comma p. So n is nothing but number of trials, p is nothing but success or probability for each trial, where q is equal to 1 minus p. Okay, and this is the formula with respect to the probability mass function to calculate the probability of a binomial distribution. Now this is done. Now let's go to one very important distribution which is called as Pareto distribution. Now Pareto distribution is a non-Gaussian, it is not a Gaussian distribution. It looks something like this. One application of Pareto distribution is nothing but power law distribution. So if I show you power law, so here everybody see this diagram with respect to this. I'm just going to take a snippet of it. We'll discuss about this. This is something very much important. Okay. Let's paste it over here. Now in this particular case, when we are discussing about power law distribution, let's see that what important information we can take out from this. Power law distribution basically says that you have to remember this rule which is called as 80-20 rule. You can see that this is probably my 80% of this entire value and this is my 20% of the entire value. My x-axis may be something, my y-axis may be something. But understand, the 80 of one kind of distribution will be falling here and remaining 20 will be falling here. Let's say take some examples. Okay, now suppose if I say that 80% of the wealth is distributed with 20% of the people. The second question, any example, any other examples? Can I say 80% of the company projects are done by 20% of the people? 20% of the people in a team. 80% of sales is done by 20% of the most famous project. Any example? More. One more example I can take. 80% of the match, cricket match, okay, let's say, is won by 20% of the team. 80% of videos are completed by 20%. 80% are serious out of all the 100%. Like 80% of the syllabus are completed by 20% of the people. 80% spamming on YouTube video has been done by 20% of the people. Yes, any kind of examples you can basically take. You can also consider salaries. You can also consider, yes, 80% of oil coming from 20% of the land. So whenever you have this kind of distribution, it is called as power law distribution, and this is also called as a Pareto distribution. Now listen to me one thing, guys. This is something very much amazing. Right now, this diagram that you see looks something like this. Right? If I extend this diagram and probably make it like this, if I probably extend this diagram if I extend this diagram and make it like this, see this is a very important thing. Then what kind of distribution this is? This is my power law distribution. What distribution is this? This is not normal. This is, can I say this is log normal distribution? Log normal, guys, not normal. The right hand side over here, this will get extended by a lot. Log normal distribution. Probably I did not draw the diagram properly, but it is a log normal. Log normal, right skewed data. Something like this, let's say. So this specifically is a log normal distribution. So there is a very good relationship between log normal and power law distribution or Pareto distribution. So mathematically, if I talk about, you can also convert this distribution into normal distribution also. And for this, you have to watch one of my video, which is called as transformation, data transformation. So definitely check out those video, and probably this is what is basically spoken about it, So that is called as Pareto distribution with respect to this. Now guys, yes, box cost transformation is basically used in order to convert this data into normal distribution. So probably you will be able to see from that video link that I have actually given. I can also show you the code. So this is how the code looks like. I've covered everything, guys. Now it's your time to flourish and learn everything. See over here, all the transformation, normalization, standardization, scaling, this, square root, everything is given over here. So this is here I have also discussed about QQ plot. So if I go and probably show you, so all the transformation is basically used. I've used all the transformation in this. You have to follow that video, guys, because it will probably take me 1 hour to explain all these things. See, this is what is QQ plot is. Reciprocal transformation, logarithmic transformation, then you have Gaussian transformation. These all transformation are the logarithmic, reciprocal, square root, exponential transformation, box-Cox transformation. So all this transformation is basically used in the initial stages. We basically apply with respect to all the features, and then we'll be able to. Can I say this distribution follows what kind of distribution this image follows? So it is in the same link in the YouTube channel that I've actually given. What kind of distribution this follows? This follows a Pareto distribution, a power law distribution, right? So we can basically use a box cost transformation to convert this data. So if you go through this, you're well covered with respect to everything. So central limit theorem basically says that if I have a distribution that is either normal, that is not normal, or that is any kind of distribution that I have, whenever we basically take up multiple samples, let's say that I have this distribution or this distribution or this distribution. If I take up some multiple samples, let's say that n is greater than or equal to 30. If I start taking multiple samples from this particular data, let's say that I have taken multiple samples like this up to n is greater than or equal to 30, like many samples, okay? And for every sample, if I start finding the mean, like this up till xfm. Why I'm saying n should be greater than or equal to 30? Because the more greater than or equal to 30, the more the central limit theorem holds, okay? So if I take this entire data of this sample mean, all this sample mean, and if I populate it in the form of PDF, then that basically says that it will get converted into a normal distribution. So this will basically be a normal distribution. All the sample mean will follow. This sample mean will follow a normal distribution. So here you can see that whatever distribution it may be, if we take some samples, specifically n is greater than or equal to 30, for each and every sample, if I try to find out the sample mean, sample size. So see, sample size, I told you it should be n is greater than or equal to 30. Sample size, the number of elements over here that we are picking, should be greater than or equal to 30. And let's consider that we have taken m samples. M samples can be anything, but more the bigger value, more better we will be able to solve this particular central limit theorem. So here you will be able to see that as we go on doing this, finally you will be able to see that if we populate all the sample mean, we get this normal distribution. Initially, whatever distribution that particular data may be, it may be a log normal, it may be normal, it may be anything. Now one assignment for you all will be Poisson distribution. Now you have got a lot of idea about data now. Okay, you just go and search in Wikipedia, see the distribution shape. This is also a non-Gaussian distribution. It also follows the Pareto distribution. You can see in this way. Just go and check it out. That's it. This was it from my side. Have a great day ahead. Thank you, one doll. Bye bye. Keep on rocking, keep on learning. Bye bye. Thank you, guys.